My name is Andreas, and in this video we'll train a convolutional neural network from scratch to classify audio files. Then we'll build a simple app to upload audio and visualize the convolutional layer outputs for better understanding. We will start completely from scratch with a quick crash course in neural networks. We'll cover how neurons, activation functions, and layers work and how we can train full networks. Then we go in depth with the theory behind convolutional neural networks. We'll talk about data representation, how kernels slide across inputs, feature maps, layer depth, common hyperparameters you might tune for CNNs, how CNNs can be used for classification, other layers you might see in conjunction with convolutional layers, and much more. Lastly, we will completely cover the architecture of the neural network which we'll build, including every component in the neural network and its purpose, along with how we go from input data to classification. Now we are ready to convert the conceptual architecture to code. We'll build out the entire model in PyTorch. Then we'll build a program for training our model. The program downloads the dataset and converts files from raw audio to Mel Spectrograms. The model trains for 100 epochs and then saves the model with the highest accuracy, which is 83%. Also, everything in this video, including training, will be done completely for free. We trained the model on serverless GPUs with Modal, and we can follow the progress of the training program in the Modal dashboard. Tensorboard is also set up, and we can visually see how the loss goes down over time while accuracy goes up. We log training and validation loss, validation accuracy, and the learning rate. After training the model, we'll create an inference endpoint where you can post an audio file to and get back predictions and the data required for visualizations. We can also see the status and logs of all requests in the Modal dashboard. We'll then build a frontend in Next.js with a simple dashboard that visualizes the raw audio, the input spectrogram we converted to, and the output of the convolutional layers. All output channels from the convolutional layers are aggregated into simple heat maps that visualize the features extracted by the model. We can then see how the model goes from extracting low-level to high-level features layer by layer. If you are ready to learn about convolutional neural networks from scratch, let's get started with the video. We can start out with an introduction or a recap to neural networks if you're already familiar. So first of all, a neuron is the basic building block of a neural network. A neuron can have multiple inputs and also a single output. And the output is determined by the inputs and then the weights, biases, and the activation function. So each input is multiplied by a specific weight per input. And the weight right here determines the importance of each of the inputs. When this then has been done for every single input, a bias is added onto that. That is the B you see down here. And then the result of this entire formula right here is then put into an activation function. And the output of that activation function will then be the output of the neuron. So basically, a neuron is a tiny calculator. It takes several numbers as input, multiplies each input by weights. That is how important the input is. And then it adds a bias value. It then passes this through an activation function, so it's basically just like a normal mathematical function, and then this will produce a single output. And then the entire meaning behind neural networks is that these weights and biases will be initialized to random values whenever you create the neural network for the first time, but then when you do train the network, these weights and biases will then be tuned to make sure the input matches what you actually expect to see. So now that we know how the weights and biases are used, we can go down and talk about the activation function. So that is down here. So an activation function is just like a normal mathematical function. Down here we see an example of one called ReLU that is super common and you'll probably see it a lot. So ReLU is an activation of an activation function, an example of an activation function. So it's just a mathematical function that only allows positive values to pass through. So let's say you have a list of numbers right here. Well, then all the negative numbers will just be set to 0. So minus 2 will just be set to 0 right here. But all the positive values will pass through just like normal. So down here, instead of having a linear line that goes below 0 on the y-axis, all the negative values will just be set to 0 instead. This means that instead of having a linear line that looks like this, the linearity will be broken, and then you'll have a network where nonlinearity is introduced. So why do we have these activation functions? Well, for now, you just need to know that they introduce something called nonlinearity. This lets the network go beyond simple linear patterns, so just linear functions stacked because you have multiple neurons. And instead, we'll be able to learn more complex functions that more accurately model real-world problems. Because real-world problems often can be modeled simply by stacking linear functions on top of each other. So now that we know what an activation function is and what a neuron is, let's go further down and talk about layers. So layers is when we combine multiple neurons to then create a more complex neural network. So up here, it is pretty simple. We only have two weights and then a single bias, which we can tune to make sure the output reflects what we want to see from these two inputs. Because that there are so few of these values which we can tune, we won't really be able to generate a very complex neural network. So therefore, the power of neural networks is putting multiple of these neurons together to form a large network where a lot of these weights and biases can be tuned, such that the neural network can learn more complex patterns. That is what we do down here with the layers. So each of these circles right here is a neuron of itself, and the same one for these circles over here. So this is a layer, and this is another layer. And these layers are fully connected, meaning every single output from this neuron, the output from this neuron is passed into every single input of these neurons. So this one will be passed into 5 different neurons in the next layer, the same for this one, and the same for this one. This also means that every single one of these neurons will have 3 inputs because there are 3 neurons before that layer. So if we take this neuron here, right here for example, going up to the initial example, we would have 3 inputs, x1, x2, and x3, and then we would have a weight for each of those. Then I'll just hop back down again. So a single neuron is pretty simple, but a layer combines many neurons, each with its own weights and biases. They then all get the same input, but they will produce different outputs. This will let the layer detect many different patterns at once. So each of these different neurons will get the same outputs because the layer is fully connected. But because the weights and biases are initialized randomly for each of these neurons, each of these will learn to detect specific patterns in the data that is inputted into these neurons. So therefore, more complex patterns about this data right here can be learned in this layer right here. So far we have taken a look at how a single neuron works, but also how we can combine these neurons. But how does the math actually look whenever we combine multiple neurons together in layers? Well, that is what we call a forward pass. So right here we have 2 different neurons and then a single neuron in this layer coming after that. So this is a super simple example of a neural network, and you probably would never create a neural network this simple. It is only for illustration, just so we can show you how the math actually works. So first of all, we have 2 different inputs right here. We have 2 and 3. These will be the inputs for this layer right here. This layer in the middle is called a hidden layer, and the reason it is called a hidden layer is because we don't really care what the weights and biases are. We won't really track those manually. The only thing we're interested in is whether the output seems correct for the input which we're giving the neural network. So all the layers between the inputs and then the output layer over here is then called hidden layers because we only care about the actual states of both the weights and biases within all of those neurons inside those layers. It is simply too many numbers, so it don't make sense to track it manually. Over here we have an output neuron. This neuron will produce a single number, and this will be determined by all the math which I'll show you right now. So just like before, for each of these neurons we have some outputs and some inputs. We also have weights and biases. So this neuron right here will have 2 inputs. It will have 2 and 3. So those are the lines you see right there and right there. There is a weight attached to each one of these lines. So we'll have a weight of 0.3, which 2 will be multiplied by. We'll then also have a weight of 0.1, which 3 will be multiplied by. This will then be offset by the bias 0.4, and this will then be passed through the ReLU activation function. So the math formula will look something like this up here. This will then equal 1.3, which will be the input for the next neuron over here. The exact same thing can be done for this neuron here, except that the bias and also the weights for each of these lines will be different. So for this one, the weight is going to be 0.2 for the first input, and the weight is going to be 0.6 for the second input right here. So for the first input, we'll take 0.2, multiply that by 2, which is the input. We'll add that to the second input, so that is going to be 3 multiplied by 0.6, the weights. Then we'll add on the bias to that, 0.2, which we get from down here. And this will produce an output that is 2.4. If this would evaluate to a negative number, this would then just be reset to 0 because we have the ReLU activation function wrapping around this equation right here. So now we actually have the 2 inputs for the next neuron right here, and these will also have 2 weights attached to them as well, and a bias. So we can take the inputs, so 1.3, multiply that by 0.9, so the input multiplied by the weights. We can do that for the other input as well, 2.4 multiplied by 0.6, and we'll then add on the bias. this is going to be a positive number as well. So even though we pass it through the ReLU activation function, nothing is going to happen to this evaluated statement just because it is positive. And finally, the output of this statement right here will then be 2.61, which will be the final output of the neural network. So internally, whenever you use a neural network, this is basically what happens. You have a bunch of inputs. These will be evaluated through some neurons by transforming them with their weights and also biases. And then you'll get some output numbers from that neural network, which we can use for the purpose for whatever the neural network was trained for. So right now I've basically just set random weights and biases for all of these different nodes. But in real life, when the neural network is created, all of these is set to random values, just like I did. But then whenever you do train the network, you'll then get different values for both the weights and biases, such that the output of the neural network will accurately represent what you actually want it to be. So let's say this neural network right here was for determining house prices, and then you have the number of rooms as the first input, and for the second input you would have something like the square meters total in the house. So maybe the number of rooms is way more important than the square meters in the house, so the weight for the number of rooms is pretty high, while for the square meters in the house it is pretty low. Well, these are some of the changes that will happen to the weights and biases whenever the neural network is trained. And this will then be reflected in the output answer over here. So what actually happens when we do train the neural network? Well, we can take a look at it down here. So let's take a look at an example of a network first of all, and then we'll go through how training works right after that. So in this example right here, we'll take a look at the MNIST dataset and then how we can create a network to process that. So I'll just go in and search for MNIST. So MNIST right here is a super simple dataset for training neural networks. So you see all of these different numbers right here. I also have an image of it down here. You have a bunch of different images, 28 by 28 pixels wide and tall. And these images just represent handwritten numbers. So you have a bunch of different zeros written. You also have a bunch of different 2s, 3s, 4s, etc. And then each of these images are then labeled by what the actual number is. So what we'd have is that we have a 0 right here, and then we say, well, a 0 can be written in all of these different ways, even though they look slightly different. So we would like to train a neural network to accept an image like this, and then be able to say that the image is actually a 0, even though that they are slightly different for each of these images. So that is the dataset that we're working with. Well, going up here, we can take a look at how these images are represented. So basically, they're just pixels. We have a 28 by 28 pixels for each of these images down here. So we can take these pixels and then just break them down to a single list of pixels. If you multiply 28 by 28, you'll get 784 as the result. So we'll create an input layer for this neural network with 784 neurons as the input layer. This corresponds to one input neuron for each pixel in the image, and then each pixel will be fed into its own neuron as the input for the neural network. So the absolute first pixel up here in the top left corner will then be fed into the first neuron. The second pixel in the top left corner will be fed into the second neuron, etc. for every single pixel in the image. Then we'll define some hidden layers between the input and the output layer over here. The hidden layers will just be containing a bunch of neurons such that there is a complexity to the network. So basically there is enough weights and biases for the network to be able to learn the relation between these images and then the outputs. So you might have 100 neurons for this one, and then you might have, let's say, 300 neurons for the second layer, and maybe that is enough neurons for the network to actually be complex enough to learn the relation between the image and then the output. The only way you can really figure out how many neurons are enough and how many layers are enough is by testing yourself or by looking at other examples of how people have built similar neural networks in the past. So all of these different neurons will flow into every single layer after that because the network is fully connected. And then after passing through these hidden layers, we'll then see an output layer over here. So we will have a single output neuron for each number the image could be classified as. So down here we see that we have 9 different categories, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll have 9 different categories, 9 different labels that the image can be classified as. So we'll have a neuron for each one of those. So we'll basically just have 10 output neurons. Each of these neurons will then output a number, And this number will represent the probability of the image being each one of these different labels. So if this is the first neuron right here, if this is the neuron representing the number 1, and this is the neuron representing the number 2, the output of the network might be something like 0.9 right here. And then the output of this one might be something like 0.1. So this is a 7 right here, so it looks pretty much like a 1. So this will then have a pretty big probability of the image being a 1, while it is a pretty low probability of the image being a 2. So that is kind of how we work with these neural networks. We get probabilities out that the input matches a specific output neuron over here. So this is a pretty basic example of how a network can be structured, such that we can pass in an image and then we can get out a label for what the image actually is. Cool. So how can we take this network and then train it? Because right now, all of these weights and biases, both for the input, hidden, and the output layers, will just be random weights and biases. So if we put in a 7, it is really just randomly guessing what the number actually is. So it is pretty much just garbage output and it's pretty useless. Before this network can become useful, we'll need to tune all of the different weights and biases to make sure that the network will learn the relation between the input and then the output, so we can use it in a generalized way. Cool. So down here, we can take a look at how we can do training. First, you'll need to know what a sample is. So this is a full dataset containing multiple different images, and then also for each image, there is a label that says what the image actually represents. So this image is just 28 by 28 pixels, but then the label is going to be 0, so what is actually within the image. So this right here, the image would be the input for the neural network, and the 0 out here would be the output of the network. We call the input right here the feature, and the output the label. So a sample is just a single set of both a feature and then also the corresponding label that is part of that. So for each of these different images, all of these are then labeled. This means that this right here we know is a free because we have a dataset that has labeled all of these. So we therefore have a bunch of samples which we can use to train the network. So the first thing we're going to do is actually divide the training dataset, dataset into two different parts. We'll take 80% of the dataset and make this a training dataset. And then we'll take the rest of the 20% and make this a validation dataset. It is still the same dataset, it is just 80% of the data, so we just take 80 random samples and make it into this one, and then we take 20 random samples, so the rest of them, and make it this one. And then we can take this training dataset right here and actually train the model on this, and this means that the model will be trained on this. So to prevent the model actually just remembering the dataset, for example, we have a different dataset for actually validating that the model is able to generalize what it has learned, so we therefore show it data that is similar to what we have trained it on, but isn't exactly the same. So by comparing how the model performs on both the training and validation dataset, we can figure out if anything went wrong in learning, and then also what we should change to actually fix that. So the first step of training the network is going to be running a sample through the network with the forward pass. So the forward pass is what we saw up here, where just pass in some inputs. This is going to be the feature which we pass in. And then we can compare the model's output right here with the output that we know is true because we have labeled the samples right here. So we have both the input but also what the label should actually be, so what the output should actually be. And then we can compare those two to then tune the model to be trained to this data. So we do a forward pass and then we compare the network's prediction with the real label, so what we know is true. And then we calculate a loss. And a loss is simply just a number representing how good or bad the network is at predicting right now. So if the number is all wrong, so if the output of the network is all wrong, it does not at all match the labels that we know are true, then the loss is going to be pretty high. But if the network is getting a lot of these wrong, a lot of these right, then the loss is going to be very low. So when we do train, we should see the loss going down in a graph over time. So now we have run a sample through the network and then we have calculated a loss, so how wrong the network actually is. And the next step is then using something called an optimizer to determine how the weights and biases the values of these weights and biases should be changed to then improve the loss. So as I explained earlier, the magic of neural networks is being able to tune these weights and biases right here to make sure that the specific inputs give the correct outputs. And the only thing that can really change the output is changing these weights and biases, so that is what the optimizer does. And this entire process is called backpropagation. So how it works internally is that partial derivatives are calculated for all weights and biases that will then give the direction of which to change the values to then decrease the loss. So going back up here, when we do the partial derivative of this weight right here, for example, we'll then have the final loss for the network, and then we would like that to go down. So calculating the partial derivative of this weight right here will tell us which direction to change the value, so whether we should make the value larger or the value smaller. So this would be smaller, this would be larger, obviously, to then decrease the loss. And this will then be done for every single weight and bias within the network. So even though these partial derivatives tells us which directions to change all of these values, they do not tell us how much to change these values. So maybe we find out that this needs to be a larger number, but should we make it 0.5 instead, or should we make it 5 instead? Because this is a pretty big difference in how we change the number. And the only real way we can find out this is by incrementally changing the numbers and then calculating the partial derivatives again. But how much we actually change these numbers is called the learning rate. So because if we change this weight right here and then calculate the partial derivatives again, all these partial derivative values will then change. It is very important that we find a balance in how much we actually change these numbers, such that we don't overshoot or undershoot the actual change we should make to these weights and biases. So going down here, again, we calculate the partial derivatives, so we know which way to change the numbers. Then we have a learning rate predetermined, and that is how big of a change we need to make to the weights and biases every single time we calculate this partial derivative. And this is just a trade-off between overshooting / undershooting the optimal values for the weights and biases, and then also speed. So if we have a very low learning rate, then the speed is going to be really slow because we only make very small changes at a time. But if we have a pretty big learning rate, then we might overshoot the optimal values, and the increments might even be so big that we don't even hit the optimal values for the weights and biases. So a good learning rate is somewhere in the middle, and usually you can trial and error your way back and forth to find out what learning rate is best for you. But you can also often see how other people have used different learning rates to kind of gauge how big it should be to work for the network you're working with. So we found out how wrong the model was. Then we made a change to the model's weights and biases to then figure out if it is wrong again. So now we do run the inference again, just like the first step up here, but then we monitor the loss to see if the loss actually improved after making these changes. So this process right here is just being repeated over and over and over and over again. And then we monitor the loss over time to then see if the network improves. And at one point, the loss won't really go down anymore. And this is what we call that the network has converged. And this is because it doesn't really get any better than it is. And therefore we might as well just stop the training. So when the network has been trained, it should know all the samples from this training dataset very well, and it should be able to predict samples not yet seen before. So even though it has seen all of these samples right here in the training dataset, it hasn't really seen any of the samples from the validation dataset. So even though it doesn't know any of these samples, it should be able to generalize what it has learned from this training dataset to the validation dataset. And that is actually why we have these two different datasets. So going down, let's take a look at some of the common pitfalls when training models. So over here, I've plotted a bunch of different samples, and these are just random values in a space which I've created right here. This line right here in the middle represents the model's ability to predict the trend, or the general trend of all these data samples. So optimally, we would like a model to generate a trend that looks like this. So we know that the samples follow this trend right here, so the curve that the model predicts should also follow that. Then underfitting is when the model totally does not get that, and it just does something that completely doesn't make sense. Overfitting is when it is hyper-focused to all of these points, so it doesn't even really generalize, it just knows every single one of these points because it just remembers them. So first of all, let's just go through underfitting. So we have two graphs over here, and these are the loss functions. So remember how I told that we calculate a loss up here, and then we can monitor that loss over time. Well, in practice, we get these two graphs out. We get a graph out for the training loss and also for the validation loss. So a loss will be calculated both for the training dataset and also for the validation dataset. So over time, we should see the loss going down because the model gets better. But if the loss doesn't really go down that much, it probably means that the model isn't getting very smart, so it is underfitting. So even though the model learns a little bit, as we see right here, it doesn't really go all the way down as we would expect and really learns a lot about the dataset. So that was underfitting. Let's just talk about overfitting quickly as well. So overfitting is when the model is trained so much on this training dataset right here that the loss goes down because it remembers every single point from the training dataset. So it is really good at predicting the correct values for the training dataset, but it doesn't really generalize those results to a dataset it hasn't seen, because it can't really generalize. It's just remembered the values from the training dataset and doesn't really know what to do when it sees values that it hasn't seen before. So even though the loss goes all the way down for the training dataset, which is good, the loss doesn't go down for the validation dataset, which is pretty bad because the model isn't able to generalize. So by comparing these two graphs right here, we can see whether the model is overfitting, underfitting, and then or whether it has a good fit. So ultimately we would like a good fit, and this is a trade-off between underfitting and overfitting, where the model doesn't really remember all of the data points from the training dataset, but it also is good enough to not just underfit. So when we take a look at these two graphs in a good scenario, we should see both the graphs going down simultaneously and then decreasing to as low as a loss as possible. And as you see right here, the loss decreases a lot in the start. This means that the model is getting really good in the start and making big changes, or big improvements, but then as time goes by, the model slowly gets less and less good every time we run all the samples through. And then at some point the model converges, and that is about right here. And the reason the model converges is because it doesn't really know how to learn more from the data that it has seen. So we might as well just stop the training right here, because the loss isn't decreasing. And the loss might even go up, as we see in this example right here, because the model starts to remember some of the data for the training dataset. So when looking at the loss graphs, this scenario right here is what we would like to see, and these two up here we would like to avoid. Luckily, when we see these two cases up here, we can take some measures to actually fix that. So underfitting is often because the model is too simple. So if the model has too few layers, or the model has too few neurons in the layers, it won't really be able to have enough of these weights and biases to learn the complex patterns of the dataset that we are providing the model. Another example is, or another reason for underfitting might just be that the model also isn't trained enough. So up here, even for the good fit, if we only train it for a couple of epochs, so we only run the data through the model a couple of times, then the loss isn't going to be very high. But as you see, if we let it run for a lot of epochs, then eventually it is going to be a good fit and not just underfitted. If we do see that the model up here is underfitting though, even though it has converged, we might want to add in more neurons, because the model might just be too simple for the dataset that is provided. So this also means that the bigger the dataset, the more neurons you would also need for the model to learn these complex patterns of the dataset. So the alternative is overfitting. So overfitting right here might happen if the model is too complex. So this is the other end of the spectrum. If you have too many neurons for the dataset that you're actually working with, because we have that many neurons, one effect of this is actually that the models start to learn the patterns of the dataset, or just remember the samples of the training dataset. So if you see overfitting, you either have too little data compared to too many nodes you have, or you might have trained the model too long. So if it's overfitting, you can either increase the amount of training data you have, or you can make the model simpler, so you can remove a layer, or you can make layers have less neurons, and then you can see if the model stops overfitting and gets a good fit instead. So these were some of the common patterns that we see whenever we train. And one of the jobs of an AI researcher is really to just find this balance between underfitting and overfitting, and then making a model that is a good fit, so it is able to generalize while still keeping the loss as low as possible. Good. So that was the small introduction to neural networks and then AI. And then from here on, we can move over to convolutional neural networks, which is one form of a neural network that is a little bit different than these layers down here, which are just normal linear layers that are fully connected. So let's just hop over here to the convolutional neural networks and then check out how they work. So like we previously saw, whenever we have a dataset, one of the tasks that we might want to do with this dataset is to give it some input and then have the neural network classify what the input actually is. So for this number MNIST dataset, the input was then going to be an image of a hand-drawn number, and the output is going to be what the number actually is. So this dataset over here was pretty simple because it only contains 28 by 28 pixels. So the dataset isn't really very complex to work with. But let's say we have images that are much more complex, for example, such as a dog right here. A lot of pixels is in this image. It might be 1,000 by 1,000 pixels, meaning there is 1,000,000 pixels in this image alone. So whereas we over here in this example right here, as I showed you earlier, we had 28 by 28 pixels. So this means that if we multiply this out, we could get away with only having 784 neurons as input neurons, but if we have the dog image over here with 1000 by 1000 pixels, then we might have 1,000,000 input neurons, and that is actually a lot of neurons in a network. And then, as I explained earlier over here with the overfitting as well, if we have too many neurons for a network, we might start to see overfitting as one of the consequences. So convolutional neural networks over here is just one of the ways of working with a lot of data, such as images, for example, and then doing classification with that. So it is an alternative to linear layers with a pretty cool technique behind it, which we'll go through in just a second. Before we are able to actually work with these or understand these convolutional neural networks, we'll just quickly go through how images are represented in computers. So as I explained earlier with the MNIST dataset, that was 28 by 28 pixels, but this is also just pixels. So an image really just consists of pixels, and if you have a colored image like this, you'll have multiple channels. You'll have a red, a green, and a blue channel. The red value can be between 0 and 255, and the same for the green and also the blue value. So for the MNIST dataset over here, this only had a single channel because it is a grayscale image. So a pixel might be between 0 and 1 in brightness, where maximum brightness is white right here. And then, so that is if the value of the pixel is 1. And then if the value is 0, then it is black. And then if it is 0.5, it is right in between. So that is pretty simple for grayscale images. But if you have colored images like the dog right here, you'll need to keep track of 3 different channels and then the values of each different channel. So zooming into a random point in this image, you'll see a collection or a matrix of pixels, and then each pixel will have a color consisting of the R, G, and B value, and that set of 3 values is going to look something like this. Good. So with that out of the way, we can move on to how convolutional neural networks work. So CNNs or convolutional neural networks use something called a kernel to scan across images and learn features from the image. So instead of looking at every single pixel one by one, it can slide across the entire image with something called a kernel to learn the features in a more broad way. So let's say we have this image right here. This is just an image. So this is just a small subset of a big image. So this right here is an image, for example. So just imagine that this right here is the same as down here, just for a single channel. So this is just 3 channels because you have R, G, and B. This might be for the red channel alone. Good. So we have a subset of an image here. And then each value in this matrix represents each pixel's value. And this then makes up for the input matrix for the convolutional neural network. So that was the input. The next thing we'll cover is the kernel. So the kernel which we'll create is something called an edge detector for vertical edges. And the kernel is basically just a matrix, just like the input matrix up here is, just with some other numbers. And what can then be done is that the kernel can slide over the input matrix, and then convolutional operations can be performed between the numbers in the kernel and then the numbers in the patch which we're currently sliding over up here in the input matrix. So let's just take a look at how that looks. So right here it has to be vertical actually. So when it slides across the first patch right here, this is going to be how it looks. Then it can slide further to the second patch. It can also slide all the way down to this patch right here and also this patch. So there are 4 different positions which the kernel can slide across to in this input matrix which we're working with. And then whenever we are at a specific patch, some mathematics is done between the kernel and then the actual input matrix. So let's just take a look at the first patch and how that looks. So we have the number from the kernel, and then we have the number from the input matrix. And then we can do what is called an element-wise multiplication and summation, and this is also called a convolution operation. And this is then calculated every time we slide across this input image. So for the first one, we have the number 1 here and number 1 here. So we'll say 1 multiplied by 1. We'll then add that to the 2 multiplied by 1. We'll add that to 3 multiplied by minus 1. And we'll do this for all the different numbers for the kernel and then the input matrix. And then when we evaluate that full statement, we'll get a single number out. And we then insert that into a new matrix called the output matrix. So since we could only cover 4 different patches, 1, 2, 3, and 4 for this input matrix right here, the size of the output matrix is only going to be a 2 by 2 rather than a 4 by 4 as we saw with the input matrix. And as I wrote over here, multiplying the kernel values with the values from the original pixels is also called a convolutional operation, and that is basically the reason why this is called a convolutional neural network in the first place. So quickly continuing this example down here, we have the 4 different positions. Then we do the convolutional operation for each of these. We get out 4 different numbers, and then we insert each of these numbers into the output matrix right here. This output matrix is actually also called a feature map because it represents the specific features that were extracted by performing all of these convolutional operations to the input matrix with the kernel. So what does these numbers up here even mean? We have -1, we have 1, and we have 0. This specific set of numbers is called an edge detector for vertical edges. You can also create one for horizontal edges, or you can randomize the numbers to extract some features we don't really know exactly what is. So all different kinds of configurations of kernels can be made to then extract specific features from an image. So how does this look if we actually try and apply this to a real image and not just a subset of an image up here? So the above was a vertical edge transformation or a vertical edge detector. So if we were to do this for a full image, this displaying the output matrix would look something like this below. So we have a full image down here, which have skies, we have a crosswalk, some doors, etc. And then if we apply the vertical edge extraction convolutional kernel, we get this one right here. So we can see that all of the vertical lines in the image are highlighted. So if we instead apply a horizontal edge detector, the vertical lines aren't very highlighted compared to the horizontal lines in the image. So that is basically the difference between different kernels. You should also note that even though that we started with this pretty complex image with a lot of pixels, and then we went all the way over to this image right here, the feature map, which only has the most important features extracted from the image. So instead of a neural network having to learn what skies are, for example, it'll only have to look at the crosswalks, the doors, and the buildings, and then all of this other maybe relevant information is then filtered out from the image by the specific kernel that has been applied. So the entire purpose of convolutional neural networks is to take something like an image and then extract the most important features from that image to get different feature maps out, which we can use to pass into neural networks, to other layers in neural networks, such as linear layers, which we have seen before. Cool. So over here, we can also see it in a more formal way by breaking down the original image into these simple features. So these features, as you see right here, the crosswalk, for example, the doors, these feature maps, the CNN can now start to learn how these simple pieces combine to form more complex objects. So this network which we are training, for example, might be able to learn that a street in the image is made up from the lines from the crosswalk, the doors, and also the building roofs, instead of having to look at the skies, the color of the pavement, the color of the walls, etc. So basically, the image is condensed into its features. So let's take a look at how we can actually use these feature maps up here, which have been extracted from the original images. So broadly speaking, the flow in a neural network looks something like this. We have a raw image. This is just an image of a dog I found online. And this image might be 1000 by 1000 pixels, so 1000 high, and then also 1000 wide. This means that there will be 1 million pixels in this image in total, which is quite a lot of data. So let's say we apply a convolutional neural network to that. Then the first layer might extract something like this. So we go from 1000 by 1000 down to 500 by 500 or something like that. So basically we reduce the dimensions while we extract the features of the image. So right now the image is more simplistic and we only see the features of the dog. Then we can further pass the feature map of this convolutional neural network through another convolutional neural network. This will downsize the image even further and extract the most important features, what the network has deemed the most important features from the previous feature map. We then do this again. We end up with a feature map with even fewer pixels, and then it contains an even more abstract view of the features of the original images over here. So it might do something like finding simple features in the first layer, then it'll find combination of simple features in the second layer, and then it'll find even more higher order features in the third layer over here. So basically we can take convolutional layers and then we can stack them. So we pass the feature maps from one to another. And then the more convolutional layers we pass these images through and the feature maps through, the more higher order the features that we see in these actual images become. So now we have a pretty small image. It is only 25 by 25. These scales are just for reference. They don't really mean anything. It's just made up. I just wanted to show you that we go from a large image to 1000 by 1000, and then a side effect of using these convolutional layers is that we downsize the images And then we end up with a rather small image right here, which is small enough that we can pretty safely pass it through a neural network. So what we do is that we take every single pixel from this neural network. So we take the first pixel right here, you can even see it. Then we take the second one, the third one, etc. And then we flatten them. This means that we take this entire image and then we make it into a single list. So we take all the pixels from the first row, and then we append all the pixels from the second row. So instead of an image, which is a 2x2, it's a matrix with width and height, then it's going to be a single vector. So basically a single row of pixel values like this. And then for our example, we have a 25x25 right here. This means we'll have 625 numbers. So we'll need 625 input features or input neurons for our network. And then we can have 2 output neurons right here because we want to classify whether it's either a dog or a cat. And then we'll get a probability out for the dog and a probability out for the cat. So now, as you see, instead of the network having to learn all the different features of this pixel right there, the pixel right down here, the pixel right there, so a million different pixels, the network only has to learn the features of 25x25 different pixels, so 600 numbers. So it is way simpler for the network to actually understand what goes on in this image rather than having to look at all of these different pixels at the same time. So extracting features, then extracting the features again, etc. just allows us to create data that more feasibly can be put into a linear layer and then used to classify what the image actually is. Or we can classify something completely else than images, such as audio, for example. Cool, so now we know how it works with convolutional neural network layers, but let's talk about how it would look if we didn't use these CNN layers, but instead just used linear layers like we have over here. So opposed to the existing architecture we just went through up here, this architecture just uses a single linear layer and it doesn't really have these convolutional layers. So to start off, we still have the same input image, which is 1000 by 1000 pixels. So whenever we do flatten this into something we can pass through a linear layer, an array will again be created with all the different pixels. So the first pixel up here will be the first item in the array, second one the second item in the array for every single pixel in the image. So we'll basically end up with an array of 1 million different pixels because we have 1000 by 1000. And because we then therefore do not have these CNN layers to extract the most important features and then also to reduce the dimensions, we'll end up having to pass these 1 million different values into the CNN as inputs. So if we have 1 million different values, we'll need 1 million different input neurons. So therefore the input layer, which will be a linear layer with 1 million different input features, and then for example 2 output features if we're trying to classify whether the image is a dog or a cat, for example. So going up here instead, if we only have these 600 different numbers because we reduced down the image to its most important features, we'll then only need to have 600 numbers, but down here we'll need 1 million numbers in this input layer. So without CNNs, the raw image is uncompressed and it requires 1 million different input features for the linear layer. With CNNs, it's only 625 input layers. So what difference does this even make? Well, based on values from 1 million neurons, the network will have to figure out the combinations that equal the image being a dog. So that's a pretty huge task, right? Let's say I gave you, the viewer, 1 million different numbers, and then you have to figure out what these numbers mean. Well, this task is pretty much impossible, right? Because how are you going to do anything with those 1 million numbers? Well, if I instead gave you only 625 numbers, it still might look impossible, but it is way more manageable than giving you 1 million numbers. Because at least you can kind of find something to look at, such as specific patterns with these 625 values compared to 1 million values. So even though it is still a lot of values, it is way more manageable having to work with less data. So what does this mean in practice? Well, it means that if we do train the model with 1 million input neurons, it is probably going to be pretty slow, because during backpropagation, all 1 million weights and biases will have to be tuned, because up here we only have 600 right here, where 600 neurons with their own weights and biases. Down here we have 1 million, so it's quite a big difference. And all of these weights and biases will need to be tuned every single time we do backpropagation, so it's going to be pretty slow whenever we train the network. Second of all, we might see the problem we talked about earlier with overfitting. So simply, the network is just too complex because we have 1 million neurons, so too many parameters, compared to how little data we might train the network on. So one side effect of this, which we talked about earlier as well, is that the network will maybe just memorize the actual training data instead of learning what the image actually is, so that it is a dog, for example. And when we see this overfitting, it'll just remember what this image is, and we won't really be able to use it in a generalized way on new images that the network has not seen before. So those are some of the risks and problems we run into if we simply use a simple linear layer as input layer instead of passing it through something like convolutional neural networks, or layers, that will then reduce the image down to its most important features. So going down, why do we not just compress the image through a series of linear layers instead of just using convolutional neural networks? So let's say we have a raw image like this again, and then we flatten the image down to a large array of pixels. Then we run it through an input layer, and then we compress that input layer down to another hidden layer with way fewer neurons, and then we compress that down to the classification heads right here. Well, the first problem with that is that we still have this 1 million neuron input layer right here. So parameter-wise, it is pretty much computationally enormous, just because we have so many different weights and biases still, just like we did in the earlier example up here. So for a linear layer, every single neuron has its own weights and biases that will need to be tuned, but for a convolutional neural network up here, the weights and biases that are tuned is actually the ones inside the kernel right here. So let me just find this. So these are all weights and these are all the weights in the convolutional layer that will be tuned, and not the actual weights and biases of the neurons as you see in a linear layer. So this actually means that these weights and biases can be reused for the entire image instead of having to train weights and biases for every single pixel of the image. Another super cool property of this is also a problem fixed that is called translation invariance, and I'll just quickly walk you through what that is now. So the problem with linear layers like these ones is that the network will have to learn or recognize a feature such as a dog's eye, for example, in every single possible location separately. So learning what a dog's eye looks like in the top left corner, for example, will not help it recognize the exact same eye if it appears in the bottom right corner. It would need a different set of weights to detect the eye down here than it would to detect it up here. And that is because every single pixel is passed into its own neuron, so the network can't really reuse what it has learned up here, for example, down here in the network. They are simply just two different places in the network because they are fed in as separate pixels one by one, different places in the input layer right here. So how are convolutional neural networks different than this? Well, because this kernel up here, let me just walk through this. This kernel up here is able to slide across the image, and these numbers right here can then be tuned by the neural network. So the neural network will figure out how to change these values to extract features that will make the network perform the best as possible. So this also means that if this kernel right here learns to detect the eye of a specific dog, this kernel right here can also be reused multiple places within the image to detect the same dog eye, regardless of whether it is in the top right corner or in the top left corner, for example. So this ability to recognize a pattern regardless of its position is called translation invariance, and it is a pretty natural property of convolutions. So going down here, again, whenever a network has a kernel that has learned to, for example, recognize a tongue of a dog, then a tongue could appear over here as well, and it will still be able to recognize that it is a tongue, regardless of whether it's over here, whether it's over here, etc. So that is one of the pretty big benefits of convolutional neural networks. You'll simply just need less data because you won't really have to train it on images with the dog's tongue being both here, etc. For every single position within the image. Another idea that can help us understand this exact concept is that an image really isn't just a random bag of pixels, and right now it is being treated as that because we just take every single pixel and then we extract them out into a single list. So we really treat every single pixel as its own thing, and these pixels aren't really related to anything. But in reality, what makes an image is really what pixels are next to each other. So we only really know that this is a tongue because we have all of these red pixels close to each other. So it is really the relationship between these different pixels that allows us to see what is within the image. And this concept right here is called spatial information. So whenever we just take a full image like this and just flatten it out into a single list, we do what we call destroy the spatial information of the image. So we just destroy the relationship between the different pixels, so we don't really know a lot about how they relate anymore, and then we also lose a lot of meaning behind what is in the image basically. So for example, if we take the first row of pixels up here, well then pixel number 1000 in the first row right here is then right next to the pixel from the second row right here, so the first pixel of the second row. So they are equally close to each other in this flattened array than the two pixels, pixel 1 and 2 in the first row right here. So we don't really know as accurately which pixels are close to each other and which aren't, and that is one of the problems with just flattening an image like this. So why should we just use CNNs instead? Well, these convolutional layers, such as the kernel up here, will specifically look at different patches, so it'll take multiple different pixels into account at the same time to capture the relationship between the pixels within the kernel, instead of just looking at pixels one by one. So the convolutional layers really use these patches or this spatial information to extract some specific features from the image to then create the output matrix, instead of only looking at the image one by one and then feeding them one by one into a linear layer like this. So to summarize it down here, a linear layer destroys spatial structure of the image, but a convolutional layer is designed specifically to preserve it, because we look at multiple different pixels at the same time whenever we slide a kernel over an input image. And then when flattening, all the pixels are put into a list. Their relationship isn't really stored in the network, so that is that a pixel A was next to pixel B, as I just explained. Therefore, no local features are really preserved, only the brightnesses of the pixels basically. And then with CNNs, because the kernels scan across patches of an image and sums them up, small local features can be learned, which is what we saw earlier when we extracted the features by sliding kernels over the input matrix. Okay, so far we have looked at convolutional layers in a little bit of a simplified way, and now I'll just hop down and go through how it actually works more accurately in real life. So first of all, when we have a CNN layer, we can talk about something called the depth. So for a convolutional layer, we define the in and also the out channels. So the in channels is the depth it receives. So for grayscale images, so for ones down here, there's actually only a brightness factor, so how bright a pixel should be. There isn't colors such as R, G, and B. Therefore, a grayscale image would have one in channel, whereas an RGB image, so one with colors, would have 3 different in channels. And then also in these above examples, only one feature map was generated per convolutional layer, while when we actually do use these in practice, a convolutional layer in a neural network doesn't really use just one kernel. It uses a lot of these kernels simultaneously, and we can define how many kernels we would want it to use. And we define this by setting the out channels. So the out channels set the depth it outputs. So setting this to 64, for example, would tell it to create 64 different kernels and then output 64 different feature maps. And then what the network will do is that it'll create 64 of these kernels up here with randomly set values or randomly initialized values, and then it'll try to tune these different values in these kernels to extract specific features for the image, which will then minimize the loss as much as possible. So in theory or in practice, we don't really know what these values actually are. We don't set them manually. This is done automatically by the framework, and the tuning of each of these values is then also done automatically by the framework. So that is one idea you should definitely understand about CNNs. So when working with CNNs, when you actually build a neural network in practice, a single layer will need to be pretty powerful. So what I mean by this is that it should be able to simultaneously look at horizontal edges, vertical edges, specific color gradients, simple curves, etc. and also combinations of these by extracting the most important features and then passing these on in the network. And the only way it can really do this is by using a lot of different kernels at the same time. So that is what we define with the out channels. And then every single kernel will be responsible for finding a specific type of feature within this image. So basically, if we set this out channel to 64, then hopping all the way up here, we'll get 64 of these different output images, or feature maps, out of the convolutional layer. And these will then be passed on to the next convolutional layer, also the linear layers further down in the network. This also means that if we have 2 convolutional layers right after each other, like this, then the out channels for this one right here also needs to match the in channels for this next convolutional layer. So if we have 64 different feature maps coming out here, then these 64 will need to be passed in as feature maps for the next convolutional layer. So the out channel right here needs to match the in channel for the next convolutional layer. Otherwise, it won't really work out very well for you. Alright, so how does this actually look? Well, first of all, if we have the input image and then we have 64 output channels, it'll create 64 kernels and then also 64 different feature maps. So we'll have a full stack of feature maps like this. And then just like we flattened out all the different pixels up here in this linear example, we can then flatten every single feature map and then append them to each other. So we'll ultimately end up with something like this, where we have a full list of all of the different pixels from all of the different feature maps in one long vector. And we can then put that into a linear layer, which we can use to then classify the image, for example. But first, you need to think about what these 64 feature maps actually represent, because they aren't just pixels anymore. They're really more of concept maps or heat maps of specific features. So the first one right here might be a feature map for a specific feature, such as fur texture for the dog, where the high values means, oh, there is fur displaced in the image. The second one in the behind right here might be a feature map for the tongue right here, for example, that says, okay, the places with the highest values or the brightest in this feature map is going to be where the tongue is. This third one right here might be something for the eyes, that detects eyes in the dog and lights up wherever there are eyes within the image. So whenever we flatten all of these feature maps over here, we aren't just scattering all these individual pixels from the image out, we're really creating a long list that summarizes all these 64 different learned features across the image. So what this also means is that if we take this like that, and then put this linear layer down here, if we take all of these flattened feature maps and run them into a series of linear layers, then these linear layers don't really care about the exact x and y coordinates of the eye, for example, anymore. They just need to know that the eye feature or the fur feature or nose feature or whatever is just detected in these feature maps at all. So instead of these layers having to learn the relations between specific pixels, they'll need to learn the correlations between abstract concepts, basically, such that there is an eye right here or there is a nose down here. So ultimately, if we pass in an image of a dog right here, what this linear layer will think is something like, okay, the tongue feature map is active, the fur feature map is active, the eye feature map is active. So it is pretty probable that this image right here is a dog. But if we put in a human image, for example, then the fur feature map is definitely not going to be active. The tongue feature map is probably not going to be active, since people don't really stick out their tongue like this very often. So these active feature maps won't really light up for anything other than dogs, ideally. So that is also the reason that whenever we flat the feature maps like we do right here, it doesn't really scatter out all the different information like what happened over here whenever we just flattened out every single pixel from the image. Because right now it isn't really just pixels we scatter out, it is really more abstract features that we scatter out. So basically, in the convolutional layers, the network will find features and their locations. So it's kind of like asking, where is the eye? And the eye will then light up in a specific feature map over here. So after flattening, the feature maps become abstract signals, like there is a pointy ear right here, or there is a furry texture right here detected in another feature map. So now the network shifts to become reasoning about those features and not specifically finding out where they specifically are, because the kernels will scan over the entire image anyways. So the exact location matters less than knowing that the feature is actually there. So whereas the exact location mattered a lot whenever we just passed all the different pixels raw into a neural network like this, now because the kernel scans across the full image, what is being ran into this linear layer right here is just whether the presence is there of a specific feature or not necessarily where it is. So that is really the power of convolutional neural networks. Cool, so let's talk a little bit more about what happens when you train a convolutional neural network like this. So let's say you create 64 different output channels, so this will create 64 different kernels. Well, then you'll get 64 kernels, these are just the first 3, with randomly initialized values. So whenever you pick a number of kernels, each kernel is initialized to a set of random values. That is what I've tried to visualize right here. So these are just all random values for different kernels. And it is important that all of these different kernels are initialized to random values, because it'll ensure that these 64 different kernels will start out slightly different, extracting slightly different features from the image. And this also means that there is a possibility of all of these different kernels learning 64 unique different features, which is better than if all of these were initialized to the same values and they just extracted the same features, because that wouldn't really be very useful. Then we might as well just have a single kernel. So whenever you take these newly initialized kernels and then create feature maps or do a forward pass basically on an image, then you'll get kind of random feature maps out. So when the neural network has not been trained, then the feature maps that will be extracted by these kernels won't really be very useful probably for making correct classifications or predictions with the model. So the loss function is going to stay relatively high before you train the model. But during backpropagation, these different numbers are then tuned for all of the different kernels and the loss will slowly decrease. So as I explained before with the fur detector or the eye detector or the tongue detector, these different kernels might learn to extract useful features that we don't really know or care that much about. We just care about the output of the model. But these features will in some way, shape or form extract something useful from the image. So this one might extract some information about whether there's fur or not. This one might extract something about whether there's eyes in the photo or not. So they'll each just extract abstract information about what makes a dog a dog. And then over time, whenever we run through all the different epochs, each kernel will then probably produce a useful signal that will make the neural network predict something that is useful to us. So basically, during training, the network predicts. If the prediction is then wrong, an error is sent backward, that is called backpropagation, to adjust each kernel slightly to better detect helpful features in the future. So basically, we just set the kernel size and then also the input and output channels, so how many of these kernels we even want. And then the specific tuning of each kernel will then happen automatically by the different frameworks that you can use. When we work with neural networks and convolutional neural networks, we can talk about the width and also the depth. So we can define our network and then we can define how many of these convolutional layers we put after each other. So in this example, we have 3 different convolutional layers passing into each other. But we can also define how many out and in channels is there for each of the convolutional layers. So we can define how many we put after each other, but also how many feature maps each of these should produce. So when we talk about width of a convolutional neural network, we talk about how many out channels or kernels is in a single layer. So for this one, for example, we have a width of 32 because we generate 32 feature maps for this specific convolutional layer. And for this one, we have a width of 64. So what the width really means is that it controls the variety of features, because the more of these feature maps we generate, the more randomly generated kernels will also be created and the more feature maps will be created. So there's a higher chance of us being able to extract even more different features if we have even more different kernels. So if we have a lot of different output channels, we'll have a lot of different kernels, and each kernel will become specialized in finding different features such as lines, circles, furs, tongues, eyes, etc. So if we have a layer with 64 kernels, we'll be able to find 64 different types of simple edges and colors, at least if we have a layer of low abstraction, which means one of the first layers right here. So that was the width of a network. The next concept we can talk about is the depth of the network, and that is how many of these convolutional layers we put after each other. So these stacked convolutional layers right here is really more of a hierarchy of abstraction. So each layer will combine features from the previous layer to create something even more complex. So this one will have a pretty low abstraction, this will have a little bit more of abstraction, this will have the highest abstraction. So if we take a look at how this actually might look, the lowest abstraction right here will then extract a feature map from the input image. So as you see, it looks pretty much like the feature image with the granularity at least. The second one, which this will be passed through, will then create an image like this, which will have a little bit higher of an abstraction. We won't really be able to see that easily that it is a dog, but the network might be able to recognize it. And the last layer of abstraction, the last convolutional layer down here, might produce something like this, which we won't really be able to decode as humans, but the network will be. So each layer which we add will then create lower granularity for that layer, meaning we'll have less and less details per convolutional layer because it'll be more abstract and more high level per these layers. So for example, for the first convolutional layer right here, it is a pretty low abstraction and it might find simple things such as edges in the image. The second convolutional layer right here might find a combination of edges because these feature maps generated will highlight the edges, and this convolutional layer will then find the combination of edges because only the edges is able to be seen from the output of this convolutional layer. And now that this shows the combination of edges, this convolutional layer will then be able to look at the combination of edges and then find out which are a face, which are a body, etc. So it'll just take the information from the last convolutional layer and then try to extract some feature or information from that. So if we talk about width, each different layer will need to produce enough feature maps, so we'll need to have a big enough depth, or out channel, that the next layer in the sequence will have data to work with. So if this only produced 2 different feature maps, then we wouldn't really be able to have much to work with, we wouldn't really be able to find many different combinations of edges. So therefore we're going to need to set an appropriate amount of out channels for each of the different convolutional layers. And when we talk about the network depth, we'll also need enough amount of convolutional layers to appropriately build a high-level understanding of the features in the image. So this will be pretty low level because we are looking basically at the raw pixels and then extracting meaning from that. This will be a little bit more abstract because we'll take a look at the already abstract features from the raw image. This will be the high levels of abstraction because we take a look at, or we extract the features from the already high level abstracted features. So modern convolutional neural networks are probably both wide and deep, giving us a good understanding of giving it a good understanding of being able to extract high-level features from the image such that it can make good predictions in the output. Good. So far we have looked at this part of the convolutional neural networks only, so that is just the convolutional neural network in itself, but often you'll see a sequence of a convolutional layer followed by an activation function followed by a pooling layer. So this means that these two right here would be in between each of the convolutional layers, both right here and also right here. And also after this last one. So let's just talk about what these are, such that you're prepared for them whenever you see them and can go ahead and work with these as well. So first of all, we can talk about the activation functions. So just like we talked about ReLU earlier, ReLU is often also used with these convolutional layers. So the feature maps themselves are often passed through activation functions such as ReLU. And as we talked about earlier, ReLU only allows positive values to pass through. So if we have if we have a feature map with a negative value such as -5 in one of the pixels, that -5 will then just be normalized to 0. And again, it might seem kind of weird that we would normalize or just reset numbers to 0 just randomly. And the reason again is that this adds nonlinearity into the network. So without nonlinearity, the network is only able to learn linear mappings, because if we have multiple of these convolutional layers after each other and all of them are just linear, the network is limited to learning linear patterns. But when we add nonlinearity, so things that aren't linear like this, but where the linearity is broken, the network is able to combine many different simple pieces into very complex functions. So basically a series of linear operations just results in more complex linear operations basically. So you can't really model complex real world data with just straight lines like this. You'll need some way to break the linearity to allow the network to learn more complex things. So by putting these activation functions after each of the convolutional layers, the network is forced to learn complex stuff instead of simple linear stuff basically. So that is why the activation function is added. Let's talk about the pooling as the next thing now. So the purpose of a pooling layer, like you see up here, is to downsample or shrink the feature maps so they don't have that big dimensions. So the purpose of convolutional layers is just to extract features. So convolutional layers can create multiple feature maps, but this can be a lot of data. So the vectors becomes huge basically. And we have to introduce a lot more features / neurons into the subsequent layers. So if we have feature maps like this, let me just scroll up, I think we have an example, yeah. If we have feature maps like this, but all of these feature maps are maybe 500 times 500, well that is a lot of pixels, especially if we have 64 of those and we need to flatten all of these into a single long vector and then put this into a linear layer. Because let's say we have 500 by 500 and then we have 64 of those, then we can multiply that together and it'll really be a lot of input neurons for the linear layers coming after the CNN layers. The convolutional layers. So therefore we're interested in reducing the width and also the height of each of these feature maps. And we can use max pool layers or average pool layers to do this. So that is what we're going to do. Also, the more neurons we have, with the same amount of data, the more prone the network is to be overfitting. So that is what we talked about earlier as well. If we have way too many neurons compared to how much data we have, the network will just start to remember the actual input data and not be able to generalize the input data to new unseen data. So we would like to reduce the amount of neurons which we'll need in the network for the network to work. So whereas the purpose of the convolutional layers is only to extract features, and then the reduction of the dimensions is only a side effect, the pooling layer's main job is to shrink the feature maps and not necessarily to extract the features up here. So when we shrink the feature maps, the network will become faster and more robust because we'll summarize the most important information in these feature maps and thereby reduce the dimensions of the feature maps as well. So we can do this in multiple different ways. One of the ways is by using max pooling. So with max pooling, we define a window size. So it's kind of the same concept as with a sliding kernel, just where we do it a little bit differently. We have a kernel which we can slide across the input across the feature map, and then we can use that to reduce the feature map down by 75%, for example. So when we have max pooling, we then keep the single largest value in the kernel and then we discard the rest. So for example, if we have a 3x3 window as below, or it is not 3x3, it is actually 2x2. If we have a 2x2 right here, so that is a kernel with 2 width and 2 height, then we'll be able to take this window right here and then slide it across the input matrix. And the input matrix in this case is going to be the feature map, so an output of a previous convolutional layer. So we can take this window and slide it across. So we have one patch here, another patch right here, a third patch right here, and a fourth patch right here. This will then give us an output matrix that is the size 2x2 because we have 4 different patches to cover. And then because we have a max pool, we take the maximum number from each of these windows. So right here for the first patch, we have 1, 2, 4, and 5. So we take 5. That we put into the first matrix item right here. Then for the second patch, we have 3, 0, 6, and 1. So we take 6 because that is the biggest out of these 4. Then we put it into the second column. So what we basically do is that we take a 4x4 and then we reduce it all the way down to a 2x2. So basically it compresses the feature map by 75% while keeping the strongest, which we assume is the most important features. So that was the max pooling option. Another option we can use is the average pooling. So instead of taking just the max value, which only represents one of the different pixels, we can do a more sensible approach where we take the average. So we take 1 plus 2 plus 4 plus 5. And then we divide these by 4, so we basically take the average of these 4 pixels. This will give us 3, which we'll put into the first column and row right here. We'll just do the same for the other patches, and then we'll get an output matrix of the same size, just with all the different pixels taken into account, instead of only the largest pixel taken into account. So how does this look in real life? Well, a neural network might look something like this. We have a sequence of convolutional layers, and then I just need to put in feature maps right here, feature maps. So the number of feature maps increase after each convolutional layer, but the size of the feature maps decreases. So as you see, we have the first convolutional layer, we have a ReLU and then a max pool. So this means we get maybe 2 feature maps out like this. This is a simplified example. Then we have our next series of these, and then we get twice as many feature maps, but the feature maps are only 75% of the size that they originally were. Then we do the exact same thing, use the same block. Then we get twice as many feature maps again. The feature maps are half the size again. So even though we get more feature maps, the feature maps are reduced in their size by using these max pool layers right here. So this basically just ensures that we don't get too many pixels to flatten, and then also requires to use too many of these input neurons, making the network just huge and prone to overfitting. So that is basically why we use these max pools or adaptive average pools basically. Another thing you might see apart from ReLU and also pools are something called batch normalization layers. So these batch normalization layers are just a technique you use when training to improve the training speed and also the stability of the training. So in neural networks, when these layers are stacked, it's basically just a chain of different layers, and then each layer will learn based on the output which it receives from the layer before that. So this layer right here, for example, will be dependent on the outputs of these layers. This layer right here will be dependent on the outputs of these layers right here. And then some instability might happen when we train, because during training, all of these different layers are updating their weights at the same time. So whenever layer 1 right here updates and gets a little bit better, the distribution of its output values will change. So the problem is then that if layer 2 right here, which is dependent on layer 1, had just started to get used to the old output of layer 1, then it now has to adapt to a whole new output from layer 1 right here. So because this changes all the time, it's then this layer right here will then have to adapt to what we call a moving target. And this concept will then make training slow and then also unstable. So the solution for this lies in these batch normalization layers, which I'll go through in just a second. So instead of these layers being directly dependent on each other, batch normalization layers will take the output from one layer, reset it to a predictable range, and then pass it on to the subsequent layers. So basically, the batch normalization layer down here will decouple these two layers, and then make sure that the data or the output from layer 1 will always be stable, making sure that layer 2 can keep training without having to adapt to this moving target from layer 1 all the time. So basically, if layer 2 is used to a specific output from layer 1, here is what might happen. So during backpropagation, layer 1, for example, is updated, so layer 1 becomes even better, but then its output is not the same anymore, so layer 2 performs worse because it was used to the old output from layer 1. So even though layer 1 got better, layer 2 now performs worse. So maybe the entire network then now performs even worse, even though convolutional layer 1 actually became better. So until layer 2 can get used to this new better output from layer 1, the network will have to be trained for longer because we are adapting to this moving target all the time, such that layer 2 can get used to the new output and utilize it correctly. So that exact problem is what we're trying to avoid with this decoupling of these two convolutional layers. So with this batch norm in between the layers, layer 1 and layer 2 are now decoupled. So batch normalization is a layer that in itself, through backpropagation, learns what a good stable output from layer 1 should be. So layer 1 can be adjusted up and down without layer 2 seeing it from the outputs of layer 1. Training then now becomes much faster since layer 2 won't have to shoot for this moving target all the time, like we talked about up here. So the standard sequence that you might see right here is that we put batch normalization right after the convolutional layer in the sequence. So you have the convolutional layer that finds the features, the batch normalization layer to stabilize the feature outputs during training, the activation layer which adds nonlinearity, and then the pooling layer to downsample and then keep the resolution low so our data doesn't get super bloated. Lastly, I just want to walk you through what it actually means to train a convolutional neural network. So when we say that we train this convolutional neural network, we basically train all the learnable parts of the network. So since a network often has both convolutional layers, linear layers, both of these layers will be trained, and then the batch normalization layer will also be trained because it has to figure out a stable range for the convolutional layer before that. So we can just go up quickly and then we can find one of our examples from earlier. So for this one example, this is a convolutional layer. So if we have a convolutional layer right here, the kernels inside that convolutional layer will then have to be trained. But then for the classification of the outputs of the feature maps, these neurons will also have to be trained as part of the linear layer. So all the trainable parts from a neural network will then be trained whenever the network is trained. So that is what I mean when we say that we train a convolutional neural network. So for convolutional layers, the two things that are trained are first of all the kernels. So the numbers inside the kernels, remember if we have a 3x3 kernels, we'll have 9 numbers we'll be able to train to extract specific features for each kernel. So the numbers inside the kernels can be trained and the network will learn the best numbers for the best configuration values for the kernels through backpropagation. So for example, if there are 64 kernels, it'll learn 64 different sets of kernel configs, meaning these kernels will go from random to useful. Secondly, in the convolutional layers, biases will also be trained, so each kernel will have a bias value that is added to every single number in the feature map that it produces. So the bias adjusts the feature map's importance up or down. So for example, for 64 kernels, the network will learn 64 bias values as well. And this is only for the convolutional neural network. For the linear layers, the weights and biases will be trained, and the weights and biases are simply just the ones we talked about earlier. So the weights right here, and then also the biases, because this is a linear layer. So that is what we train whenever we train a convolutional neural network. So whenever we went through the kernel, for example, you might have wondered why the kernel size was specifically 3, for example. And that is just a hyperparameter that I specifically chose, just so I could walk you through how the kernel works. But you can actually tune these different values of, for example, how big the kernel should be, and all kinds of other things when you do initialize this convolutional layer in an actual neural network. So we can go over here and then we can check out the actual hyperparameters which we can set for each convolutional neural network layer, such that our different convolutional layers in the network extract different things basically. So the things we can set is, for example, the kernel size. We can set something called the stride. That is how fast or how many pixels each of these patches jump every time a new patch is taken when the kernel slides over the input matrix. And we can also set something called padding, which will allow us to capture the edges of the input matrix more accurately. So first of all, just to refresh the kernel, we have a kernel right here, and then that kernel can jump over different patches. So there is the patch right here, the patch right here, and also a patch right here, for example. And then as we talked about earlier, each one of these patches will produce a pixel of its own in the output matrix over here. So the first patch is going to produce this output pixel, the next patch will produce this output pixel, and the patch in the middle of the entire input matrix would produce this output pixel, for example. So that is how the kernel position moves or changes whenever the kernel slides across the input image. So now that we know this, we can go ahead and talk about the first hyperparameter which we can tweak, which is the kernel size. So different kernel sizes can be used for different purposes. So first of all, you can have a super small kernel size like this, which can slide across the input matrix, but you can also have a pretty large input size like this, kernel size like this, which will create a smaller output matrix. So these will have different purposes. So different kernel sizes are specialized for different tasks. So if you have a super large kernel like this one right here, they will be better for broad, simple patterns, so it'll help the network get a quick general understanding of the input before diving into the details. But they're also more computationally expensive because there'll be more parameters. So remember how I said that each of these parameters will be trained by the network? Well, if it's a pretty small kernel, there'll be fewer of these parameters to train, so it'll be faster in general. But if you have a pretty big one, you'll need to change or train more of these parameters in the kernel, so it'll be slower. So that is what I mean when I say that it is more computationally expensive. If you instead use a small kernel, the kernel will be better at capturing fine-grained local details, and actually using several small filters instead of one big one will help the network learn better because it'll add more of these activation steps, so nonlinearity into the network. And because there are more nonlinearity in between the different convolutional layers, this will make it easier for the network to learn complex patterns from the same image area, and it'll probably use fewer parameters too, making it less computationally expensive. So as you can probably imagine, if you are able to look at 9 pixels at a time, you'll be able to extract more information about the broad pattern of the image. Whereas if you look at a single pixel at a time, a kernel size of 1 doesn't really capture that much of the spatial features because it only looks at a single pixel at a time. So to spot features, multiple pixels will need to be analyzed together, and then this will be able to reduce the information to fewer dimensions. And that is exactly what these larger kernels over here do. Good. So going down, kernel size is the first hyperparameter which we can change. And you often use a combination of different kernel sizes. So maybe for the first convolutional layer, you would have a larger kernel size. And then after that, you would have maybe 4 different convolutional layers, which would have smaller kernel sizes. So that was the first hyperparameter. The second one is called the stride. So you might have also wondered why sometimes the kernel would move 1 pixel at a time, whereas other times it would move 2 pixels at a time. And there actually is a hyperparameter for this, and that is called the stride. So the stride is how many pixels the kernel skips over whenever it slides over the input in a CNN. So it affects how much you learn from the input matrix and also how fast the CNN runs. So the stride is really a balancing act between the detail you capture. So if you have a low stride, you cover more pixels, so you have a higher level of detail, and computational efficiency. So let's imagine that we have a pretty high stride, so we go from here and then we go all the way over to here. Well, then we skip these 2 pixels in the middle, so we save the computation of these 4 pixels right here, but we also lose those additional details. So that is basically the trade-off we make with changing the stride. So a small stride, like a stride of 1, moves 1 pixel, grabs more detail, and also makes a bigger output, but it takes more work. A large stride will jump more, lose more details, shrink the output, and also work faster. So if you have a kernel size of 2 and then a stride of 2, we can take a look at how it moves or how the kernel slides across the input matrix. So it'll take the first 2 columns right here. That'll form this pixel. It'll then take the next 2 columns, which will form this pixel, take the last 2 columns, form this pixel, etc. But it won't jump into uneven territory. So you notice how it said 1, 2, 1, 2, 1, 2, and that's because we have the stride 2 and kernel size of 2. So it won't jump into uneven territory where it says 2, 1, for example. It'll continue this pattern of 1, 2, 1, 2, 1, 2, etc. So this will not happen because where we're supposed to put this pixel, it doesn't really fit into the output matrix right here, as you can probably see. So that was one example of stride. Let me just take another one. Here we have a kernel size of 2 and then a stride of 4. So now we have 1, 2, 3, 4, and then we have 1, 2, and then it says 3, 4 into the horizon. So the first 2 right here will be put into the first pixel. The next 2, because we skipped 2, we have a stride of 4, will be put into the second pixel. So that is how it works with stride 2. Well, let's now say that we have kernel size 2 and then stride 3. Well, this won't really work, and we won't really be able to set this in a neural network because, as you see, we are into this uneven territory again. So right now we have 1, 2, 3, and then 1, 2, 3. So if we cover this one, for example, and then we jump all the way over to stride 3, so we start from 1, 2 again, right here, well, then we'll have 1 leftover pixel. So that really won't work because this leftover pixel, we won't really know what to do with it. So irregular spacing like this means that the kernel doesn't really process the entire input, and then because it can't do it systematically, it won't really know what to do. So some values of strides and some combination of values for kernels and strides won't work in the system. So I just wanted to tell you why that is, just so you know why it is whenever you might encounter an error or something with this. So how can we determine allowed strides? Well, first of all, we need to ensure that the kernel can slide across the input without leaving uneven gaps, like we saw right here. So the output size must be a whole number, so we can actually figure this out just by calculating the input size minus the kernel size plus 2 times the padding. Then you divide this by stride plus 1, and then the result should be an integer. So this is just one way to figure it out. A lot of times you'll probably just use a configuration of convolutional layer that you found somewhere else on the internet. But if you want to build one yourself, you can, or configure one yourself, you can just use this formula to quickly figure out if the stride is allowed or not. So that was the second hyperparameter that we took a look at. The next one is called padding. So right now in the convolutional layers that we are looked at, without padding, the output will just shrink with each layer. So what happens here is that we potentially lose edge information, but we can then use a padding hyperparameter to help maintain the edge information or even adjust the size of the output matrix over here. So let's say we have an input size of 3 by 3, we have a kernel size of 3, so the same size, then that would just create a single pixel as the output right here. So we have a pretty heavy dimension reduction. Let's say we include some padding instead. That is what we have right here. So the input is the 9 pixels right here in the middle, and the padding are the gray pixels out here that I put around the input. Well, let's now try and simulate the same thing again. So instead, if we say that this is the kernel, I can just color this as a red background. We'll be able to take this and then slide across. So this is the first patch, and because we have a stride of 1, this will be the second patch, and this will be the third patch, and then we have a fourth, fifth, and sixth patch, and then we can continue doing that. This will leave us with a 3 by 3 output instead of a 1 by 1 output. So this way the padding can be used to determine or to help control the actual output size matrix which we get out. So what are these padding values then? Well, these padding values are typically filled with zeros, and we put them in to help preserve the edge pixels. And why do we preserve edge pixels? Well, I can show you an example. So first of all, if we have this example with a 4 by 4 input matrix, kernel size of 3 and a stride of 1, meaning we hop 1 pixel every time. Let's take a look at how this is with padding 0. So right now, in the first patch which we cover, the top left corner is only covered in one position. And with one position, I mean where the kernel currently is. So this is one position for the kernel, this is another position, this is another position, and this is another position. So this first position right here is the only position which will actually cover the first pixel. So as you see in the second position, the kernel does not cover the first pixel right here. So only a single position will help us create a convolution across the first pixel, and that is the one right here. So right here it is covered, now it is not covered, now it is still not covered, and now it is not covered. So we have relatively few convolutions, a single one, to help extract information from this pixel. But if we take a look at this pixel, for example, this pixel is covered both in this position, right here it is also covered, down here it is also covered, and over here it is also covered. So that pixel is covered in way more positions, so the information about that pixel will be included more in the output over here than the edge pixels. So we'll lose a higher degree of information about the edge pixels than the middle pixels. And padding can help us preserve that information because we can cover the same pixels multiple times. So let me just show you how that would look with padding. So over here we have the same configuration, except that we just added a padding of 1. So these gray boxes right here are just the padding, and they're filled with a value of 0. So their only purpose is basically to allow the kernel to properly process the edge pixels of the original image right now, so we can ensure that they're fully represented in the output. So let's say that this is the edge pixel, because it is. Well, now we can see that this edge pixel can be covered by multiple different positions. This is the first position of the kernel, which will cover this edge pixel. This is a second position of the kernel, which will cover this edge pixel. And right here we have a third position, which will also cover this edge pixel. So basically, with padding, the top left corner of the original input can be covered by all of these different configurations. And this makes that specific edge pixel much more represented in the output matrix than it was without the padding up here. So that was kind of the thing I tried to explain before. So I hope it makes a little bit more sense now that you have seen a specific example of it. Great. So now that you see these different hyperparameters whenever you configure a CNN layer in, for example, PyTorch, you'll know what padding is, you'll know what stride is, and also what kernel size is. And now we basically have the basics of convolutional neural networks down, so why they work the way they do and why we use them. And now we can go and take a look at how we can actually use them for our use case. So we have gone over how we can represent images in computers like this, that is basically just pixels, and then we pretty easily was able to understand how we could use a kernel to slide across the image. But what if we have audio, for example? Because audio is kind of a different thing than just an image. So let's talk about how we can represent audio in computers. First of all, whenever you record audio, you can represent this audio as a waveform. So what you do when you record audio is that you go from analog to digital. So analog is just a continuous signal. That is what you hear in the real world. So analog is just real world sounds basically. Then you want to convert these analog signals into something that the computer understands. So you take a bunch of measurement within a time frame, and then you get a bunch of discrete values out. So by discrete values just mean 1, 2, 3, etc. instead of a continuous graph like you hear in the real world. So a microphone basically just listens to audio, and then every something millisecond it just takes a measurement of how loud the audio is, and that will then be measurements of audio which we can then play on the computer. So when you talk about sample rate, for example, that is how many measurements are made by the microphone per second that you measure in hertz. And the output of all these sample measurements is a WAV file, which will then store that. So let's say you go to a drum march like this, and then you put up a microphone and listens. Then what you'll end up with is a WAV file that will measure the amplitude, so the strength of the signal. So right when he bangs his drum, the signal will be pretty loud, but when he is not banging his drum, the signal will be pretty low. So on the y-axis right here, you'll have the strength of the signal, and on the x-axis, you'll have the time of the signal. So this is in the end of the recording, and this is the start of the recording. So this right here only measures the strength of the signal, but it doesn't really measure the tone that is actually played. And that is because the tone that is actually played is encoded into the signal. So the amplitude right here is the sum of all frequencies at a given time. So both the low and the high tones just added together, because that is also what we hear with our ears. So low frequency is encoded such as the peaks and the troughs of the wave would be far apart, and then a high frequency would have the peaks and the troughs of the wave packed tightly together. So this is the most basic representation of audio basically. We just measure that and then we get a WAV file out. But we need to convert this to something which we can actually use with CNNs. So we can take this a WAV file and convert it to a spectrogram. This is just a regular spectrogram. So how we do this is that we use something called the Fourier transform to extract the frequencies and the strengths. So up here we talked about how the tone is not encoded, the tone is encoded into the signal, but it isn't really explicitly shown. We can only see the strengths of the signal and then the time. Well, down in a spectrogram, we can see the specific frequencies, so the specific tones, and the time, and also the strength of the signal. So we have 3 different axes here, whereas we only have 2 on this diagram. And the way we go from this one to this one is by using the Fourier transform to extract the specific frequencies from this, because they are embedded into the signal. And that is a little bit complex, so I won't really go over this in this video. So what you get out of this is now a diagram where you can see the time, frequency, and the frequency strength as I just explained, and not just the sum of all frequencies like we were able to see up here. We also have a linear scale right here on the x-axis. So the frequencies go from 1, 2, 3 and all the way up to 10 kilohertz, where the very low frequencies, so the bass sounds for example, are down here, and the high frequencies such as a flute or a whistle would be up here. Cool, so now we know what a spectrogram is. And what we then do to be able to work even more with it with CNNs is we convert a spectrogram to a Mel spectrogram. So a Mel spectrogram is kind of like a normal spectrogram, it is just a little bit different. So spectrograms can be changed to match how humans perceive audio. So up here, this is just a representation of audio, but it isn't exactly how humans would hear audio. So for human ears, we are much more easily able to hear changes in low frequencies. So whenever you change from 100 to 200 Hertz, for example, so from a low bass sound to a little higher, a little more high-pitched bass sound, we'll be able to hear that frequency way more easily than a difference between high frequencies, such as 10,000 to 10,100 Hertz. So this means that this linear scale over here isn't quite sufficient for how the humans are actually hearing. But because if this down here is much more distinguished for human ears than this one up here, meaning that we can more easily hear changes in these frequencies than in these ones, well then these ones down here are obviously more important than the frequencies up here. But right now, all of these different frequencies take up as equally much space on this plot, so they are obviously the same. And that is exactly what we do not want if we want to make it fit to how the human ear listens. So with Mel Spectrograms, it is basically the same format as up here. The graph is going to look exactly the same, just with a little bit of a change. So the y-axis follows the Mel scale, so the bands of energy at the bottom will look taller and more spread out, while the patterns at the top will look more compressed. So up here, because these frequencies aren't as important to the human's ear, the changes in these frequencies aren't as distinguished for the human ears, these will be more compressed, so we'll lose more detail, and these down here will then take up more space on the plot, and then also be more recognizable by the convolutional layers, just like it is more recognizable by the human ears. So these Mel spectrograms is what we are going to feed into the convolutional neural network. And as you can see, it is actually just an image right here. So just like we can process an image of a dog, we can also process this image of a Mel spectrogram. So why would we use a Mel spectrogram for a convolutional neural network over just a normal waveform diagram, a waveform representation of the audio up here? Well, a single point on the waveform up there is just the sum of all different frequencies at that moment. The difference between that and a Mel spectrogram is that a Mel spectrogram details each different frequency, so it's much more detailed. Here you can see the specific decibel values at a specific time point for a specific frequency. Up here you can only see the strength of the signal, so how much noise there is at a specific time point. So this also means that this is basically a line up here, a 1D line, whereas this is a 2D picture, just like an image which the CNN can look at. Also, if you think about it, the waveform is kind of like a blended smoothie because you have all the different frequencies blended into one right here. So if they are both high and low frequencies, they'll probably just be added up right here, and then this will be that specific time point, that specific sample right there. Whereas if you have both high and low frequencies, you'll be able to keep those apart or tell those apart from this image you see here in the Mel spectrogram. So because this Mel spectrogram is deconstructed or more detailed, we can say that this is kind of like a deconstructed smoothie where you can see all the ingredients instead of being able to only taste the smoothie but not see the ingredients. So having this extra level of details is pretty important for the CNN because it gives it a better basis for actually getting to know this audio signal and learning what it is. Another thing we're able to do with these spectrograms is that we can use the Mel scale, like I just explained before, and in here we can represent these low frequencies as being more important than the high frequencies, because the Mel scale emphasizes low frequencies because of the not linear scale by giving them more resolution while grouping these high frequencies together with less detail. Also, convolutional neural networks are better at handling sounds shifted in time with spectrograms than with waveforms. So for example, if you have a sound signal right here in the waveform format, you can see that right here we have a clip, maybe it's 5 seconds long, and then there is a pretty loud noise right here in the start, and this might then be a door knock, for example, which a neural network could learn. But let's say you have the same 5-second audio clip, but the door knock is in kind of the end of the sound clip instead of in the start. Well, it is the same door knock, so we would expect the neural network to predict it as being a door knock, even though it is in the end of the audio clip. But well, that is not really how it works. This is actually the same problem with translation invariance, which we talked about earlier, meaning that the kernel can slide across a Mel spectrogram like this, and then because the kernel has been trained to find specific features such as this one, which might be a door knock, the kernel would be able to find the door knock regardless of where it is in the signal. Whereas if we just took this entire signal and passed every single sample into a neuron of its own, the neural network would have to see this signal being in every single different point in the audio signal to learn all the different variations that might occur in the real world. So that is why CNNs are better at handling sounds shifted in time with spectrograms than with waveforms. It is kind of the same problem as we talked about earlier, just for images. So we can also talk about how it is actually seen as the CNN. So whenever this is run into a CNN, but represented as a waveform, this shifting in the signal would completely change the raw input values. So a convolutional neural network would have to relearn the same features at multiple different positions, which makes generalization harder. So let's say you trained a CNN with only the waveform, but then all your training data had the actual sound in the start of the clip. Well, then if you try to use this on other samples that the network hadn't seen before, but now the sounds are the same, but then shifted a little bit, then the network might perform really bad, even though it has already learned what all these sounds are. And the problem is then only because your training data wasn't diverse enough, but only contained samples where the sounds are in the start of the clip. With a Mel Spectrogram, the time shift will move the pattern horizontally, but the overall frequency pattern will stay intact, and because the CNL kernel can detect this different shape, and extract that specific feature, it'll just do that just at a different time position, thereby making it more time invariant like we talked about earlier. So therefore, we definitely want to use Mel Spectrograms instead of just the raw signals of audio up here. Luckily, it is very easy to convert between this one and this one down here, the Mel Spectrogram, whenever we work with audio, because most machine learning libraries, such as PyTorch for example, has inbuilt APIs for doing exactly this. So now we know how we can work with audio. Let's talk about the specific model architecture which we'll implement, and also the dataset which we'll work with. So cool. First we can talk about the dataset. We have the ESC dataset, ESC50. This dataset contains about 2000 audio files. You can find it on GitHub. It's very open and very well used. So there are a bunch of models already trained on this out there. And each of these 2000 audio files has been labeled with one of the 50 classes below. So for example, you might see an audio file and then it says that this audio file is a dog speaking. So the basic flow of our neural network is therefore going to be, we take the VAV file from the dataset, we turn that into a Mel Spectrogram, then we create a neural network where we can pass in the Mel Spectrogram, we have some hidden layers, and then we have some output layers. We'll have about 50 of these because there are 50 classes to pick between. And then each of these classes will give us the probability of the VAV file being that specific class up here. So for example, we might see that it is 90% certain that it is a dog in the audio file. And then it is, for example, 1% certain that it is a training in the audio file. So that is kind of the super simple architecture which we're going for, or the super simple flow, not the architecture. And now I'll just walk you through the architecture as well. So we'll use a ResNet, which is going to be a paper which we'll base our architecture on. You can read the paper right here. And then we'll implement a pretty similar architecture since it works very well. So ResNet contains a very deep network with first a 7x7 kernel convolutional neural network, convolutional layer. Then we have multiple convolutional layers after that, divided into blocks of 2. Each of these is called a residual block as well. And these residual blocks have different kernel sizes and also out channels, as you see, 3x3 all the way through, but 7x7 up here. Then we have 64, 128, 256, and then 512 lastly. Then all of these are put into an average pool, and then a linear layer is used to classify whatever should be classified with the neural network. And one of the things that was introduced by this ResNet paper is something called shortcuts. So with very deep convolutional neural networks like this, you'll see something called a vanishing gradient problem. So in deep networks, gradients can get smaller and smaller, so the earlier layers stop learning. So whenever you do a forward pass during training, you get a loss all the way down here at the end, and you can then calculate the gradients for each layer, which will tell the previous layer that these weights and biases will need to be changed in this way for the loss to be minimized for this layer. So basically, each layer will pass the blame of the high loss back to the layer before that. So this correction signal, if you might call it that, will be passed all the way back through all of these layers. But because it has to be passed through all of these different layers, it might get pretty weak up here at the first layers. So we might see a problem called the vanishing gradient problem, where these layers don't really see that they are in blame of any of the loss down here. So the weights and biases of these layers will not be changed a lot, so they won't learn a lot, and therefore the network won't perform very well. So ResNet up here introduced a new thing called residual blocks with shortcuts to help solve this vanishing gradient problem. So without shortcuts and how you would normally do it before ResNet, you would take a convolutional layer, have it produce some feature maps, and then you would pass those feature maps into the next convolutional layers and pass those feature maps through the next ones, etc., all the way through the deep network. And then that is when you see the vanishing gradient problem. With the shortcut, you then do the exact same, but you make a little bit of a change. So whenever you get an output from a block like this of 2 convolutional layers, you then take the same input as you gave to those, and then you add that input to the output of the layer. So I've expressed it over here with math as well. So basically, the input of a layer is added to the output of the same block's convolutional layers. So instead of just having the final output be whatever the block generates, the final output is going to be whatever the block generates plus whatever you inputted to the block in the first place. We can then also see that what the layer learns, or what it is able to, or what it should generate, is going to be the final output minus the input. That is the difference between the input feature map and then what it should improve the feature map with to become even better. So instead of having to learn to create a full feature map down here, it only has to improve the feature map, so the input, by making a small difference in the feature map, thereby making what the layer has to learn way simpler. So without a shortcut, a convolutional layer would have to learn to generate a feature map, so it would have to learn the entire final output from scratch. But with a shortcut, the convolutional layer would only have to improve the existing feature map, so the X, by making a difference within that feature map. So it has to learn less. Also, during backpropagation, the addition operator acts as a gradient distributor, so the addition operation, which you see right here, the plus. So what happens is that it copies the incoming error signal, so the gradient basically, and then it sends that down both paths simultaneously. This is the first path, this is the second path, and then even if the gradient going through the main layer, so the layer right here, the path right here, it gets weaker, the clean gradient from the shortcut, so the clean gradient right here, ensures a strong signal that always reaches the earlier layers, preventing training from stalling. So this is kind of a difficult concept to understand, but I hope you just understand at least why we fixed this, and also a little bit about how the fix works. Also, you need to know that these residual blocks exist. So residual blocks are just sets of these convolutional networks, or convolutional layers, put into blocks, where you then add the input of the layer to the output of the layer to create these shortcuts over here, and then allow the network to actually train properly. Good. So now that we know a little bit about the architecture which we're trying to build, we can try to map it out how we actually want to do this in PyTorch. So the architecture, in the architecture, we'll first define the residual block. So the residual block is just this reusable block right here. So this one, for example, or this one, sets of two convolutional blocks, which we can use down in our final architecture. So first we want to define the first convolutional block, then we have a second one, and then between each of these, we'll both put in a batch norm 2D to decouple these two blocks, and we'll put in an activation function, which is relu, to add in this nonlinearity into the network. So we have two different blocks of these two, where the shortcut is then added at last, right here, after the second block. After the second convolutional layer in the block. So what happens is that feature extraction takes place, then this is done to stabilize training, nonlinearity is added into the network, then from this feature map over here, another set of feature extraction is done, training stabilized again with this batch norm, the shortcut is added, so the input is added to the feature map, and nonlinearity is introduced again. So this residual block right here is just a reusable block where we can adjust both the kernel sizes and also the stride, for example. Good. So how is our final architecture going to look? First, we'll have this initial convolutional block up here. So that is what we see right here with a 7x7 kernel and a 64 output channel and 64 output channels. This is then pooled, and right after the pool, we'll see these layers of residual blocks being stacked on top of each other. So first, we define this initial convolutional layer. It is going to have a single input channel for the Mel Spectrogram. We'll set the kernel size to 7, stride to 2, padding to 3, and then we'll output 64 output channels. So we'll create 64 feature maps. This will extract the broad features from the Mel Spectrogram, and then after this, we'll pass this into a batch norm 2D, which will then help stabilize the training. We'll then pass it through the activation function, and we'll then pool the results to reduce the dimensions of the output from this feature map over here. We can also quickly just go through the dimensions of the tensors, which we'll see in the initial convolutional layer. So first of all, we pass in a Mel Spectrogram. This is going to be a grayscale spectrogram. So we'll have a batch size, that's how many we pass in at a time. Then we have the grayscale, meaning we'll only have a single channel. If this was RGB, for example, we would have 3, because we have 3 channels, but we are grayscale, so we only have 1. Then we have the height, which is 128, also called the frequency bins in the spectrogram. And we have the width, which is 256, also called the time frames in the spectrogram. It will then produce 64 feature maps, which are passed through the batch norm. So that input will also be 64 and output as well. It is passed through the nonlinearity, where we don't really define the inputs or output channels. And then we pass it through the max pool. And here, because we have 64 feature maps, we pass in 64 right here. And then we have the height right there and the width right here. So as you see, this height is about 1/4 of this height, and this height is about 1/4 of this height. And that is because the stride of 2 is going to reduce the dimension of 128 by 256 with 1/2. So that leaves us with 64 by 128. Then over here we have a stride of 2 as well, which will furthermore reduce our dimensions by half, leaving us with 32 by 64. So that is the dimension of the feature maps, and these are the amount of feature maps. Then this output is passed into the first convolutional block right here, consisting of 3 residual blocks. So all of this up here is copied 3 times, 1, 2, 3, each with the in and outs of 64 feature maps. So the reason we have 3 right here is because we have 3 right here in the ResNet as well. So we have a block of 2 convolutional layers, another block of 2, and then another block of 2. And that mimics exactly what we have right here, where we have 2, and then we have 3 of those. So the purpose of this one is really just to deepen the network and learn more complex features without changing the dimensions. So that is also why you see that the dimensions do not change right here. We still have 64 feature maps with the same width and height. Then next up here, if we take a look, we have a set of 4 residual blocks with 128 in output channels. So if we hop over here to the second one, we have 4 of these residual blocks. And then the first input channel is going to be 64 because this one has to be, the out right here, has to be compatible with the in of the first residual block. And then otherwise the ins and outs, so the amount of feature maps outputted for each of these is going to be 128. This means that in the end we'll be left with 128 feature maps instead of 64. And then also we'll have our feature maps downsampled from this dimension to this dimension right here. So we'll do a half reduction in the dimensions. So basically we reduce the spatial dimensions while increasing the number of feature channels, and this allows us to just capture more intricate patterns. So this is just a higher abstraction than this over here. Then going over to the next one, we see that we have 6 of these residual blocks, and then the first input channel is going to be 128 to make it compatible with the output from this one. But otherwise each of these blocks will produce 256 feature maps. And I also cut the resolution in half again. So the output is going to be 256 feature maps and then half the resolution per feature map. So here we just get even more abstract. And then lastly, we have this convolutional layer number 4, where we have 3 residual blocks with even higher output channels. So we have 512 as the output right here, with very few pixels at the end. So here we'll extract the final and most complex feature representations before the classification stage, where we pass it into a linear layer over here. Cool. So let's just take a look at what this entire process does. So first of all, we capture the broad patterns with a 7x7 kernel, and then we downsample 4x. Then with the series of 4 convolutional blocks, we then capture more localized features because we have 3x3 kernels. And then each of these convolutional layers have the dimension size while doubling the amount of channels, so the amount of feature maps. And then hopefully we have the amount of features extracted over here, which we expect. And these features are stored in 512 different feature maps, and each feature map will be 4 by 8 in their dimensions. Now, as you can probably imagine, these are very pixelated feature maps. And what will be done to these pixelated feature maps is actually take these and reduce them even further down to a single number, so a 1 by 1 that represents each feature map. And this is done with the adaptive average pool 2D. So I explained how the pooling works earlier. So this is just going to be the average pool, which we talked about. So this layer right here has a single job, and that is to take the 4 by 8 spatial grid, so the feature map, and then for each of the 512 channels or feature maps, it'll average those values down to a single 1 by 1 value that will then summarize the spatial information for each feature channels. So we'll basically end up with a vector with only 512 values. So even though we reduce it down to a 1 by 1 instead of a 4 by 8, we still have the same format of the tensor. We have the batch size, then we have the feature map, and then we have a 1 by 1. But since this is a 1 by 1, we can really reduce this down by flattening this tensor structure. So we can go from this structure right here, and then we can flatten this to a single vector, so we get the batch size, and then just a single vector or list basically of 512 single numbers, which is what we talked about here. So now that we have flattened all the feature maps, then we can pass these feature maps through a layer called a dropout. This dropout layer is done to prevent overfitting during training, so it is only applied during training. And what it does is simply that it helps the network not to get too overconfident by randomly skipping some neurons during training, and this prevents the network from relying too much on specific neurons because sometimes they're just switched off basically. And by setting a drop-off rate of 0.5, about half of the neurons are turned off before being passed on to the next layer. So if all neurons aren't always available, then the network won't be able to as easily just remember the data, and then the overfitting problem will become less prominent. So now that we have this data structure right here, the batch size and then 512 neurons numbers in an array, then we can take all of these numbers and then pass them into a linear layer that just takes 512 as the input features, and then it outputs 50 different features as well. These 50 features correspond to the 50 different classes that exists right here in the dataset. So up here we have 50 different classes, and then we would like to output a probability for the sound being each of these. And that is what we do down here with 50 different output neurons. So that is the simple walkthrough of the architecture which we're going to build. So I hope you learned something about both convolutional neural networks, but also the specific architecture and model which we're going to build. Otherwise, you'll also learn more about it whenever we build out the actual model and then test it. So without further ado, let's hop into the code now and then try to build out this specific architecture. Good. I have opened up my code editor Visual Studio Code, and then the first thing I'm going to do is just make sure that you have the same extensions as me in case you want to make it look exactly the same. So for Python specifically, I use this one, also pip8. I also use iSorts. Then I have this Pylance, Python, and Python debugger, and then I have Tensorboard. So in case it doesn't look like me and you don't know why, and you can't figure it out, maybe that is why. Okay, so first I'll open up a folder, and then I'll say documents, go under my folder where I would like to create the project, and then I'll call this audio CNN, like that. In here I'll just say open. I'll then close this tab down, and then I'll say Shift Control P, and then I would like to create a new Python environment. I'll say venv, and then I would like to put in a 3.12.3, and then I'll just wait for this to create. Good. In case you didn't see any Python versions, you should be able to hop into Google and then search for Python install, and then find a Python version that suits you. So for AI, I usually use 3.12 or 3.11 just because the newer versions sometimes aren't fully up to date with the new Python versions. The newer versions aren't fully up to date with the machine learning and AI libraries. So therefore, I'm just going to go ahead and move with 3.12 for this video. You can go ahead and install it by going down here and then finding the version you're looking for. So I think I picked 3.12.11, then you can download that. And after a quick restart of your computer, maybe you'll be able to open up this, create an environment, and then use the created environment like I just did basically. So the first thing I would like to do is create a new file. I'll say model.py. So this should contain our model for, I'll just close this down, this full model which we just drew out in the architecture here. So first I would like to create this residual block just because we'll reuse it in the full architecture down here. So I might as well just create this as the first thing. So I'll hop in and then I'll create a new class. I'll then say audio CNN. I would like to inherit from NN, and we'll just need to install the Python package here. So I'll say open integrated terminal, and then I can say pip install torch. So that is PyTorch, which is going to be the AI library which we'll use to both create the model, so the architecture, and also to train the model. And now that that is installed, we can go ahead and just import it up here. So I'll say import torch.neural networks as neural network. Then we can say neural network.module like this, and define a class like that. So this just means that the class that we just declared will inherit from this already existing class from PyTorch. And I'll just rename this residual block actually, because that's what I promised to do. I promised to implement the residual block first. Then if I close this down right here, we should be able to implement this class. So first of all, I would like to define a constructor. So I'll say def init. So this is what happens when the class is constructed. Then I'll pass in self first of all. And then if we go back here, we can see that this residual block should be able to be reused, but the in and out channels, so this is 64, will differ depending on which convolutional layer it is. This one is going to be 128, 256, etc. So we'll need to make those variable. So I'll just go ahead and say in channels, out channels as well. I'll put in a stride because that should be able to be varied as well. And that should be it for now. Then we can call the constructor from the superclass, so the one right here. And then I'll say, to do this, I'll say Subaru.init. So we'll just call the constructor from the parent class. And now we should then be able to define the different layers which we'll need. The first one is going to be this one, Convolutional 2D. So I'll go ahead and say self.conv. One is going to be equal to neural network.convolutional 2D, like that. And then we can put in the in channels, we can put in the out channels, and we can then put in free. So that is going to be the kernel size, as you see right here. We can put in the stride, and we can put in a padding of 1. So I'll just set the padding to 1, and then I'll put in something called bias is equal to false. So going back to the diagram here, we have batch norm coming right after convolutional 2D. So inside this batch norm, you already have a shifting mechanism, and the bias false will then make sure that the bias for this convolutional 2D layer will not be learned. So basically there is no bias for this 2D layer because it is already included in the batch norm. So it would just be a waste of compute to just both have a bias right here and have a mechanism for shifting right here in the batch norm 2D. So it's pretty standard practice when using batch norm after 2D, after convolutional 2D, to just set the bias to false to save computational processing. Cool, not processing, but parameters and computation, sorry. Cool, so after this we can go ahead and put in a batch normalization layer. So I'll say self.bn1. This will be equal to neural network.batch norm 2D. We'll put in the out channels right here, because that is really all that is needed for that layer right here. We only need to put in what size it should expect. Then we can put in another convolutional layer. So I'll just copy this one right here, call this conv2 instead. This will have in channels as well. Sorry, it will have out channels because it should support the output of the previous convolutional layer right here. So if this outputs out channels, this one should input out channels such that these two layers are compatible. The out channels will just be the same as out channel right here because we don't really have anything else defined. Good. Now we'll just create another layer under this. This one will be the batch normalization layer 2, and we'll just set this to out channels as well. Next up, we can go ahead and define the logic for the shortcuts as we talked about earlier as well. So we have the shortcuts being shown right here, and the shortcuts need to be routed from the start of the block to the end of the block. So we take the input data and then we add this to the output data that the block produces. And we have two different cases here, as you can see. There are some lines that aren't fully connected, and then we have these continuous lines. So the reason that these dotted lines exists is because the input tensor for this layer right here doesn't really match the output tensor of this layer. So we'll need to do a transformation for this input data such that we can actually add it to the output data. For this one, for example, or for this one, for that sake, the input data is 64 feature maps, so we can just take this and add it directly to the output data over here. So we won't really need to do any transformations, but right here the input data is 64 feature maps, but the output data is 128 feature maps. So we'll need to transform this tensor so we can add it to the output data. So those are the two different cases which we'll need to be able to handle. So first of all, I'll go ahead and create a shortcut instance variable. So I'll say self.shortcut is equal to neural network.sequential. And I'll just make this a sequential, so just an empty sequence that by default just does nothing for the shortcut. It just returns the input unchanged, and this is just to have it initialized. Good. After this, we can say self.useShortcut, and we'll use the shortcut if the stride is not 1 or input channels. So in channels right there is not equal to the output channels, like this. So first of all, if the stride is not 1, then the code will by design downsample the data, and therefore the output matrix will not look like the input matrix. So as you probably remember, if we hop over to stride over here, let me just see if we can find this right there. So stride 2, for example, will then take an input matrix that is a 6x6 and make it all the way down to a 3x3, thereby reducing the output matrix, the input matrix by 75%. So we won't really be able to just take this one and then add it to this one because the width and height does not match. Instead, we'll need to do a transformation making the input and output compatible such that we can add them together. So that is exactly what we'll do if the stride is not 1. The second option is that if the input channel does not match the output channel, and let me just go up here, in that case, that is what we hit right here. So whenever we have 128 feature maps and we need to make that compatible with 260 or 256, then we'll need to handle that case as well. So let me just handle these cases, and I'll then say if self.shortcut, or I'll say use shortcut, and then we can say self.shortcut is equal to neural network.sequential, and then we'll pass in a neural network.convolutional2D. Inside here, we'll pass in the input channels, the output channels. We'll pass in a kernel size of 1. We'll put in the stride to be stride. We'll put in bias false. And after this layer, we'll put in an additional layer. And the reason we put it into this nn.sequential is because then we can stack multiple layers right after each other, making the network deeper. So we'll just want to put in a neural network.batch normalization 2D right after this, where we put in the output channels. The reason we're using a convolutional layer right here is because this transformation is applied to the input data such that we can add the input data to the output of these layers right here in case we want to apply the shortcut. So first of all, if a stride was more than 1 for this, well, that means that the output matrix will be downsampled. So for the input data, we'll have to downsample that similarly. So therefore, we'll need to apply the downsample, also the stride, to the input data as well. And then if the out channel does not match the in channel, well, then we'll need to transform the input data also to be the size of the output channel, such that the amount of features is the same both for the output of the layer and also for the input of the layer, which will transform. Good. So now that we have defined the architecture of the actual layer, we can also define the logic of the forward pass. So I'll go ahead and create a new function down here. So I'll say def forward. So this is going to be which layers are used in which order, for example. So we can control completely how the forward pass works. So we'll pass in self, we'll pass in the input data, that is going to be x. We'll then just do that. And then I would like to say out is equal to self.convolutional1. So the first thing we're going to do is we'll take the input data, pass it through the first layer, which we defined up here. Next, we'll just copy this line, then we'll pass out through the next layer, and that's going to be batch normalization 1. Then we'll say out is equal to torch dot, and I think we just need to import torch, maybe not, torch.relu. We'll just import it like that, torch.relu, where we pass in out. So we have convolutional, batch normalization, activation function. So that should match what we did down here. So we have convolutional, batch normalization, activation function, and another convolutional. So we can just take this entire thing, and then we'll just copy that down. And then we'll have convolutional layer 2. We'll then have batch normalization 2. And we can then also apply the shortcut. So I'll then go ahead and say shortcut is equal to self.shortcut. I'll pass in the input if self.use shortcut else x, like this. So basically what happens is that up here we determine whether we actually need to use the shortcut transformation down here, because if the input does not match the output, we'll need to apply this transformation to make the input x right here look like the output, so out right there. So if this variable right here is true, that means we'll need to apply the transformation. So we pass the input into the shortcut transformation function right there. And this means that it'll now look exactly like the output of this layer right here. Otherwise, we'll just pass the input straight away into this shortcut variable such that we can add out and then x together. So now we can say out add. So that is out with the shortcut added. That is going to be out plus shortcut like this. And lastly, we'll just need to return out as well. I think it'll have to be out add like that. And I think I just forgot one thing actually. We need to pass in or put in this activation function right here, relu. So what I'll do is I'll just say out is equal to torch.relu, like that. pass in out at right here, and then I can return out right there. So as you can probably see now, the architecture of the actual code very much resembles how it looks in our color diagram right here. We have convolutional, batch norm, relu, convolutional, batch norm, shortcut, relu. And that is the exact same thing we have right here. Convolutional, batch norm, relu, convolutional, batch norm, shortcut, relu, like this. Cool, so now that we have defined this reusable residual block right here, let's go ahead and define the actual neural network down here, which we can use to both train and also run inference. The first thing I would like to do is just create another class. So I'll hop down here and then I'll say class, and then I'll call this one audio CNN. I'll then say inherit from nn.module again. Down here we can define a constructor, so I'll say const init. And then I would like to pass in self as well as the number of classes. I'll set this to 50 because that's how many classes we have in the database, in the dataset. Then I'll call the super, so the parent constructor, and then we can define the different layers. First of all, we have the initial convolutional layer down here with the convolutional, batch norm, relu, max pool. So we'll just do the same as we did up here basically. We'll say self.convolutional1. And that is going to be equal to neural network.sequential. And we would like to pass in neural network.convolutional2d. We would like to set the in channels as 1, because remember we only have a single input channel for our Mel Spectrogram. Then for the next one, we define the out channels. Here we'll define 64. So I'll just go ahead and do that. Next, we can go ahead and define the kernel size. That is going to be 7 by 7. And we'll then also set the other hyperparameters. We'll set the stride to 2, the padding to 3, and we'll set bias to false because a batch norm 2D layer is going to follow it. Good. So right after this, I'll put in a neural network.batch norm 2D. Then I'll put in the parameter 64 because that is the output of this one right here. Right after that layer, I would like to put in a activation function. So I'll say neural network.relu like this. I'll then say in place, set this to true. So the reason we supply this in place true flag is because that means that this relu activation function will be applied directly to the output of the previous layer, which in this case is batch norm 2D. The alternative to in place true is to actually go ahead and manually write out the variables like it is done right here, where you say torch.relu, for example. We just use in place true such that we can use convolutional 1 without having to type out the variables for every single one of these, store the results, and then pass the results into the next one. Good. So after relu, I would like to say neural network.maxPool2d, and then we'll put in 3 as the kernel size. We'll also put in stride 2, and I would like to put in padding 1 as well. Then I'll save this, and then below this I would like to create another layer. So the next layer is going to be self.layer1. So if we just hop back into our architecture, now we have created the following initial convolutional layer right here. And then I would like to create this one. It really consists of 3 of these residual blocks, so we'll need some way to create them instead of typing them out manually every single one. So I would like to just loop through a loop 3 times and then create 3 of these residual blocks. So the way I'm going to do this is by saying neural network.module list. And then I would like to pass in an empty array. And then I'll say residual block. And then I can pass in 64, 64, and then I can go ahead and say for I in range 3. And what this will do, and we just need to enclose this by a parenthesis, I can see, like that. What this will do is it'll just loop through a loop 3 times, and then it'll create 3 of these residual blocks, each with a 64 input and a 64 output, and then it'll append these to a list called module list. And the reason that we put it into this module list is because that tells PyTorch up here that the residual blocks are actually trainable. So it knows that it should be able to change the weights and biases of all the elements within this module list right here. Good, so that was the first one. Let me just take this line from layer 1 and just copy this down, call this layer 2. And then hopping back into the architecture, we can see that for the second layer, we're going to need 4 then we're going to need 6, and then we're going to need 3. So I'm just going to copy this down, and then I'll say 4 right here. I'll say 6, and I'll say 3 again. I'll call this layer 3, and I'll call this layer 4. And then remember how I, in the architecture right here, said that we need to make the first input channel compatible with the output of the last convolutional layer right here. Well, for this one, we are working with 128 in general, but we still need to make this first one compatible with 64 right here. So what we can do is that we can say 64 right here. So I'll say 64 if I is equal to 0, so if it is the first iteration, else I'll say 128, and then for the output it is always going to be 128. This will just have to be 0, of course, like that. So that just means, if you didn't quite catch that the first one, so this one for example, the first residual block within this convolutional 2 will just have the same input as this one has its output. This means that these two, convolutional 1 and 2, will be compatible data-wise. Good. We'll just need to do something kind of like this for the two others right here. So what I'll do is I'll actually just copy these down quickly. And then this was 6, and this was 3. Remove these again. Call this 3 and 4. And then for the second one right here, we are working with 2, 5, 6, 2, 5, 6, and this is going to be 5, 12, and 5, 12. And we'll just need to ensure the compatibility of these ones as well. So this one is going to be 128. This one is going to be 256. And that should make these layers compatible with each other. Good. Lastly, we'll just need to, that was all of this by the way. Lastly, we'll just need to put in this average pool first of all. So we take all of these feature maps, which is 4 by 8, and then we reduce them down to a 1 by 1. So we can say self.averagePool is equal to neural network.averagePool 2D, and then we'll just pass in 1 by 1 as the output size, which we are looking for. And then we can say self.dropout is equal to neural network.dropout like this. We pass in 0.5 to 0 half of the neurons or half of the data. So that is the one right here we're taking care of. Next up, we can say self.fc. So that is the linear layer right here. That is going to be equal to a neural network.linear, where we take in 512 because those are the amount that we get right here whenever we flatten the feature maps. And then we would like to have an output feature of 50, which meaning we can classify 50 different classes. So 512 input, and then a number of classes output, and we have 50 up here because we have the data set containing 50 classes. And then exactly how we also define the forward function up here, we can do the same for the audio CNN down here. So I'll say define forward, and then we can use self x like this. And then we simply just pass the data, so the input data right here, through all of these different layers. So I can say x is equal to self.convolutional1, where we pass in x. We can do the same for the second one. We can do the same. Oh, sorry, we do not need to do this actually. We need to go to layer 1 and loop through the different residual blocks and then pass it through that. Just a small mistake on my end. So I'll say for block in self.layer1. So we loop through all of the different residual blocks in this module list right here. And then what we can do is we can say x is equal to block and then x. So we just pass x through every single one of the residual blocks. So that was for the first layer. Then we'll just go ahead and do this for the second layer as well actually. And we'll do this for the third layer. And we'll lastly do it for the fourth layer. So this one will be 2. And we'll have a 3 and we'll have a 4 like that. Next we can pass the data through the average pool. So I'll say x is equal to self.averagePool, where you just pass in x. Then we can go ahead and flatten it. So we go from a 1 by 1 per feature map all the way down to just a super simple vector like this, which is just 512, so just 512 different values. So the way we're going to do this is we're going to use x.view, and then we can pass in x.size. And we can pass in -1 like this. So this view data right here comes from PyTorch, and it is used to reshape a tensor without actually changing its data. And that is exactly what we are interested in here. We don't really want to change the data. We just want to reshape it such that this 1.1 is gone basically. So first we give it the input data right here, and then inside the parameters, we specify the output dimensions, which we would like the X to be in instead of what it already is. So first of all, we would like to keep the batch size as it is. So this is the batch size right here. So that is going to be the first element. So we just get the first element from X, which is the batch size, and just set that as it already is. And then for the second one, we set this to -1. So what this does basically is that it tells PyTorch to just infer the size of the second dimension automatically, such that the total number of elements stay the same. So basically what it does is that it just goes from this to this right here. And that is exactly what we wanted. Then I'll go ahead and apply the dropout layer. So I'll say X is equal to self.dropout. And then for the dropout, I'll pass in X right here. And then we can say X is equal to self.fc, and then I can pass in X as well. So that is the linear layer. And lastly, we can return X, which is going to be the output of the linear layer. This right here was all the code we needed to define the actual model architecture itself. So now we can go ahead and create the program which we'll use to actually train this model. So what I would like to do is open up a new file, call this train.py. And inside here, we're going to define everything needed to train the model. First of all, I just want to create another one called requirements.txt. In here, we can define requirements that should be installed into the container, which we'll use to actually train the model. So we'll just leave this as it is right now, and also just go into train.py, like this. I'm going to use Modal as the cloud provider for today's video, both to train the model, but also to deploy the endpoint where I can run Inference with our trained model later on. So Modal is just a website where you can run serverless GPUs on. So instead of renting a server and then paying for all the uptime, you only pay for the seconds or minutes that you actually use on the graphics cards. Luckily, they have a pretty generous free tier, so you can just do the training and also the inference without having to pay anything basically. So just go to the link in the description and then click on the Modal link. I'll just hop into Modal via the website right here. And then under pricing, if we go to per hour, we can see that an H100 is about $4 an hour. And then the free tier down here gives you $30 per month of free credits. This means you can run this H100 for about 20 hours. I don't think it takes more than maybe half an hour to a couple of hours to train this actual model, which we're going to build. So you won't really run into having to pay anything yourself. So that is very nice. Cool. So to get started with Modal, you can go into the documentation. And then you should be able to find a way to set it up. So pip install Modal we'll need to run first of all. So I'll hop into the terminal right here and then say pip install Modal. And then when that is done, we can go ahead and paste in the next command, which is going to be Modal setup. So now it is done. So I'll just paste in Modal setup as well. And then that should open up a link to a web page, which we can use to authenticate. So if I just take this link right here, and then paste it in over there, should be able to first of all authenticate. So I'll just go ahead and do that. I'll click continue and then just authenticate with my GitHub. And I just authenticated, so now you should be able to click authorize. And then in a couple of seconds, we should be redirected, it says. Then over here, we should be able to see that it successfully wrote a token to our local system, which is perfect. So now we should be authenticated with Modal and we should be able to actually run a program in the cloud. So we'll just try and go ahead and do that. So I'll just go down to hello world, import this program right here, paste that in, and then I'll create this function as well, just paste that in. And lastly, I think that should be enough. We might want to add a local entry point though, like that. Cool. So let me just go through this code and see what it does. So first of all, it creates a new app. Up here, I would like to just name this the same as we name our app. So I'll call this audio CNN. And then it defines a function which will run in the cloud. So this will not run on a local machine, but in the cloud as soon as we run the code down here. So what it'll do is that it'll print hello, and then it'll do some math and then print something out. And then down here, this is what actually happens whenever we run the file. So it'll first of all run this file locally 1,000 times. So it'll print 1,000 times probably. And then what it'll do is it'll run it in the cloud as well. I'll just tone this down to 10 and 10. And this we won't really need. This way we can just test whether modal works. So I can then say modal run train to Py like this. And then it should create the infrastructure in the cloud, run it in the cloud. So right here, 100 is what it ran locally, and the blue text is what it ran in the cloud. So actually you have already run your code on the cloud now. This is not just local, but actually in the cloud. So over here in the modal dashboard, we should be able to actually see, let me just find this, see the stop app. So right here we have the audio CNN, and the audio CNN has an app function, but also the app logs. And then here we can see hello 10, which it printed from the cloud. Good, so modal actually works now, and we can go ahead and set up the actual training script for training our application, our neural network. So that is very good. So I'll just close this down, and then we can move forward. So the first thing I would like to do is just change this application a little bit. I would like to more specifically define the Docker image which we're going to build and which will run over here in the cloud. So one thing I would like to be installed into the Docker image is the actual dataset itself. So if you search for ESC50 and then dataset, you should be able to find the dataset right here. And as you see, if you go under audio, you can see all of these different WAV audio files, which we can then download down into the Docker container and then use to train the actual model. So I would like to say image is equal to, and then we can say modal.image, and we can say db slim. That is just going to be the base image of the Docker container. Beneath this, I'll say .pip install from requirements, and I would like to pass in the specific file which we'll install from. So this will be requirements.txt. So what it'll do is that it'll take this requirements.txt file, find every single dependency in here, and then install those just like we said pip install in the terminal. So that is what it'll do. Beneath this, I'll put in an apt install. This will just install some dependencies into the Linux operating system. So I would like to install, first of all, wget, and next of all, unzip. We can use these to download some things and also to unzip whatever we might need afterwards. I also would like to install ffmpeg for working with sound, and also libs, and then nd file 1, because often when you work with audio and PyTorch, etc., you might get some errors that will occur unless you have this library. So I'll just install it just to make sure. So this should install the Python dependencies, and it should install the system dependencies which we'll need. And next of all, I would like to run some specific commands that actually downloads down this dataset right here to the system. So the way I'm going to do this is by saying run commands. This will then run a series of commands in sequence. So that's why I put in an array to define multiple commands. The first one will be change directory, and I would like to go to the temporary folder and say and wget. So I'd like to download from the internet. Then I'll take the code, copy this HTTPS one right here. Then I'll hop over, and then I would like to remove that, say /archive/master.zip. It'll download everything, and this way we can get it as a zip file and then unzip it right after. Then I'll say -o esc50.zip. I'll just do that, .zip. And then this is the first command we are going to run, or the first two commands it actually is. Cool. So right after this, we can go ahead and unzip this. So I'd like to change the working directory again. And then I'll say unzip esc50.zip, like this. After this command, I would like to create a new directory. So I'll say make directory -p. Then I would like to create an opt esc50 data. So I'd like to take what we unzipped and then put it in somewhere that we can actually reference it later. Then I'll copy what was unzipped from this zip file and then copy it into the folder which we just created under the opt directory. So I would like to say copy /r for recursive. Then I would like to copy from the tmp, and the unzip is going to unzip to a directory called esc50 master. And we would like to take everything from that directory and then paste this into the opt esc50 50 data slash. So we'll take all elements inside this folder and copy them into this one right here. So the last command we're going to put in is just the one to remove all the temporary data up here from the temp folder. So I'll say rm for remove, then I'll say rf, and then we can put in tmp esc50.zip, and we can also just take this one right here and remove that as well. So we'll delete these two ones, and that should clean up the Docker container for us as well. Lastly, we'll take the file which we created up here called model.py and also just import that into the Docker container. So what I'll do down here is say .add local Python source, and then I'll put in the model right here. So this will just reference the model file and make sure that this is copied into the Docker container such that we can import it down here in a function if we would like to. Then we can create a volume, which is like a persistent storage, which we can attach to the Docker container, which is going to be running up here. And this will make sure that even though we run the Docker container and then close it down again, then all the different files which we have downloaded and unzipped, etc., won't just be lost. So I would like to create a volume and then attach it to the following path right here, meaning that whenever we transfer the data to this path right here, close down the Docker container, and then start it back up again, we should be able to find the same data under the same directory. So luckily, Modal is pretty good with this, because if you go under storage, you should be able to just create a volume right here. So you can see volumes. So we can just create this via the code. So if it doesn't exist, it'll just create one. So it's pretty simple to do. So we'll say volume modal.volume. And then I would like to say from name. I can then pass in esc50 data, and then I can say create if missing true, like this. Below this, I would like to say modal volume is equal to modal.volume.from name, and then I would like to say esc model, like this, and then I would like to say create if missing true as well. So the volume right here is going to be the one that attaches to where we store all the data, and then volume right here is going to be the one we attach to the model which will generate whenever we train the actual model. So the model file, so the actual model will generate a model file that may be a gigabyte or something in size, so we would like to store that in an external volume as well. Obviously, when we run Inference, we won't really need to attach this volume because we don't really need to have the data available. We already have the trained model. So that is why I split them up into two different volumes. Then what I'll do is I'll just take this one right here and just only call the one called if on remote. And then I would like to just call this function train. So I'll say train.remote to run the training job in the cloud. And then what I can do is just remove this as well, and then just say print training. Inside the function, we can define the things that should be available for this function whenever it is running in the cloud. The first thing I would like to do is to say image is equal to image. So when this function runs, it will have all the things we have defined up here available, such as ffmpeg, the requirements in the Python environment, and also the dataset from this volume right here. So I would like to, after image, go ahead and define the GPU which it'll run on. So remember how I said that you can choose a GPU in here, and it costs a specific amount. Let me just go to the pricing. So if you want to run with an H100, you can do that pretty easily, but you can also set them to other GPUs and then you just pay per use. I'll pick this A10G right now because it's pretty simple and paste it in right here under GPU. So whenever we run this function, it is going to run on this GPU specifically. Good. So after this GPU, I'll put in the volumes that should be accessible by this function whenever it runs in the cloud. So the first one is going to be the volume for storing the data. So I'll say /data, and then we can pass in the volume. And then I would like to say /models, and that is where we attach the model volume to. So the model volume should be attached to this right there. Good. Then we'll at last just set a timeout. So I'll say timeout. So that is how long this function can run for before it times out. And because it is a training function, we'll probably want it to be able to run for a couple of hours. So I'll just say 60 by 60, that is 1 hour. And then I would like to give it maybe 3 hours before it times out. Good. So now if we go ahead and run this, we should be able to see it build the actual Docker image successfully. So I'll say modal run train.py, and then we'll see what happens. So I'll just go ahead and wait for this to finish. This one just finished after a couple of minutes, and we see that it says training, and because it is blue, we know that it ran in the cloud. Also, we can see that it ran through all these different steps, and these different steps are the steps which we defined up here. This is a step, for example. The apt install is another step, run commands is another step, and this one is another step as well. So we can see how it did what it was supposed to do, and then it says training at last. So it seems to be working just fine. So now we can go ahead and define what we actually want to do with the dataset, which we just downloaded. Another thing you just need to notice as well is that if you run this again, it should be cached because these steps are cached sequentially such that this one is done first, then it's cached, then this one is done afterwards and cached. This means that if you change nothing, then it won't really have to do all of these different steps again. If you change the first step up here, then it'll have to invalidate the cache and redo this step and all steps coming after that. But if you just change this line, for example, then it'll only have to redo this line and then not the ones coming before that. So try and not change any of these too much, because then you'll just have to wait for a couple of minutes, depending on what you have done up here, for all these steps to rerun again. We will have to run all of this again a little bit later though, because whenever we do change this requirements.txt, this will be one of the first steps up here. So this means that all the steps after those will be invalidated, and then they will have to be recached and rerun. Doesn't take so long though, so it's fine for now. The next thing I would like to do is to create a class for loading the dataset. So I would like to say class ESC50 and then dataset. And I would like to inherit from this dataset right here, which is from PyTorch. So I should be able to get this from up here. If I go ahead and say from torch.utils. And then I think it's data import data loader like this, dataset like that. Then we should be able to create this dataset class, and then what the purpose of this dataset class even is that we can automatically get items from the dataset, and it'll then go into the file, find the file, so both the feature and the label. It'll then make sure that the feature, so the file is converted to a Mel Spectrogram like we expect it to be, and then we do not have to do any of this ourselves wherever we want to use one of the samples from the dataset. So that is really why we create this dataset class, just to load the dataset and then also to be able to get items from the dataset in a pretty quick manner. So whenever we create this class for the first time, we would like to load a couple of things into memory. So I would like to create a constructor for this. So I'll say def init, and then I would like to pass in the data directory to where the dataset is. I would like to also name the metadata file. So if we hop into the ESC dataset right here, we should be able to see both all of the audio files right here, all of the features, and then under meta, we should be able to, under CSV, see all of the different file names along with their different categories. So these are the labels. Another thing that's pretty important for you to know is this fold parameter right here. So as you see, we have about 2,000 items in the dataset. So scrolling all the way down, we have 2,000. And then for every 400, the fold changes one number up like this. And let me just find this. Yeah, about 400. And then at about 800, it changes again. Right here, from 2 to 3. So this means that the dataset is divided into 5 different parts, or 5 different folds as they call it. So if we want to follow, let me just go all the way over here. I'll just hop over to this place. If we want to follow this example right here, where we have 80% training data and 20% validation data, well then we can take the first 4 folds, because 4/5 is 80%. And make that the training data, and we can then take the last fold and make that the validation data. And then that should give us the 2 different data sets which we are looking for. Good. So now that we know how the data set is kind of structured, we can go ahead and adapt our code to actually get those files. So I would like to also be able to create 2 of these instances. I would like an instance for the training, and then I would like an instance for the validation. So this means that you can say the instance of this dot and then get an item, and then you will get out a sample from the validation dataset, or you can use the other instance to get out a sample from the validation dataset. So I'd like to put in split here and then say train, just so it's the default. And then I would like to pass in a transform as well. So a transform is something you can pass in that will do a transformation to the dataset. So how we load the dataset is going to look a little bit different when we do it for training versus when we do it for validation. So therefore we pass in this generic transform right here, which will then just be applied to the element which we are loading whenever we use this dataset class. Good. So the first instance variable we're going to set is going to be self.data_directory, and that'll be equal to path, which we can import, and then we'll pass in the data directory. So we'll say pathlib import path. Next, we can go ahead and define self.metadata. And this will need to read from the pandas library, because remember, this is a CSV file right here. So we'll just go ahead and import pandas. So first of all, I'll put it into the requirements, pandas. And then what I would like to do is just open up the terminal and say pip install pandas. So pandas is just a library for handling CSV files and all kinds of numbers. So now we should be able to import pandas as PD. So I can say import pandas as PD, like that. And then down here, we should be able to say pd.readCSV and then pass in the metadata file, because then this is pointing to a CSV file, and this readCSV is accepting a path object. A path instance. Lastly, we can say self.split, just so we store this somewhere so it isn't lost whenever we exit the constructor. Then we say is equal to split, and we can say self.transform is equal to the transform if it does exist. So the next thing we can do is actually filter the training data and the validation data depending on whether we have the split variable set to train or set to validation. So first I'll say if split is equal to train. In that case, I would like to redefine self.metadata to filter away all of the different folds that we do not want for the training data. So because we're using the 4 first folds, so 80% of the data for the training data, we'll filter out any fold that is that has the value 5. So we'll go ahead and say self.metadata is equal to self.metadata. And then I would like to do something called a Boolean series. So we can say self.metadata, and then we can pass in fold is not equal to 5. So what this does is that it'll check for all of the fold columns, it'll check all the rows for the fold columns, and all the ones that aren't 5 will be set to true, and all the ones that are 5 will be set to false. And because we have wrapped this statement inside the braces right here, we'll then filter out all the different rows where the condition is true. We'll select all the rows where the condition is true and filter out all the different rows where the condition is false. So basically, we'll end up with all the different rows where the fold is not 5. And then for the validation dataset, because we want the rest of the data, we of course just want to do the opposite. So I'll just say else here, and then copy this line down. So self.metadata, and then I'll say is equal to 5 instead. Next up, I would like to find out what all of these different categories are. So for example, we have vacuum cleaner, chirping birds, dog, etc. But we do also have a lot of duplicates in this list of rows, because obviously we have way more rows than we have categories. So I would like to find all the different unique category names, just so we have a list of the different classes which we should be able to classify audio files as. So what I'll do to do this is I'll hop down and say self.classes is equal to, and then I can say sorted. I can then say self.metadata. I can get the category, and I can say, category right here, and I can say unique. Good. So over here we can see that this was called category. So I just grab the following column for all different rows, and then I say .unique, and .unique just makes sure that if we have duplicates, so we have 2 vacuum cleaners right here and 2 thunderstorms, then we'll only keep 1 of each class, and then we put it inside this sorted right here. So as you can see, it will return a new list containing all elements from the iterable in ascending order. So now we have a list of all the different classes which we can classify it as. Then I would like to assign a specific integer for each different class. So right now each class is basically just a word, so just a string, sorry. So we just have vacuum cleaner, but it doesn't really have any numbers, which is what we usually work with computers. So what I would like to do is say self.class class to idx is equal to, and I'll say CLS for class idx for idx class in enumerate. This is IDX right there. In enumerate, and then I'll say self.classes like this. Good. So this will give us a unique number for every single class that we just found up here. So basically we have, for example, dog, 0, rain, 1, etc. for all the different classes. And now I would like to take this number and then add it to the actual metadata, because right now I would like to also give each row a new column that says label, and this label should then contain the number for the actual category instead of just a string like it is right now. So we'll take the data frame which we got from up here, this metadata, that is a data frame, and then we can say self.metadata. We'll add a new label, new column called label. This will be equal to self.metadata, and we would like to say category, and then we'll say .map, and I'll then just pass in self.class to IDX. So what we basically do is that we loop through all these different rows with this map function right here, and then for each of the categories we can use this mapping table which we just created. So for example, if we in the mapping table can see that dog has the number 0, well then this will yield 0, and 0 will be inserted into the column label, the label column for that specific row. So that is the constructor of this dataset class. Next I would like to define another function called len. So for example, if you say class instance, that is, if I have a class instance of this class right here, if we put in len, if we wrap it around an len, then what is returned by this len function is what is defined within the function right here. So we basically just override the default len function. And the way we're going to do this is by saying self right here, and then we can just return the length of, return the length of the metadata class, self.metadata right here. So if you were to use length, so if you were to create an instance of this class right here and then wrap it around length, well, how is the class supposed to know that it is metadata that we want the length of and not split or transform, etc.? It doesn't really know that, and that is why we override this length function with the following logic right here. Good. So the next thing I would like to do is to create a function that makes us able to extract samples from the dataset very quickly. So we can go ahead and define this get item, override that one as well, where we pass in self and IDX. So IDX is going to be the ID of the element which we're interested in. So what we're overriding here is basically if we say class is equal to ESC 50 dataset, etc. Then if we say class 0, then this right here will then index into something inside the class, and what it indexes into is what we define right here in the get item. So obviously we would like to first of all get the metadata, so the label. We would like to also get the feature, so the audio file. It should also be converted to a Mel Spectrogram instead of just being the raw waveform. So these are some of the problems that we'll handle inside this get item right here. First though, I would like to get the row, the specific row. So if you say index 0 for example, we'll get this row out, and we'll get this from the metadata. So I would like to say row is equal to self.metadata.ILOC. So this allows us to do selection within this data frame with an integer as the index. So we can then pass in the IDX like this, and I think we might want to pass it in like this actually. Then we can say the audio path, and the audio path is going to be equal to self.data directory. So that is the directory that points to the audio file right here, or at least the audio file in our local system. And then this is going to be the first part of the path. We'll then also have /audio, and we'll have /row, and then file name like this. So what this will evaluate to is something like data directory /audio / and then for example, if we were interested in the following file right here, if we put in the index 204 or something, then we would get out a file that looks like this. So this way we can actually get the audio file out. Good. So now that we have the audio path, we can go ahead and load out the audio. So we'll say torch audio, and this will just need to actually install. So I'll just open up the terminal again, right here. And then we can go ahead and say pip install torch audio. Oh, I think I put in a P, torch audio like that. And then just put the same into the requirements, because the same will be running on the cloud. So torch audio. Then we can go ahead and import torch audio now. Say torch audio dot load. And then we'll load the audio file from the audio path, which we just constructed up here. Good. So we'll just need to destructure the output from this to waveform and sample rate, like this. So this will give us the waveform and also the sample rate, just the number, from the file that it just loaded right here. One thing we now need to take into account is that audio, so a WAV file, can be with multiple channels, and we only want to keep a single channel. So therefore I'll check for whether it's multiple channels or not. The shape of this waveform tensor right here is going to look something like this. We'll have the channels and we'll then have the samples. So in practice, this is going to look something like this. If we have multiple channels, then we'll have 2 right here, and then something like 44,000 blah blah samples. We want to reduce this down to a 0 and then take the mean between the left and the right channel. So therefore, if it is a 2-channel WAV file, we'll then reduce this down. So I'll say if, and then waveform dot shape 0 is more than 1. Then I would like to say waveform is equal to torch dot mean. We just need to import torch, and then we can take the mean where we pass in the waveform dim 0, and we can say keep dimension true. So dimension 0 right here is the channel dimension. So as I explained before, let me just do it again. As I explained before, if we have channel and then samples right here, then the channel dimension is obviously this one. So we want to go from 2 and then 44 something 1,000 samples, and then we want to go to a single channel by averaging these two, or taking the mean of these two channels. So the channel dimension is this one, and those are the 2 ones which we would like to take the mean of. And then the reason we put in this keep dimension flag is also because if we do not do that, it'll go from this, if there are 2 channels, to this, and we don't really want to do that. We would like to keep it as a 1 right here, just to keep it consistent. So that is basically what we do to transform from 2 to 1 channel. Lastly, we can take this transform, which we defined up here, and then we can apply that to the actual audio which we're trying to get with this get item right here. So I'll go ahead and say if self.transform, because remember it can't be none, so we just want to check if it is actually set or not. If it is set, we'll then say spectrogram is equal to self.transform, and we'll pass in the waveform. Then I can say else spectrogram is equal to the waveform. So if no transform is passed in, then we'll just set the spectrogram to the waveform that we already have. Then I can go ahead and return the feature, that is the spectrogram, and the label, which will be row, and then label like this. So basically, when you get an item, you get the feature, and then also the label returned, so a full sample. And remember, the reason we can just get the label right here is because we found the row as the first thing up here. So this would just get the specific row for us, and then the associated ID of the class, which is the true label of that feature. Now we can go ahead and use this dataset class, which we just created, to actually load in some data down here in the train function. So first of all, I would like to say esc50 directory is equal to a new path. So we will instantiate a new path object that points to opt esc50 data, which is where we download the data to up here whenever we build the Docker image, like that. Good. Before instantiating this class esc50 dataset, we can go ahead and define the transforms which will pass into the class right there. So we would like a transform both for training, but also a transform for validation. For training, I would like to say train transform is equal to neural network dot, We'll just need to import this. So I'll hop up and say import and then torch.neural network as neural network. Then we can say neural network.sequential, and we can pass in first of all t, which we'll just hop up and define as well. So we'll just say import torch audio dot transforms as t. So this just allows us to transform from the WAV files right here to Mel Spectrograms. So that is one of the transforms we would like to do. And then we'll say dot Mel Spectrogram. And then for the Mel Spectrogram, we'll need to set some parameters. We can put in a sample rate of 2250. We can also put in a window size. We can say NFFT. We can put in 1024. We can put in a hop length where we put in 512. We can put in a number of mels, which we'll just set to 128. We can put in an F minimum. And we can put in an F maximum, like this, which we'll set to 11,025. So these are just pretty standard Mel Spectrogram configuration values, which I just found from looking at someone else's code who had to convert from WAV to Mel Spectrograms themselves. So first of all, the WAV is turned into a Mel Spectrogram. One other thing that needs to happen is that we need to convert to decibels. So we can say amplitude to dB afterwards, to decibels. After this, we can say t.frequency masking, where we're going to put in frequency mask parameter of 30. After this, we can put in one more thing, t.time masking, where we'll set the time mask parameter to 80, like this. So just like we had the dropout earlier, let me just show you this. We had a dropout over here, and the dropout basically just changes things within the network such that the network will have a harder time just remembering instead of having to actually learn and be able to generalize, which will then prevent overfitting. So dropout was one technique of being able to do this. Another technique is these two, which we have applied right here, frequency masking and also time masking. So these are kind of like dropout, but just for audio. So for the frequency masking, for example, this will randomly mask frequency bins within the Mel Spectrogram. So it'll basically just pick a random frequency range and then set those bins to 0. And then by setting this frequency mask params, up to 30 of these bins can be set. And this will then help the network prevent overfitting because some of these are set to 0 sometimes. We also have this time masking right here, and it kind of does the same, but it just sets the time ranges to 0 instead of frequency bins up here. So this just prevents overfitting in another way, just by changing the time to 0 sometimes as well to prevent overfitting. And we obviously only want to keep these two things inside the training transform. So that is why we have a training transform, but also a validation transform, which we'll define in just a second. So what we're going to do for the validation transform is basically just to copy this, and then we'll remove what we don't really need for validation. So this is only really needed for training, because why would you ever mask your input for the model whenever you're doing the actual inference? You only want to do this with training to really make the model be able to better generalize. So now we have a validation and also a training transform, and then we can pass these into the instance, which we'll create up here. So let me just hop down here, and then I'll create a training dataset. And then I would like to say that is equal to ESC dataset. The data directory will be the ESC data directory. The metadata file is going to be the ESC directory. And then we'll append meta to that. And we'll append ESC50.csv to that. So going over here to the GitHub, we can see that this meta file is inside the root directory /meta/esc50.csv. So that's where I'm getting this from. Good. Now I also want to put in a couple more things. I'll put in split is equal to train for the training dataset, and I'll put in the transform, which is going to be the train transform. Then what I can do is just copy this entire thing down, call this the test dataset right here, or just the validation dataset actually. And then we'll just pass in this validation transform instead, and call this validation instead of train. We can then just test this out actually. So we can go ahead and say print, and then I'll say training samples, and this will then be plus length of the training dataset, and then we'll do the same just with the validation dataset, and then we'll call this validation samples. And now we should be able to open up the terminal, say modal run, and then train.py, and then we can see if it actually works as it is supposed to. Because remember, we did some overriding of this length function right here up in the dataset, so we should be able to see this kick in, and then it should work fine. Remember, we did change a couple of things inside of the requirements here. We changed both pandas and also torch audio. We also imported torch actually. So what I'll do is I'll just take this torch, put it into the requirements as well. And then let me just see if there's anything else. I think that should be it for now. Good. I'm then just going to cancel this run right here. And then I'll just create a new one by saying modal run train.py, because we did just add torch as well, just to make sure it doesn't fail. So I'll just go ahead and run this again with the new requirements.txt and wait for this to finish. And it has been running for a minute or so, and now it just finished, so it can really concatenate an integer with a string, which totally makes sense. So what I'll do is I'll just need to scroll down to where we do this and make this a formatted string instead. So maybe you already caught this error and fixed it, but this is what you gotta do. Gotta put it into the string like this, and then make the string formatted. Good. So we'll just need to put in a start curly brace, run it again, and then this should be super quick this time because it already cached the things that we installed from the requirements.txt. So this should only take a couple of seconds. So we now see the validation samples 400, training samples is 1600. So this means that 80% of the data will be training samples. So that is exactly what we actually wanted. Then we can create two data loaders to actually loop through the different data and then run that data through the network. This means that instead of having to manually go ahead and get the data out of these datasets, we can use a data loader to get them out in batches, and these batches can then be run through the neural network to train it and also to test it out with the validation dataset right here. So what we'll do is say train data loader is equal to a data loader, which we'll just need to import. So I think we'll need to search for this. I think it comes from up next to the dataset right there. Good. So now down here at the data loader, we can say data loader, and then we'll pass in the train dataset. We would like to define that we want a batch size of 32. So this means we'll put in 32 samples into the network at a time, and we'll then also just set shuffle to true as well. So if you hover shuffle, it's just a boolean. But what it does is that it randomizes the order of samples in each epoch whenever you train the model. So for this should be fine. The next is going to be the test loader or the validation loader. So this will be data loader, and I'll put in the test or validation dataset. We'll just call this test from now on actually, because we use it to test the model. So I'll say test dataset, validation dataset right here, and then we'll put in a batch size of 32 as well. And I would like to set the shuffle to false. So we want to have shuffle be false for invalidation or test, because it will maintain the original dataset order. So the same sequence will be used every sequence. This also means that every time we test, we can then compare the test results to last time we did this test, because it is the same. Good. So now we can go ahead and actually initialize the model. So I'll say device first of all, to figure out what device we're on. We are obviously going to be on a GPU. It is just good practice to say device is equal to torch.device, and then we say CUDA if torch.CUDA is available. So CUDA is only available on GPUs. Otherwise, we'll set this to CPU, meaning that the model should be able to run on a CPU and theoretically. Then we can say model is equal to audio CNN, and we'll just need to import this from the other file which we created earlier. Then we can go ahead and pass in the number of classes. This will be equal to the length of train dataset dot classes like this. Then we can move the initialized model to the device, so we can move it from the CPU to the GPU if that is the case. So we'll say model.to, pass in the device, like that. Then what I would like to do is just define the amount of epochs it should run for. So I'll say number of epochs, and I would like to run it for 100 epochs. Then we can set up the loss function, which we'll call the criterion, like this. That'll be equal to neural network, and we'll just use a super simple cross entropy loss function, which is the default for most neural networks, which will train that out this simple. Then we'll put in label smoothing and set this to 0.1 like this. What this label smoothing does is that it forces the model to be more humble in its predictions, so be less certain in certain predictions. So for example, our dataset might look something like this, or a sample from the dataset might look something like this. So let's say we have 5 different classes in our dataset, and then one of these is correct for this specific sample. The first one is correct, then all the other ones will be set to 0 like this. And this is then normally what is used when training the model. And because this is set to 1 and all of these are set to 0, this will then train the model to think that it is correct to output as high of a number as possible for the prediction that it thinks is correct. Instead of doing this, we can use something called label smoothing. So for our training data, it will take this one and then it'll make it a little bit smaller, but then distribute the rest of these numbers, the rest of the number out to the other different options. So for example, if we set label smoothing to 0.1, well, then this might be 0.9, and then the rest, so the 0.1 will be divided into the other categories. This means we would get 0.25, 0.025, and then we would have 0.025, 0.025, etc. for the rest of the categories. This would then make the model less confident in its predictions, because instead of now thinking that 1 is the only correct answer, 0.9 is a little bit lower, and then it forces the model to also consider these other options because they are a little bit more correct than they were with this harsh truth over here. And the reason that this label smoothing is passed into the loss function specifically is because these smoothed labels over here are used in the loss function, which will then make the model learn to have more reasonable predictions. So we won't really change what the model predicts. We'll just change what the model is fed, like the data it is fed basically, and make the data more reasonable to hopefully also teach the model more reasonable predictions. So this was the loss function, which will then determine how wrong the model is whenever it does a prediction. The next thing we're going to define is going to be the optimizer. So I'll say optimizer is going to be equal to optim, which we'll just need to import as well. So we can just scroll all the way up to torch, and then we can say import and then torch.optimizer s optimizer like this. Scroll back down, and then we should be able to use the atom w optimizer like that. And for the optimizer, we'll need to pass in the model.parameters, because remember, the optimizer's job is to tune the weights and the biases of the entire model, aka the parameters of the model, to then make them better so the loss is decreased as much as possible. So we pass in the model parameters. We then also pass in the learning rate, so how confident the model is, how confident the optimizer should be whenever it makes changes to the model. So we'll set it to 0.05, and we can then also set a weight decay, which we'll set to 0.01. So remember back to the theory where we talked about the learning rate. Well, if you have forgotten already, the learning rate is controlling how fast the model learns. So if we set this learning rate too high, we'll then have some pretty big steps whenever we change the weights and the biases. So this will do something like, it will cause unstable training basically, where it can overshoot the optimal values. But if we set this too low as well, then the training is going to be super slow and might take a long time. So this is just a value that I found online that other people have trained a similar model with. So you can only really figure this out by looking at how other people have set the learning rate, or by just trialing your way forth, just by testing different values basically. Then we also have this weight decay parameter over here, which is a parameter you can put in to try and prevent overfitting by penalizing large weights. So it basically just encourages the weights in the model to stay small, because large weights can apparently cause the model to become overfit because it remembers the input data more, and that is the sign of overfitting basically. So these are the parameters which we are going to input for the optimizer. And that should be that for the optimizer, which we can then use in just a second. Next, we're going to implement a scheduler, and a scheduler is something that adjusts the learning rate during training so the model can just learn more effectively, basically. The scheduler is created from the optimizer because the scheduler needs access to the optimizer such that it can modify the optimizer's learning rate during the training. So to create this, we'll go down and then we'll say scheduler is equal to, and then we'll say 1 cycle learning rate like this. And then we'll just need to go ahead and import this scheduler up here. So let me just scroll all the way up. And then we should be able to import it like this. So I'll say from torch.optimizer dot, and then we can go ahead and say learning rate scheduler import, and then we can say 1 cycle learning rate like this. Let me just find where that is. It is down here. And then for the first parameter, we can go ahead and pass in the optimizer, because remember, the scheduler will need to change the learning rate within the optimizer, and the learning rate for the optimizer is set right here. So this is right here is what is going to be changed. And then for this 1 cycle learning rate scheduler right here, it is going to start with a low learning rate, and then it is going to increase the learning rate to a maximum. So we can go ahead and set the max learning rate. So I'll go ahead and say max learning rate, and we'll do 0.002. So this is 0.0005, and we'll increase it by a factor of 10-fold, a factor of 10x, such that the optimizer becomes way more confident in its predictions later on during the training process. So now we can go ahead and say epochs, and then we'll put in the number of epochs like this. Under this, we'll put in steps per epoch, which is another parameter. And we'll put in the length of the training loader right here, like this. So the parameter will tell us how many, or tell the 1 cycle learning rate, how many optimizer steps happen per epoch. So this will help the model learn quickly at first, and then fine tune more carefully later. And the length of the training data loader right here is going to give us the number of batches in 1 epoch, which also corresponds to the number of optimizer steps per epoch, because 1 optimizer step is going to happen per batch during the training. Lastly, we can put in %start like this. We'll set this to 0.1, and what this means is that it'll spend 10% of training increasing the learning rate, while spending 90% of the training decreasing the learning rate. So actually this 1 cycle learning rate class right here overrides the learning rate initially set right here within the optimizer. So even though we have set 0.0005, the scheduler is going to ignore that and then start with the value that is much lower, so something close to 0. And then it is going to spend 10% of training increasing this from around 0 and then all the way up to the max learning rate right here. Then it is going to spend the rest of the 90% of the training decreasing it from the max learning rate right here, and then all the way down to something close to 0 again. So the scheduler actually creates its own learning rate curve that goes from really low, close to 0, up to the max learning rate, and then close down to 0 again. So this up here is actually ignored, now that I remember it, by the 1 cycle learning rate right here. Now we are able to loop through the different epochs whenever we do the train, and then start actually following the training process. So first I would like to create a variable called best accuracy. So best accuracy is a variable that holds the best accuracy value so far during training, such that we can figure out if the current iteration or the current epoch has to have done better than any of the last epochs, and then if that is the case, we then save the model. This means that we only save the best model files, so if we get an epoch that does even worse than the last one, we won't save the model file. So we'll just set this to 0.0, and then we would like to print out starting training. Good. Then we would like to say for epoch in range number of epochs, like this. Good. In here, we would like to first set the model to training mode. So we can go ahead and say model.train. And the reason we set the model to training mode is because if we hop into the model.py, remember how we create this dropout layer, for example? So up here, this dropout layer should only be used during training, and this will then zero out or drop specific neurons during the forward pass. This obviously shouldn't be done for inference mode, but only for the training mode. So setting the model to training mode is going to activate this layer right here. Another thing that is going to be activated as well is these batch norm 2D layers. So by setting the model to training mode, the batch norm 2D will update their running statistics and then use the batch statistics for normalization during the training process, and that should not happen during the inference mode. We can then just hop back into the train.py over here, and then we can continue on. I would like to define a variable called epoch loss and set this to 0.0. So this epoch loss is the accumulated loss calculated batch by batch, because we can't really compute the loss for the entire epoch at once due to something like memory limitations, for example. So what we do is that we add up all the different batch losses to then get the total loss for the epoch. That is then going to be stored within this epoch loss variable right here. If we then divide this variable by the number of epochs, we get the average loss of the epoch based on, the average loss of a batch, because we'll just take the average of all the different losses in all the different batches in this epoch. We can then loop through all the different batches in the training dataset to do the actual training. First of all, I would like to install a library which we can use to visualize this with a progress bar. So I'll go ahead and say pip install tqdm, and then we'll also just take this and add it to the requirements.txt down here and just save that. And this should allow us to show a show a progress bar whenever we do the actual training. This progress bar is going to be shown in the terminal, and it's going to be created in a way that is compatible with text. So first we'll define the progress bar. We'll say progress bar is equal to tqdm, and then we'll just need to import tqdm like this. And if I go up, we just need to say from tqdm import tqdm like that. And then going all the way back down, we can now inside tqdm open it up. Then we can pass in the train data loader like this, and then also the description that is going to be shown in the bar as well. So I would like to put in description like this. Then we can put in a formatted string that says epoch, and then the number of epochs, epoch plus 1. Right after, we're going to show a / like this, and then we'll say out of number of epochs like that. So this is just going to loop through all the different batches in the training loader, and then it's going to show a progress bar in the terminal with the following description next to it. Now we can say for data target in progress bar like this. So this means we'll loop across this data right here, but then because we loop across the progress bar and the progress bar is initialized with this data, the progress bar is going to be shown and we'll be able to loop through the data just like normal. Good. So now we can say data target is equal to data.to, and we'll just move it to the device, and then we'll just do the exact same for the target.to device. This means that if the data or target was on the CPU, but we have a GPU available, we'll just move those to the GPU, otherwise they're going to stay on the CPU as they should. Good. And in case you're wondering what the data and the target is, well, this training data loader is going to return a batch at a time every time we iterate through this. The data is going to be the batch size of, it's going to be the spectrograms, and this is going to be the labels for the spectrograms. And these will each come in the batch size. So if you have a batch size of 32, for example, we're going to get 32 spectrograms right here. We're going to get 32 labels, one for each spectrogram right here in the target. The next thing I would like to implement is a technique for making the model smarter, and this is called data mixing. So in simple terms, this technique helps us create a new training data by mixing existing sounds, so we blend them together basically. So for example, we can take a dog bark sound and then also a car horn sound, and then we can combine these two sounds, so basically we merge them into a single sound. And then we train the model on this merged sound. And this has a couple of benefits. So first of all, instead of just memorizing what a perfect dog bark is from this example, it will be better at just learning the essence of a dog bark. So for example, if we have the dog bark and then the car horn mixed together as one sound, the model will need to work even harder to extract the dog sound parts of that merged audio, meaning it'll be better at detecting dog barks in the future. Also, in the real world, sounds often aren't as isolated as they are in training data, such as the training data we're working with, because the training data we're working with is pretty high quality, but in the real world, sounds are often mixed together. So by training the model to actually extract audio from these mixed audio samples, the model will be even better for working with real world data as well. Second of all, it also makes the model less overconfident, because instead of giving the dog only a dog sound, for example, then the dog will know that that is specifically a dog sound. We'll teach the model to say that, okay, for example, I'm 80% sure that this is a dog sound, rather than teaching the model to say, okay, I'm 100% certain this is a dog sound. And preventing the model from being super overconfident, it can help make predictions both more realistic and also more reliable in general. Also, if we actually train the model on like strange mixed up data, which we'll create with these synthetic samples, it's also harder to fool the model. So basically the model just becomes more robust because it has seen more different things. And it doesn't really get thrown off as much by a little bit of background noise in the samples, which is basically what we'll do whenever we merge two things together. So for example, if we mix two samples together, like a dog sound and also a car horn, it might be 80% dog bark and then 20% car horn. So there will be kind of like a background sound in the audio clip, which is like the 20% car horn, for example. So this little background noise shouldn't really throw the model off, but if we do not do this data mixing, it might have a pretty big effect on the model performance because it hasn't really seen any audio samples with this background noise before. But because we do train the model on this background noise, the model should be good at recognizing that it is just background noise that should be filtered away and not really be given attention to. We'll start off implementing this method by hopping over here, over this train function, and then I would like to create a new function called mixup data, where we pass in x and also y. Inside here, we would like to first calculate something called the blending percentage. So for example, if this variable blending percentage is 0.7, that means that if we merge two audio clips, we'll use 70% of the first audio clip and then 30% of the next one. So I would like to go ahead and say lambda for the blending percentage. Then we can say numpy, which we'll just need to import. So import numpy, if it is not there, as np. And then in requirements, we'll just put in numpy as well. Then scrolling back down, we can say numpy.random.beta. So we'll create a beta distribution and we'll set these values to 0.2 and 0.2 for both A and B. X right here is going to be the features and Y is going to be the labels, so the two different inputs for the function. We can then go ahead and grab the actual batch size, and because we have the features right here, we can see the batch size from the first dimension in the tensor. So we'll go ahead and say batch size is equal to x.size 0. So we take the size of the first element in the tensor, so that is going to be the batch size. Cool. Then we can go ahead and say index is equal to torch.random permutation, like this. Then we can pass in the batch size, say .to x.device, like that. What this does is that it shuffles the batch of audio clips. So basically it's like taking a deck of cards or something and then shuffling them such that we can match these ones that are shuffled with the ones that are right here in the correct order, and then creates random pairs whenever we do mix the data. Next we can implement the logic that actually does the mixing. So this will create the new audio clips. So first I would like to say mixed x is going to be equal to lambda times x, and then we'll say plus 1 minus lambda times x index, and do this. So what this basically comes down to is linear interpolation. So basically if we have 0.7 times the original sound, times let me just do this as a comment, times audio 1, and then we multiply then we add this to 0.3 times audio 2. So this is basically what we're doing. We take 70% of the first audio clip and then we blend this together with the 30% of the second audio clip, and this will then create a new synthetic samples between two audio clips. So as you can see, this is going to be the first audio clip and this is going to be the second audio clip right here. Good. So that is basically what that does. Nice. After this, we can go ahead and create a new line, and then we can get the labels for the two original audio clips for the first one and also for the second one up here. So these should be the labels for the two ones that were mixed together. So I'll say YA for so Y is going to be label and X is going to be feature. So Y, the label of the first audio clip, and then we'll also say YB, so the label of the second one, is equal to Y and Y index, like that. So now we basically have the new blended audio in this variable. We have the two original labels, so the two original true predictions, and then we have a blending percentage between the two original, between the two different audio labels, audio features. So what I'll do is say return, and then I'll first return the feature, and then I would like to return YA and YB, and I would like to return the blending percentage. This right here allows us to be able to actually calculate the loss, so that is why we also return the original blending right here, also the original labels, as well as the blending percentage. Good. So now that we have this function created, we can go down to where we originally were, and then we can go ahead and use that. So I would like to, in 30% of all cases, apply this mixing whenever we run through the training loop. So I can say if numpy.random, call this function, is more than 0.7. So this random will return something between 0 and 1. And then if we are above 0.7, that means there is a 30% chance, because 1 minus 0.7 is equal to 0.3. If that is the case, then we would like to apply the mix-up. So we'll go ahead and say mix-up data, pass in the data and the target. So this is going to be the features and the labels. And then we'll have the return statements, then we'll have the variables returned, which we defined just a second ago. So we defined the data, the original label for audio 1, the original label for audio 2, and also the lambda, so the blending percentage. Then we can go ahead and run this mixed data through the model. So we'll say output is equal to model, and then data. This will run the data, the new synthetic data through the forward pass, which we defined in here within the model. So this one right there. Then after running it through the model, we can go ahead and calculate the loss. And the loss will need to be calculated a little bit differently whenever we do this data mix-up compared to whenever we do not do this, because we do blend together two audio data. We do blend together two audio files. Or it's not even two audio files, it is two spectrograms. So we'll need to take into account how big of a percentage each of these make up in this feature right here. And then also taking the original loss into account. So going up, we'll just create a function for that as well, right under this mix-up data. I would like to call this mix-up criterion. So there is a criterion function whenever you do these kinds of programs. And this criterion function is used to calculate the loss. So first we pass in the criterion. That is a function we can use to just calculate the loss given a prediction, and then the value that the prediction should be if it was true. Then we can pass in the actual prediction of the model. We can then pass in the true label for the first one, the true label for the second audio in the blended audio, and then also the blending percentage. Nice. Then we can return the actual loss. So I would like to calculate the loss first of all by finding the loss for the first one, and then we can multiply that by how big of a percentage it made up in the blend. And then we can add this to this exact same thing just for the second one, which is also multiplied by how big of a percentage that made up in the new blended audio. So first we can say blend percentage times, and then we can calculate the loss where we pass in the prediction and then YA. So this right here is going to calculate the loss of the prediction as if the sound was 100% the first sound in the blended audio right here. And we can then do the exact same thing, so we calculate the loss as if the sound was 100% the second audio right here. And then after doing those for each, we can then multiply the percentage that each one of these audio files made up in the blend. And this will give us a weighted average, just a weighted loss basically for both of these combined. So we take the first audio right here, multiply it by the blend. So this could be 70% of dog bark. And then we can multiply this to, then we can add this to 1 minus the blend percentage. Then we say criterion, prediction, and YB right here. So right here again, we calculate the error as if the sound was 100% dog bark. And then over here, we calculate the error as if the sound was 100% car horn. And then finally, by adding these two together, we'll combine those so it takes 70% of the dog bark error, and then we add this to 30% of the car horn error. This will then give us a fair score that reflects the mixed nature of the sound of the model that we tested on, so this synthetic audio which we created. And now we can actually go ahead and take this function, go down and calculate the loss from the output which we just created. So we'll call mix-up criterion, then we'll pass in the criterion right here. We'll say output, we'll say target A, we'll say target B, so the label of the second audio, and then we'll put in, pass in the blending percentage as well. And now we then have the loss right here of how well the model actually did. And as I explained before, the criterion is just what we call the loss function up here. So this cross-attribute loss right here is going to return the loss function, which we can use to calculate the loss, so how wrong the model is. Then in the cases that we do not use this data augmentation technique, we can say else. So if we are in the 70%, what we can then do is just calculate the output like normal. So we'll say output is equal to model, where we pass in the data that is not mixed, and we then calculate the loss by just running the prediction through the criterion, so the regular loss function, passing in the output and the target, so the feature and the label. So now we have the prediction of the model, and we can go ahead and say optimizer dot 0 grad. This will erase the gradients. So if you just hover here, it'll reset the gradients of all optimized torch.tensor.s. So it'll basically just erase the gradients from last run in this iteration right here, or last iteration, sorry. So we remove the old calculations from last iteration such that we can optimize the weights and biases and do the gradient calculations again from a clean slate. So we can say loss dot backward. Then we can say optimizer dot step, and we can say scheduler dot step as well. So for the second line over here, loss dot backwards, we have the loss which we calculated up here with the criterion, and the model will then be able to think backwards and then find the internal settings that were most responsible for the error. The optimizer.step down here is then going to update the model to become better. So based on what we learned in the previous step, the optimizer will then make a small adjustment to the model settings, so the weights and biases, such that the model becomes better and hopefully decreases the loss in future iterations. And as we went through as well before, the scheduler.step is just going to adjust the learning speed of how quickly the optimizer changes, or how big of a change the optimizer makes to the different weights and biases. So we start with bigger adjustments and then we make them smaller over time. We can then just keep the running total of mistakes, so the loss. So we'll just say epoch loss plus equals loss.item right here. So the epoch loss up here is going to be the average loss whenever we have finished all these different iterations. So we'll just keep a running loss of the mistakes during each iteration here. We can then also show the actual loss in the progress bar, which we displayed up here, this progress bar. So we can go ahead and say progress bar dot set postfix, and then we can put in the loss, put in a formatted string where I display the loss.item, and we'll then just format the decimals. So we'll say .4f like that. After looping through all the different iterations right here, we can then hop out of that loop when that is finished. And remember, this loop right here goes through all the different batches within the epoch that we're currently in. So for the epoch, we are now interested in calculating the epoch loss, so the average loss across every single batch in the epoch that we're currently in. So we'll do this down here, and we can do this by saying average epoch loss is equal to epoch loss divided by the length of the training loader. So that is going to be the amount of epochs. So we take the running average of losses, divide that by the amount of batches, and this gives us the average epoch loss, so the average loss per batch within this epoch. Every time we're done with an epoch as well, we'll also just test the trained model on the validation data. So up here, we set the model to training mode like this, where we enabled both the dropout but also the batch normalization layers. We'll just go ahead and set this to model.evaluation mode instead, just so we do not affect those two different layers. So what we'll do down here is just say model.evaluation, and then I'll just put in a comment that says validation after each epoch, just so we know why we're doing this. Good. Now we can say correct is equal to 0, total is equal to 0, and validation loss is equal to 0. Then we'll need to say with torch dot no grad, and what this no grad does is that it tells PyTorch not to touch neither the weights or the biases whenever we use the model within this Torch.NoGrad, because now we aren't really training the model in this step right here. We're just really testing out the model. So we don't really want to affect neither the weights or the biases. And also remember down here, we are going to work with the 20% validation data. So up here, we created two different loaders. We create the test of the train data loader with 80% of the data. We then also have the test data loader with, I'll just call this data loader, test data loader with 20% of the remaining data. And that is what we're going to validate the model with down here after each epoch, just so we can see if it is able to generalize what it learned within the epoch to data it has not seen before. And it hasn't really seen this validation data before, so that is why we use that instead of the testing data, instead of the training data. So we'll do the same thing as we did up here, where we loop through the features and labels from the data loader, but we'll just use the test instead of the train data loader. So first I'll say for data and target. So for the feature and label in test data loader, we'll then say data target is equal to data dot to device to transfer it to the GPU if that is the case, otherwise to the CPU, and we'll say target dot to device to also keep the labels right here on the device which we're working on. Then we can say outputs is equal to model data. So we take the data and then we pass it through a forward pass in the model which we just trained in the training step up here in a training mode. Then after doing that, we can say loss is equal to criterion. We pass in the data to calculate the loss. Then we can say validation loss is equal to, plus is equal to loss.item. So just like we were tracking a running loss up here, where we plus equal to the epoch loss up here, we'll do the exact same thing just for the validation down here, because remember, we're passing multiple batches in after each other. So we'll just do the exact same thing down here, where we track the loss each time, and then we divide it out at last to find the average loss in the validation step as well. We can now then find the model's best guess for each sound. So what we'll do is make this, which is just a throwaway variable, and then we'll also take predicted. That's going to be equal to torch.max. We'll put in outputs.data and set one as other right here. So remember that for each output neuron, and we'll have 50 output neurons because we have 50 different classes to pick between, the model is going to give a score for every possible class. So for example, all the different categories out here, we have dog, chirping birds, vacuum cleaner, etc. It'll give a score to, so dog might be 10% correct, chirping birds might be 50% correct if you put in a sound of chirping birds, vacuum cleaner might be 20%, etc. So we'll have a different percentage score for each of these different classes. And the model will look at all these different scores and pick the one with the highest number, and that will then become the model's final prediction, which will be stored right here in predicted. We will then keep track of how many sounds we have tested in total, so we keep track of a running total. So what we'll do is grab the batch size from the target, so we'll say total plus is equal to target.size 0. So we grab the batch size and then we add that to the total. So if we just tested a batch of 32 sounds, this line right here is going to add 32 to the total counter up here. And this will then help us keep track of how many sounds we have graded so far. Good. We can then say correct is equal to or plus equal to predicted. And then we say is equal to target dot sum dot item like this. So this will count how many guesses in this batch were correct. So basically it will compare the model's guesses, so predicted right here, with the total to the actual right answer, so that is target, and then it'll count up how many it got and then add that number to our correct score over here. What we'll then do is then calculate the final accuracy percentage. So we'll do this outside this Torch.NoGrad because we don't only need to be inside of that. We'll then say accuracy right here is equal to 100 times correct divided by total. And this is the total amount we've tested, how many is correct, and then we multiply by 100 to get it to be a percentage. We can then also find out the average mistake score. So we'll say average validation loss is equal to validation loss divided by the length of the test loader right there. So we do the exact same as we did further up right here whenever we calculated the average just for the epoch. Good. Then we can print out this information in the terminal, because remember, this entire script is going to be run as a service in the cloud on Modal. So we'll be able to follow along in the terminal when this is running to then see how the training is going. So we would like to print out some of this information just so we know how the training is going in case we want to stop it earlier, for example. So we can say print, put in a formatted string. I'll then put in epoch, put in epoch plus 1. I'll then say loss. I'll put in the average epoch loss, format that as well. So I'll say dot forf. I'll then put in the validation loss. That will be average validation loss. Format that as well. I'll then just put in the accuracy at last, and we'll just format that as well. Accuracy dot 2f, and then we'll say percentage because it is a percentage like we just determined, with times 100 up here as well. Good. Now we can save the best model, because as I explained earlier, up here we have the best accuracy, and this will keep track of the best accuracy which we have achieved so far throughout all the different epochs. And we only want to save the best model. So what I would like to do is just hop under this print statement, and then we'll say if the current accuracy of the current epoch is better than the best accuracy, so this is the best accuracy out of all the epochs we have run so far, we'll then just keep track of the new best accuracy. So the new best accuracy is going to be the same as the current accuracy, and then we'll also just save the model checkpoint. So we'll say torch.save, then we'll save the model state dictionary. So these are all the different weights and biases. This will be equal to model.stateDict like this. We'll then also save the accuracy like this, and then this will be equal to the accuracy. We'll save the epoch. That is going to be epoch like this. We'll then also save the classes, which will be equal to train dataset like this dot classes, and we'll just define where to save it to. So we can go ahead and put in /models/best model.pth, and then this /models up here is where we also attached the volume to. So remember, we have this model volume which we attach to the following path in the system or in the function which we're running, and this model volume up here will then be the one which will contain our best model file, and this is also what we can attach whenever we want to run inference, because this will then contain the best model file. So that is just so you know that as well. Nice. So going down, after having saved the best model file, we can go ahead and just print out and then a formatted string, new best model saved, and then we'll just put in the accuracy, just so that is, I'll just put in an F. I'll just save the accuracy as well, or print out the accuracy, just so that is clear whenever we do the training as well, and put in the percentage like that. And then whenever training is finished, and training is finished when we have ran through all the different epochs, so that should be at this level right here. So right outside the epoch loop, it'll be right there. We can then say print, and then a formatted string, training completed, and then best accuracy, and we'll then put in the accuracy, and then say .2f and percentage. And I think I'll just put in the best accuracy actually, because that is not correct, just put in the accuracy. Good. So this should then tell us when the training is finished as well. Now, one more thing I would like to do before we can start the training is set up something called Tensorboard. So if you just hop over to the browser here and search for Tensorboard, we'll just take a look at what it actually is. So right here is Tensorboard. So Tensorboard is a dashboard like this, and let me just refresh, that will allow us to track the accuracy and the loss of our trained model throughout the different epochs which we'll run. So this lets us log specific numbers such as the running loss or the running accuracy, as you see right here, and then show those as a graph instead of only looking at the numbers that are printed out in the terminal whenever we print out this or this or this for that sake. So it is very helpful, and it is great as also at also just understanding a little bit about how the model is performing, because you can really not imagine all these different numbers in your head if you have a lot of these, so it's way better to just look at a graph and then visualize it that way. So to get started with Tensorboard, it is pretty simple to set up. We'll need to, first of all, just go up to the train up here, the train function, and then I would like to import a couple of things. First of all, I'll just say from datetime, import the date time. This will allow us to create a unique file name that corresponds to the timestamp which we began the training within. So I'll go ahead and say timestamp, and by log I mean that whenever we write a log to the Tensorboard, we are going to write to a file, and this log file will then be named something in the names of the timestamp in which we start the training. So we can go ahead and say is equal to datetime.now to get the current timestamp whenever the training function began. Then we can say string format time, and we'll then like to format it as, let me put in a percentage sign, the year, another percentage sign like this. We'll then put in the month, another percentage sign, we'll put in the day, and we'll then do an underscore. We'll put in one more percentage sign like that, put in hour in uppercase, put in one more, minute, put in one more, and then seconds. So this is going to be the final timestamp or final string where the date will be formatted into, which date will be formatted as. So year, month, day, hour, minute, seconds. Good. We can then just create the log directory. So that is where we're going to save our Tensorboard file to. This is going to be a formatted string which will be saved under models. And then we'll save it under Tensorboard logs. So there's just a directory filled with log files. And we'll then just call this run. And then we'll put in the timestamp like that. And that should then be the file name which we saved the Tensorboard to. Or I mean the Tensorboard log file. We can then just go ahead and say writer is equal to. And now we'll just need to import an actual Tensorboard writer. So if we hop up here and then we search for from, and then we say torch.utils.tensorboard import summary writer like that. We should then be able to, let me just scroll down, say summary writer. So we instantiate a new of these summary writers. And we then just pass in the log directory right here where we write to. So we can then use this writer right here to log to the following directory. We can start by logging the training loss and also the learning rate over time. So if you hop down to the average epoch loss down here, that is going to be the loss that we calculate for each epoch whenever we do a training run. What we then do is say writer.add scalar. So a scalar is just a single numerical value which we want to track over time. So this could be the training loss, for example. So if we want to log the training loss, we'll log it under the name loss/train. And then the number we would like to log is going to be the average epoch loss. And we'll then also log the epoch. So this is going to be the y-axis and this is going to be the x-axis whenever we see the finished plot in the Tensorboard dashboard. We can then do the same just for the learning rate, because remember, we're using a scheduler to actually change the learning rate dynamically as the training progresses. So right here, we'll call this learning underscore rates. I would like to put in the optimizer like this, then say .parent group like this. We can then say 0 and we can say learning rates, and the epoch should just be the same because it changes per epoch. Then I'll just take these two lines right here, copy them down to under the average validation loss. And then in here we can say loss validation. We'll log the average validation loss. And then instead of, let me just copy this line and remove this one. We'll then also track the accuracy and call this validation. And this will then be the accuracy right here. Then what we need to do whenever the training is finished is just to close down this writer. So down here, whenever training is completed, right before that, we'll go ahead and put in writer.close like this. And this should then close down the writer. So remember, if we just take writer up here, the basic flow is that whenever we start the training, we create a new log file under this directory right here that is named by the date that we're currently at and also the timestamp where the training started. We then create a new writer from Tensorboard. And then every time we want to track a specific number, which we can plot in the Tensorboard dashboard, we'll add that number under a specific name. So loss train, for example, where we'll just add a single number So we add the number, which is the y value for the sample, and then we add the x-axis, or sorry, the x for the sample. So this is going to be the epoch in this case, and then we do this for all of the different numbers we want to track. So these two, and then also the accuracy and also the validation loss down here. And then lastly, we close down the writer such that the file is going to be saved. And then when we open up a Tensorboard server, so just a local server, we can then open up the log file, which we created whenever we say writer.close. And this is then something we can do whenever training has stopped. Good, so the training script is already set up to actually work right here. We have train.remote. That should be able to just start up this function, called the function, and then start the training. So let's just see if it actually works. I know we have changed some of these requirements, so these should reinstall because they're all the way up in the top of this pipeline right here. They are right there. So all of these things should then be redone, so the cache will be invalidated. So it might take a little bit of time for this to start, but we can just test it out if it actually works or not. So if we go under terminal, open an integrated terminal, put in modal run train.py, and then we can try and run that and just see what happens. So it says no module named Tensorboard. So I'll just go ahead and go to requirements, put in Tensorboard, also say pip install Tensorboard locally, just so we have it in case we need it for the API. Then we can just go ahead and say modal run train.py again. And then hopefully we should have the pip packages that we need. This will just run for a second. In the meantime, I'll just go ahead and hop into modal. And then as you can see under apps, we should probably be able to see under apps, we can see the audio CNN right here, which we just started. And this just needs to build, and then it'll start up an app function. And then under storage, we can see the two different volumes. We have the data, which contains the dataset. And then we have the ESC model, which should contain the model file that is going to be saved whenever a best checkpoint is created. Good, so I'll just hop back to apps and then hop over here and just wait for this to finish, or at least finish building this Docker image, just so we can see what happens and if the training starts as we expect it to. So the first error we're getting is the following one, which is a runtime error. So we have two tensors that does not match, and it's something about the convolutional layers. If we scroll up to right here, model.py, we can check out what it actually is. So first of all, it's line 25, and then we're passing x to the convolutional layer right here. This should actually not be x, it should be out, like this, so that will fix that error. Next up, the stride should not be applied up here for the second convolutional layer, so I'll just go ahead and remove that. The stride should also be determined automatically down here. So right now we do not pass any stride into the residual block like we're able to right here. So we of course want to do that. So after the following statement right here, 28, we would like to put in stride is equal to 2 if I is equal to 0. Else we'll set the stride to 1. And we'll just take this right here and copy it down to right there as well. And we'll copy it down to right here as well. And we're actually also redefining layer 3 right here. You see how we redefine it twice. This should be layer 4. And then down here, we do have layer 4 referenced correctly. So that would have given an error as well. Then I'll just hop into train.py. And then another thing I found also is that when we instantiate the dataset, I just want to call this split test as well. So I'll say test instead of validation, VAL. And then another thing is that down whenever we calculate the loss, let me just scroll down to this criterion right here. So as you see, whenever we do the training loss, we calculate the loss where we put in the features and also the labels. But going down here, whenever we calculate the loss for evaluation mode, we only pass in the data right here, so the input data. And that is obviously completely wrong. So we need to actually put in the outputs and then also the target like that, so we can calculate it correctly. This was just a spelling mistake on my end. Now we should then be able to run the script again because we fixed all these small bugs, and then we can see if we get any more errors or if it works this time. It should be a little bit quicker this time because all these will not have to run because we already did this once. So let me just return whenever this is done so we can see if any output that we expect comes out. Actually, we can already see that we have training samples 1600, validation samples 400, and then the training is starting. Then we can see the different epochs and we can see the progress of each epoch. The reason we can see this progress bar is because down here we have TQDM. So we can see the epoch, as we say in the description. We can then see the epoch out of the total amount of epochs. So that is what we print out right here. So that is the power of having a progress bar like this. It really just makes the entire training process a little bit more visual, which is very nice. So this was the first epoch that finished right here. So now all the batches has been run through the entire model once. And then validation was run, and then we can see the validation loss down here. So we have the loss, the validation loss, and we have the accuracy of the trained model. And then because this is the first epoch that we run, it is going to save this as the new best model, and then it is going to do the second epoch. So it'll do this for maybe half an hour to an hour, and then it should finish up, and then I'll catch you when that is done. As we can see, training just finished. It took about 40 minutes, and the best accuracy was 83%, but the last epoch had an accuracy of 82.75%. Good. So now we can scroll up and just see what actually happened. So through all of these different epochs, we can see that validation was done every single time. And then if we go even further up, we can see that accuracy jumps up and down and up and down. And that is because the learning rate sometimes overshoot the optimal values for the weights and biases, meaning that the loss sometimes goes down even though more epochs are run. Good. So as you can see, it goes up and down, but then all the way down here at the end, it stops at about 82.75%. We should also be able to hop into the modal dashboard here. We can see the app just stopped as well. And then we can go into storage, and then under the dataset, I can see that the folder is empty. So if you just hop into the code again and then go back, I think I know why. So I've probably made a little mistake in the beginning of the video. So we create this volume right called ESC50 data to store the actual dataset such that you can mount this, and then it will contain the dataset. And then this specific volume right here is then mounted to the following path /data. This means that the data must be placed within the dataset for the data to be persisted within the volume. But up here, whenever I check out the run commands, it downloads the dataset, unzips it, then creates a new directory under this folder right here. Then it copies all the files from the dataset into this new folder, and then it removes the old zip file and the leftover files. So the dataset is actually stored in the following directory right here, and not in the /dataset as we would expect. This then just means that the dataset is not stored within this image right here, but it's rather baked into the image and part of the image from when it was built. This doesn't really matter much though, because the dataset was downloaded in build time, so we can just go ahead and just ignore this because the training worked out just fine anyways. Good. So if we hop under the ESC model instead, that is where we save the best model file. So we have the best model.pth right here, and then we have the Tensorboard logs right here as well. As you can see, we have two runs. We have the first run that failed, that is this one, and then we had another run right here that succeeded. Inside this one, we'll have a file that is going to be the file for the Tensorboard, and we can then go ahead and download this file down to our local computer to display the loss and also the accuracy in a nice graph. To do this, we'll first of all open up a new tab, then we'll search for modal volume download, because we can use the terminal with the modal CLI to actually download this file down to our computer and then show it locally. So I'll just go ahead and find modal volume get, that is right there. And then we can see we need to pass in modal volume get along with the volume name. So we'll start by doing that. Open in Integrate Terminal, modal volume get. The volume name is going to be called, let me just find that, ESC model. So we'll just pass that in as the next argument, and the argument coming after that is then going to be something like the specific files. So we have the following folder right here. So if I just open up this again, then we should be able to just take the path. I think I'll just take the path with the Tensorboard logs like this, copy that entire thing, and then paste it in as the next command, and then press enter. And then this should be downloaded down to our local computer. And as we now see, we have this folder Tensorboard logs, which shows us these two files that was in the server just a second ago. Then to open up Tensorboard, we can go ahead and head to the terminal, put in Tensorboard --log directory, and then we'll put in /, and I would like to put in the newest one, so that is going to be the training run right here. So we'll have something like, let me just take this and see if I can copy the relative path. So it's going to be something like Tensorboard logs / and then the run, and this will then point to the specific run folder. So let me just try and run this, and then open up the following URL. So I'll just paste this in right here, and then zoom in a little bit. Good. So we have the accuracy / validation right here. So that goes up over time, just as we would expect, and we end up at around 83%. Good. And then we also have the learning rate, and as you see, it goes up a lot in the start, and then it slowly goes down as training progresses all the way up until the 100th epoch. And the reason the learning rate goes up and then down is because of the learning rate scheduler, so the one cycle learning rate, which we use to modify this. Good. So now let's take a look at the next graph. So if I open up loss right here, we should be able to see the training and also the validation loss. So as we can see, the training loss and also the validation loss both goes down over time. The validation loss has had some ups and downs right here in the beginning, but they seem to smooth out later on as the epochs went on. They also seem to go down at about the same rate. So if we take this and compare this to the Excalibur drawing from earlier, so if I just scroll over to where we talked about training AI models, that is down here, we should then be able to see that this is probably a good fit because both of the graphs go down at about the same rate. We don't see this problem with overfitting where the training loss goes down but the validation loss goes up, and we also don't see that they only go down just a little bit. If I just hop back into this, we can see that both go down to below 1, so they continue all the way down, and they also follow each other, so it seems to be a good fit for the model. Great, so now you know how to use Tensorboard as well, and then if you create another one, run for example, you'll then just have another folder right here called run, and then your timestamp, which you'll then be able to download down with the method I just showed you, and then open up to see how training went. Good, so now we actually both have the trained model, and we also know that it is correct. So we'll then be able to go ahead and create the inference endpoints. So hopping into this ESC model, we can see under right here that we'll need to reference the following file right here and load that into the memory whenever we want to run inference with the model. Luckily, we have this stored within a modal volume, so we can just take this volume and attach it to the new endpoint, and then the file will be available for us under the following folder right here, or at least within the folder that this volume attaches to in our function. To get started with the inference endpoint, we'll create a new file called main.py. In here, I would like to do a couple of things. First, I'll import modal. So I'll say import modal. Then we can go ahead and create a new app. App is equal to modal.app. The app should be called, and let me just check what we call the training app up here, Audio CNN. I'll just call this Audio CNN Inference. We can then define the image. The image should be modal.image.debianslim, so that is what we'll build the Docker image from. We can then say .pip install from requirements, like this, and then we can specify requirements.txt. After this, we'll say .add local Python source, and we would like to include this model file again, so the following one right here, such that that is available for import whenever we do need that. Then we also need to just specify fast API in here. So we'll just put in fast API because we'll need that for the endpoint which we'll create, and then also another library called librosa. So I'll say librosa as well, and that is for changing the sample rate in an audio file. Then I would like to define the same volume which we created in here, so that's going to be the model volume. And it already exists because otherwise we would get an error with inference. So I'll go ahead and remove this right there. And then we can create a class called audio processor that it takes in some audio and then it runs it through a transformation to a Mel Spectrogram. So in this class, we'll first put in a constructor, so def init, and we'll then say self. In here, we'll put in a self.transform. This transform is going to be equal to neural network, and we'll just need to import that the same way we did up here, right there. So I'll import that as well. We can then say neural network.sequential, and I would like to then put in t dot, and we'll need to just import t as well, like this. We can then say t dot Mel Spectrogram, and we have already defined how this Mel Spectrogram transform works. So we'll just go ahead and actually use the same one, so as we did down here. we can take this entire thing and we can paste it in right there. We can then just define a method on the class called process audio chunk. This should take self and audio data. What we'll then do with this raw audio data is convert this into something that the model understands, so just the basic model input format, which we also used whenever we fed something into the model for training or for validation. So first we'll convert it to a torch tensor. I'll say waveform is equal to torch.from numpy, and we'll just need to import torch up here. And then from numpy we can go ahead and say audio data, and we can say dot floats. This transform up here, this Mel Spectrogram transform, also expects the data to contain a channel dimension in the tensor. So we'll just go ahead and add a channel dimension. So I'll say waveform is equal to waveform.onSqueeze. Right there, 0. This will then add another channel or another dimension to the tensor, which is going to correspond to the channel dimension. Good. We can then just go ahead and say spectrogram is equal to self.transform, and we'll then transform from waveform to spectrogram, and we can then add a batch dimension to that spectrogram tensor. So we'll say return spectrogram.onSqueeze, like this. It's just going to be the exact same on squeeze as right there, and then 0. So the same way that we fed tensors with the batch dimension into the model whenever we trained it or ran validation with it, we're also going to add a batch dimension to the spectrogram whenever we run inference with the model, because that is what the model expects. And then down here we'll create a class for the endpoint. So I'll go ahead and say class and then audio classifier. We'll then just create a def load model. And this will then take in self, and we'll just say pass inside of this. And then first we'll just decorate the class itself. So I'm going to go ahead and say app.cls. We can then pass in the image, that is going to be image. We can pass in a GPU, that is going to be A10G, the same one we used for training. We can then also just specify the volumes. The volumes is going to be the following one, model. So we'll just mount the model volume to the following directory. So the model volume, and we'll also specify something called a scale down window. So whenever we make a request to the endpoint which we'll create, the model which we created, so the following one right here, is going to be loaded into memory. And loading a model into memory might take some time depending on its size. This is only about 81 megabytes though, so it shouldn't take that long. It will still take a little bit of time though. So for first requests, you might experience a little bit of latency. So we want to do this as few times as possible. So one way you can do this fewer times by setting this scale down window. So because this is serverless, the model will have to be loaded in per request. So this means if the scale down window is 0, this process of loading the model into memory will have to be done every single time we make a request. And that might take a lot of time per request. So requests will feel very slow. So therefore, if we set the scale down window to 15, for example, this model will be kept in memory for 15 seconds after each request, and therefore requests will feel way snappier. But you'll also pay for 15 seconds of extra runtime on the serverless GPU after you made the request, regardless of whether the endpoint is going to be hit again or not. So it's kind of a trade-off between fast requests and then also how much you want to pay to keep the function warm with the model loaded into memory. So what we can then do after defining this scale down window is to define the following class, or just decorate. So we'll say model.enter, and what this does is that whenever you make a request to the following class or the endpoint within this audio classifier class, if the function is called, meaning that the model has not yet been loaded into memory, this load model is going to be called. So basically every single thing you would like to keep warm whenever the scale down window is active, you should probably do within this load model right here, and then save them as instance variables so you can use them in the different inference functions, which we'll define below. So we have model int right here, and then first of all I would like to just set the device for the class. So I'll say self.device is equal to torch.device, and we'll say CUDA if torch.CUDA.isAvailable. Otherwise, so else we'll use the CPU. The CUDA GPU is going to be available though, because we do set the GPU to an A10G up here, so we should have CUDA. It is just good practice to do this. And this will of course be if and not is, so that we won't have that error. Good. Next we can define the checkpoint. So I'll say checkpoint is equal to torch.load, and we would like to load from /models. So this is where we attach the volume to /models/best model.pth. So the best model is then going to be the one right here, and that is in the root of the volume which we attach. So that should be all good. Next we can say map location is equal to self.device. And whenever we train, we stored a couple of things. We stored classes, for example. So let me just scroll down to where we did that. It is right here. So what we stored in this PTH file right here are the following properties. So we stored the model state dictionary, so that is what we'll load into memory. We also stored the classes, so these are the 50 different classes which we can pick between. So we would like to load these for the inference endpoint as well, just so we have those available. So after the checkpoint, we'll then go ahead and say self.classes is equal to checkpoint, and then we'll put in classes. We can then say self.model is equal to audio CNN, and we'll just need to import this as well. And then we'll say number of classes, that'll be equal to the length of self.classes. And because we have these 50, the length is going to be 50, so they should all work out just fine. Then we can say self.model.load state dictionary. So these are going to be all the different weights and biases that were saved for the best model checkpoint during training. So we would like to load in the checkpoint and then model state dict. So that is exactly what we saved right here. Then after this, we can go ahead and say self.model.to, move it to self.device. So it can be moved from the CPU to the GPU if the GPU is available. Then we can say self.model.evaluation mode. This means that the batch normalization layers and also the dropout layers are going to be disabled. And lastly, we can go ahead and instantiate an instance of this right here, and also save that as an instance variable. So I'll just say self.audio processor is going to be equal to audio processor like this. And lastly, I'll just say print and then model loaded on enter like this, just so we know. And then I'll just go ahead and just print out a function up, print it up here as well. So I'll say loading models on enter. This is where we can just keep track of what's going on in the logs. Next up, I'll create the actual endpoint. So below this method which we defined, we'll just say def inference. So we'll create a function called inference. We'll pass in self and then also the request like this. We'll decorate this with modal.fastAPI endpoint, and then we'll say method is equal to post, because we would like a post request, or we would like to be able to call this with a post request. Then we can create a class. So if I scroll up, we can say class and then inference request. So this will define the schema of the request which we'll receive for our inference endpoint. So we'll need to inherit from a base model from a library called Pydantic, but I'll just go ahead and define the audio data as a string for now, and then we can just go ahead and see if we can import Pydantic. So I'll say import, it's going to be from Pydantic. So we'll just need to import that. So I'll go ahead and open up the terminal, say pip install Pydantic, and then I'll just add the same library to the requirements right here. So from Pydantic import, and then I'll import the base model. And this is just a library for verifying model schemas and also creating them. So we'll just inherit from this. And this means that we'll have a schema that is compatible with what the model endpoint down here expects. So we can now pass in the inference request right here. Oh, I actually meant the schema. So whenever we receive a request First of all, we would like to decode the base 64 audio data from the request payload. So because this is a super simple visualization frontend which we'll create, I would like to just send the file directly from the frontend and then to our endpoint, and not upload it to an S3 bucket and then download it to this audio CNN endpoint. If you would like to run this in production, I'd probably prefer if you took the other route. So for production environments, it's probably best to have the frontend upload file to S3 bucket, and then in the Inference endpoint, we then download from S3 bucket. This is probably what we want to do in production, just to not have to ship super large files and audio files that might be 50 megabytes or have a gigabyte or whatever through network requests. But what we'll do is just say frontend send file directly, and then we'll get this in the Inference endpoint. So this is the approach we'll take, because we're just creating a super simple visualization frontend. But if what you want to do, if you want to serve a model like this in production, this is probably the route you're going to take. So just for your info, this is what we'll do. So first of all, we would like to decode this. So we'll say audio, and then bytes is equal to base64.base64 decode. And we'll just need to import this base64. I actually think it's B64 decode. And we can then pass in the request dot and then audio data. And because we defined the schema up here, we're able to see that audio data is a string down here. Good. So now we have the audio request decoded as a base64 audio data. Right now, this audio bytes is the entire file that was sent to the endpoint, but we would like to be able to access the sound only. So what we'll do is say SF, and then just scroll all the way up and define import sound file as SF, and we'll just need to install this sound file. So I'll say pip install sound file and add this to the requirements as well. Then this should install in just a second, like that. To be able to use the sound file library though, let me just see if it's spelled correctly. Yeah, to be able to use that, we'll need to just import a system dependency. So after this pip install from requirements, I'll just say .apt install. So this is for installing system dependencies, and I would like to just install lib snd file 1, because that is what the sound file library right here uses under the hood to actually perform the operations for both reading and writing audio files. Then we can further scroll down and just continue where we left off. So we can go ahead and say sound file dot read, and I would like to read, and we'll need to say IO and just import that IO dot bytes IO. Then we can pass in the audio bytes from the file which we received and define the data type to float 32. So this is the data type of the returned array. So that is the array which we'll receive from this read right here. Then we can just go ahead and get the return statements, all the return variables. So I'll say audio data, and I'll say sample rates. So that these are the two things, or at least some of the things that this returns, which we'll be able to use. So just like earlier, we wanted to, or maybe you remember this, we wanted to actually keep audio mono instead of having multiple channels. So in case it is not mono, we would like to just take the mean of the two channels and then use that as the mono channel. So I'll just go ahead and say if audio data dot number of dimensions is more than 1, meaning if there are 2 channels, for example, this would be 2, so left or right. What we'll then do is say audio data, just redefine it to numpy.mean, and we'll just import numpy as numpy. We'll pass in the audio data, and we'll say access 1 like this. Good. So now we make sure that the audio is actually mono, because that is what we have worked with so far, and we know the model is able to work with that. Good. So far we have also worked with a fixed sample rate. So I think the sample rate is something like 22,050. So we would like to make sure that the input file is that sample rate, or at least is resampled to become that sample rate, because it is best practice to use the same settings whenever you run inference with the model as you use whenever you trained it. So we'll go ahead and say if, and then sample rate right here is not equal to, and then the sample rate which we used. What we'll then do is just say audio data is equal to lib_rosa, and we'll just need to import this lib_rosa up here. So I'll say import lib_rosa, and this is actually inside the requirements right here. So we'll say pip install lib_rosa just so we have it locally as well. And then down here, whenever we need it, we can say lib_rosa.resample, and this should show up in just a second right there. Then we can pass in the y, which is the audio data. We can pass in orig sample rate, which is going to be the sample rate of the original audio, the target sample rate, which is going to be the following right here. So we basically just resample the file to have the correct sample rate. Good. Then we can process the audio, because now we have the raw audio into a spectrogram which we can feed into the model. And that is exactly what we created this audio processor class for. So we'll need to create this and then pass in this pass data into this process audio chunk function to then get the spectrogram out, which we can feed into the model. So what we'll do is we'll say spectrogram is equal to self.audioprocessor.processAudioChunk, and we'll then pass in the audio data like that. We can then say spectrogram is equal to spectrogram.to, and then we will move this tensor right here to the device that we're currently working on. So if you're on a GPU, it'll be moved to a GPU, otherwise it'll be on the CPU, like this. Lastly, we can actually use the model. So remember how we used the model down here? We said with torch.no_grad, and then we ran through all the batches. For each batch within this data right here, we were able to run inference with the model like this, calculate the loss like this, and then also see its predictions like this. So we'll do something similar down here. First, we can copy this with torch.no_grad, or you can write it yourself. And then what you can do is you can say output, and you can say, well, I think that is it for now. We'll then say self.model, because remember we loaded the model into memory early on in the enter function up here. So we are able to use the model just through the class instance. Then we can pass in the spectrogram, and we get the output out from the model. We'll then just clean the raw model output to prevent not a number probabilities. So we'll say output is equal to torch dot. We can then call a not a number to number, meaning if there is a not a number for some reason in the model output, this will just be converted to a 0, as you can see right here. So let me just hover it. By default, not a numbers are replaced with zeros. Good. So the model's raw output is just something called logits, which are scores and not probabilities. So we can use a function called softmax to convert these scores into a probability distribution, and then all the different values will sum up to 1. So all the different values will also be between 0 and 1. So we can go ahead and say probabilities is equal to, and then we'll say torch.softmax like this, and we can then pass in the output, and we can say dimension is equal to 0, because that is the dimension where the logits or the scores will be at. So if we just make a comment right here, the dimension 0 is going to be the batch, and then the dimension 1 is going to be the classes, because the tensor looks something like this: batch size, comma, number of classes like this. So this is just for info, you don't really need to keep this, it was just for me to explain what it actually is. Next, we can grab the top 3 probabilities or top 3 predictions. So what we'll do is we'll say top 3 probabilities, and we'll say top 3 indices. So these are the indices of those probabilities. These will be equal to torch.top_k. We can then pass in the probabilities, and we can pass in a 3 right here to return the 3 largest. So the reason we index 0 into the probabilities right here is because we only have a single item in our batch. So we select the probability distribution for the first, but also the only item in the batch. We can then create a dictionary of the different classes and also those classes' confidences. So the scores for each class, the probability for each class. So what I'll do is say predictions. And what I first of all want out of this, and let me just make a comment right here, is I would like something like dog, and then it should be 0.9, that is the score, and then this should be chirping birds, and that is going to be something like 0.1, etc. So we'll take these three probabilities, and then we'll make that dictionary. So I would like to create an array of dictionaries right here, and then I can say class. This will be self, and let me just say 0 right here actually. I can then say confidence, set this to 0 as well. What I'll then do is I'll create a bunch of these dictionaries right here, depending on the variables, depending on the top three probabilities. So we can go ahead and say for probability.idx in zip, and we can then pass in the top three probabilities and the top three indices like this. This means that we'll create pairs of these probabilities and indices. So let's say the probabilities right here contained the following. They contain 0.9, they contain 0.08, and they contain 0.01 and 0.08, something like this. Then we also have the indices, and the indices correspond to the specific classes which have these scores. So that would be something like 15, we could have 42, and we could have 5, for example. So whenever we put it into this zip function, this is going to create tuples like this, 0.9 with index 15, that is the first one. We then have the second one right here, 0.01 with index 42, etc. So that is what we do with zip right here. So we get the probability and also the index, these two numbers right here, and then we can use those to actually insert it into the correct dictionary up here. So we'll just need to replace this 0 with something that is true. So what we'll do is we'll say self.classes, because the class should be the string of the class. So I'll say idx.item, because the item is the index, remember. And then for the confidence, we have that inside the probability here. So what we can do is we can say probability.item, like that. Good. So now we have the top three predictions with the class and also the confidence for that class. I'll then just create a response variable. So over here, I'll say response is equal to, and I'll make a property called predictions right there. And this will contain the predictions array right here. We can then just return the response like that. And this is then a super simple endpoint that just returns the top three predictions. So before we move further, we can just go ahead and test this. First of all, I would like to hop into the ESC M50 dataset right here. And then I would like to find a file we can just test with. So if I hop under audio and then just take this one, for example, let me just play that for a second. We can actually just press a download raw file. This should download the file for you. So I'll just take the file and copy it into my folder right here. So I'll just do this. And then we can just play the audio file quickly. So these are definitely chirping birds. So I'll just call the file this as well. Good. So now we know that that works. We can then just create a mock frontend down here in a local entry point, which we can use to send this chirping birds file to the input right here, to the endpoint right here, sorry. And then we should be able to get those predictions back. So that is exactly what we'll do. So down here, I'll go ahead and say define main, and we'll then just say app.local entry point like this. So when we run the file locally, when we run this file, this should be executed locally. So that is the exact same as we did right here whenever we ran the training script. Good. So inside here, we would like to first of all load the audio file. So I'll say audio data is equal to sf.read, and we'll read the audio file, and the audio file is going to be chirpingbirds.vav. So I'll just do that. I'll then just go ahead and prepare the payload. So we'll say buffer is equal to io.bytes.io, and then we can say sf.write buffer audio data, the sample rate, and we'll set the format, which is going to be VAV. So this will just create a VAV file in memory instead of writing it to the disk. What we can then do is just go ahead and say audio base 64. So that is what we'll send to the endpoint. This will then be equal to base64.b64 encode. We'll say buffer.get value, and we'll say .decode to UTF-8. So this right here, B64 encode, takes the raw audio bytes and then encodes them, but the result is still going to be a Python bytes object. So because we're sending JSON to the endpoint and we can't just put in raw bytes into a JSON payload, we'll just need to convert it into bytes, which can be sent as a regular string within a JSON object. So therefore we decode it as UTF-8. Next we can say server is equal to audio classifier, and then we can say URL, so we'll just get the URL of the actual endpoint which we have created up here. So URL is going to be equal to server.inference.get web URL, like that. We can then say response is equal to, because now we'll make the requests, which we'll just import, dot post, so we'll make a post request, because remember we defined up here that this is a post receiving endpoint. Then for the post request, we can pass in the URL we are calling to, so that is the endpoint URL, and we can pass in the payload, so pass in the message which we're sending to the endpoint, and that is going to be the encoded file from local. So we'll say JSON is equal to payload, like that. And actually we haven't really defined the payload, we have only defined this. We'll just need to put it into JSON, so we'll say payload is equal to audio data, and we'll put in the audio byte 64 right there. And the reason we are defining this key audio data is because remember up here in this inference request, we defined that this is a required string within the schema. So that is why we pass this in and send that to the endpoint. Then if we get a bad status code back, we'll just say response.raise for status. So we'll throw an error in our local Python program if we get a 400 back, etc. So we can then just decode the result we got from the server. So we'll say results is equal to response.json. So we'll now have the response as JSON. We can then say print and then top predictions. Under this, we'll just go ahead and say for prediction in, and then results.get predictions, because we defined that we return predictions right there. Then we can say .predictions. If it is not there, we'll just return an empty array from this get operation right here, so we don't get an error. And then we'll loop through each of the predictions and say prints, and we can put a formatted string. We'll say something like this, and then I'll put in, this will need to be F, not an R. Then we'll put in prediction class. We'll put in the prediction confidence, like that, and we'll just format this number right here as a number with 2 decimals, and then we'll format it with a percentage right after that. Good, so now we can go ahead and save this file, and now we should be able to deploy the endpoint and then just test it locally, because we do have the file right here, chirping birds. Good, so what I'll do is just say modal deploy main.py, and I spelled this incorrectly, modal deploy main.py, and this should then just build this Docker image up here, because we did change some of the files from requirements.txt. It does not download the entire dataset though, because it is not the one right here which we are running, but the image right here. So it is a little bit different and also a little bit simpler. So I'll just come back whenever the modal endpoint has deployed or failed, we'll see. Alright, so the endpoint just deployed. As you can see, this entire image up here was built just like it was earlier. It had to download some of these files, librosa for example, and then all the way down we can see that the image was saved and built, and then we have the actual URL which we can use to call the endpoint up here. So now that we have the endpoint deployed, if we hop into modal, we should be able to see it under apps. So under live apps right here, we see that we have 0 calls, but it is at least deployed as a web endpoint. Then what we'll do is say modal run main.py, and whenever we run main.py, this triggers the local endpoint down here. So, local entry point. So that is going to be the following function. So that should let us test out the endpoint. So let me just run this and then see what happens. And I actually just looked into this for a second, and it looks like we'll need to destructure this into two different variables. Also unpack the tuple into two different variables. So we'll say sample rate right here. And that should then allow us to call this correctly. We'll just need to deploy it again because we did change the code now. This should take not a lot of time though. Then we can say modal run main.py and then just see what happens whenever we run the app. So I'll just let this run and then come back when it is done. Alright, so these are the predictions that we got. So we got loading models on enter, model loaded on enter. Then we get the top predictions. These are ran on the server, these are ran locally. So we can see locally that we got a response from the server with chirping birds being the absolute highest prediction. So that is very true because we did just listen to the actual sounds and those were definitely chirping birds. So seems like it is working just fine as it is supposed to do. So that is actually great. It did seem like the terminal reset in kind of a weird way and really removed the results, but that doesn't really matter that much right now. Good, so we'll just close this down and then I would like to move on to the part with the visualization. So as you saw in the intro, we are going to visualize the output of the specific convolutional layers, and these are the layers which we're talking about. So the different blocks right here from the different layers. So the way we're going to do this is by saving the outputs of the feature maps after each convolutional layer in the forward right here in the network. So right now we have created the totally normal model, which does not do this, but I would like to create an option up here. So a parameter that says return feature maps, which should be equal to false by default. But if you switch this to true, you should also get the output of each of each layer in addition to the actual model outputs, because that is what we're going to use whenever we visualize what it outputs. So first of all, up here, I'll say if not return feature maps, then we'll just do what we usually did. So we'll go ahead and do that. Otherwise, if we do want the feature maps returned, we can go ahead and say else, and then we can define a feature maps is equal to an empty dictionary right here. And then what I'll do is just take all of this up here and just copy that, because we'll need to run the same forward anyways. Then we can just save the output of each of these. So for the first one, we can say feature maps, and then we would like to save the first convolutional layers output. That is going to be equal to x, because that is what was outputted by the first one right here. We can then just do the same for the rest of the feature maps. So first of all down here, or second of all, sorry, this is going to be layer 1. And then for the next layer, this is going to be layer 2. We can then also do the same for the next layer. That is going to be layer 3. And for the fourth layer, which is layer 4. Then instead of just returning only the results of the model as we did up here with return x, what we'll do is just return both x but also the feature maps, just so we can return those to the client, so the front end, and then render those out as the visualizations which you saw within the intro. Now these right here, layer 1, 2, 3, 4, and also the first convolutional layer are just the outputs of the full convolutional layers, but remember each convolutional layer consists of multiple of these residual blocks. So what we can do is actually take the output of the residual blocks, so the inner workings of these convolutional layers right here, and then also map these out in as you saw in the intro, just so you're able to look at even more. So what we'll do is just allow for that to happen. So we go into the forward function for the residual block specifically because we want to save something from that. Then we can say feature map dictionary is equal to none, so you are able to pass it in if you would like to. We can also define a prefix, so that is what we would like to save the actual output as, so that is the same as right here, for example. Then the prefix will just set to an empty string for now. Then down here, I would like to save the output. So since this can be used with either the feature map set to none, but also not none, which all depends on whether we're using the return feature maps flag. So this one right here. Or if we do not want the feature map returned, we'll just check whether this is none or not, because it might not always be passed down. So first of all, this out add right here, I'll say if map dictionary is not none. So sorry, not on this, after this out add a variable right here, we'll check if it is not none, and if it is not none, we'll then go ahead and save the output after this out add. So we'll go ahead and say if map dictionary, and we can then create a formatted string where we put in the prefix. So let me just spell this correctly, prefix.conv. So this is the prefix. The prefix might be something like layer 1 dot, and then the specific residual blocks which we're referring to. And then within that residual block, we can then say dot convolutional layer, because that is the output of the convolutional layer, as you see right there and also right there. And then we can save the output after the convolutional layer, but also the output after the relu, because it is pretty interesting to see what relu actually does. So this right here is going to be equal to out add. Now we can then also do the same after the relu. So after relu down here, we'll just go ahead and do the same. So we're just going to say relu, and then that is going to be equal to out, because as you can see, relu right here returns out. We then now need to pass down the feature map dictionary and also the prefix into this forward function whenever we use a residual block. So that is right here, right here, right here, and also right here. Sorry, we actually use them right here whenever we call the actual blocks within these specific layers. So for this block right here, we're just going to pass in the feature maps, and we'll pass in a prefix. And the prefix should be something like a formatted string, where we say layer 1 dot block, and then we put in the specific block number. We do not have the block number right now, but we can go ahead and say enumerates like this, and then we get out both the index and also the block itself. And this way we can put in the index like this, and then we say layer 1 because these are the blocks for layer 1 specifically. Good. So let me just go ahead and do this for the rest. So I'll put in I, and then I'll wrap this in an enumerates, and then I'll put in I, wrap it in an enumerates, and I'll do the same for layer 4 down here. And now we can just set in, I'll put in the prefixes as well. So I'll do that, that, and that. So this is going to be layer 2, this is going to be layer 3, and we'll have layer 4 at last. Then because we now also return the feature maps, we can go ahead and get those out from the tuple, which we get when we run inference. So we'll say feature maps like this. So now we also have the feature maps after running inference with the model. If we then scroll down, we can go ahead and add some more things to this response right here, containing both the input data, such as the waveform, the spectrogram, and then lastly also the output of the feature maps, the output of the convolutional layers, aka the feature maps. So that is what we'll do right here. So after predictions, I would like to create a new variable called visualization data, like this. And the goal here is then to take these complex multi-dimensional tensors from inside the CNNs and turn them into simple 2D heat maps basically that we can easily display in the front end. So we'll need to do a little bit of processing to just take the feature maps and then display them in the front end. So the first thing I would like to do is just loop through all the different feature maps. So I can say for name and tensor in feature maps dot items like this. Then I would like to say if tensor dimension is equal to 4, then we would like to include it. And the reason we're only taking tensors with the dimension of 4 is because feature maps specifically have the following structure. Batch size, they then have channels, and they have a height and a width. And remember, depending on how you set up your convolutional neural network or convolutional layer, you might have a different amount of channels. So you might have this tensor with 64 channels, for example, but we can't really show 64 plots for each of the feature maps in the front end. So we'll need a way to condense these 64 different channels, if that is the case, down to something that is easily displayable. So we'll need to take the aggregate of all of those, and we basically do that by taking the mean of every single channel and then building a single 2D heat map from that. So this check, where we check if the tensor dimensions is equal to 4, just checks if we actually have the output of a convolutional neural network, or a convolutional layer, sorry, because we would like to just ignore any other spatial feature maps if there is a 1D or 2D tensor, even though it probably shouldn't happen. So inside this if statement, what we can do is say torch.mean, and then we can pass in the tensor, and we can say dimension is equal to 1. We'll then just take the output of this and call it aggregated tensor. So basically we take all the different channels, because as you see right here, we pass in the tensor, we take the mean of the first dimension, which is the channel. So let's say there are 64 different channels, which are the outputs of the convolutional layer. Then we'll take the mean of all of those different channels, and then this will be the aggregated tensor. That will then also take this channels right here and remove that. And now we have the batch size, width, and also the height. So the next thing we're going to do is just remove the batch size, because we only pass in a single file at a time whenever we do inference. So we know that this is always 1, so we can just go ahead and remove that. And the way we remove a dimension is by saying squeeze. So I can say squeezed tensor is equal to aggregated tensor dot squeeze. And we would like to squeeze the 0th dimension, which is going to be the one right here. After squeezing it, we're going to turn it into a numpy array instead of just a tensor. So I'll say numpy array is equal to squeezed tensor and then .cpu to transfer it to the CPU if that was not there already. And then we'll say .numpy to turn it from a tensor to something which we can send back in a JSON response if that is what we would like to do. Next we can say clean array and just take all not a number values if any of those actually occur and just turn those into zeros. So we'll say np dot not a number. So we'll use the exact same method as we used before, not a number dot to number. We'll pass in the numpy array, and after this we'll just append the current feature map, which we're currently looping over, to the visualization data right here, so we can send this back as part of the response. So the way we're going to do this is by saying visualization data, and then we'll take the name, so that is what we'll call the index property key. Then we'll make it equal to the following dictionary. We would like to store the shape. The shape will be a clean array dot, and then we'll take the shape, and then we'll also take the contents of the actual array. So this is going to be clean array dot to list, like this. Good. So now we loop through every single feature map. Then we take the mean of all the different channels in the feature map, so we only are left with a single feature map. We also remove the batch size channel, so we only have the height and the width channels left. And then we append it to a list such that we have all the different feature maps, but with only one channel per feature map. And we can then take these and return them down here in the response. So we'll call this visualization, and this will be equal to visualization data, like that. We can then also send the input spectrogram that we fed into the model initially back to the front end, such that we can also visualize the input spectrogram and how this is turned into the outputs of the convolutional layers. So what we'll do is under this right here, say spectrogram numpy is equal to spectrogram.squeeze, and we would like to squeeze the 0th dimension and do that twice. And the reason we're doing it twice is because the 4D shape is going to look something like batch channel and the width, the height, and then the width. So we squeeze the first one, the batch, and then we squeeze the second one, the channel, and then we are left with only the width and the height because we don't really need the other ones. So that is why we do a double squeeze right here. Good. After this, we can move this to the CPU, and we can say dot numpy, like this, to turn it into a numpy array. Then I'll just go up here to where we actually get it. So right here with self.model, we'll just need to say return feature maps is equal to true, because remember we defined this property, this parameter, which we'll need to pass down into the forward function right there. So we'll need to set that to true for it to work. Good. Going back down, we can then again remove all the not numbers if they even exist. So we can do the exact same as we did right here. So what I would like to do is just say clean spectrogram is equal to the spectrogram passed in like that. And then we should be able to actually append this to the visualizations down here. So I'm going to use kind of the same format as we did there. So I would like to say input spectrogram, and this is going to be equal to that dictionary. So the first thing we'll pass in is the actual shape, and this is going to be the clean spectrogram.shape. The second thing we'll pass in, we just need a comma right there. The second thing we'll pass in is just the clean spectrogram itself, .toList, so we have the values. The last thing I would like to pass in is the waveform that the input spectrogram was based off of. So we'll just go ahead and transform that data into something which we can ship back to the front end as well. So I'll just create a new line down here. And the first thing we should do is just downsample the raw audio waveform just to a manageable size, because if you have a sample rate of 22,000, for example, that means you have 22,000 data points per second. So if you have maybe 5 seconds of audio, well, that is about 100,000 different data points, which you send back via JSON. So it's really a lot of data. So what we'll do is define a max samples. That is going to be the maximum amount of samples which we would like to send back. We'll then check if the number of audio samples exceeds max samples. So I would like to say if, and then length of the audio data is more than the max samples. And if that is the case, we'll create a new step variable or step value, which we can use to create a smaller version of this audio data that takes every nth sample from this original data. So what we'll do is say step is equal to length audio data, and we'll do a division with rounding of max samples. So for example, if we have 100,000 here, but the max samples is 8,000, then we'll take about a little more than a tenth of the actual samples. So we'll step over every 10 of the samples in the original audio data. So we can go ahead and say waveform data is equal to audio data. And we can then put in 2 of these, and then we can say step like this. If there are less data samples in this audio data than 8,000, well, then we are not exceeding the limit, so we can just go ahead and send it back because we are already fine. So we'll say waveform data is equal to audio data without transforming it in any way. And just to explain this syntax right here as well, this will create a new array in Python, and then it'll select the items elements from this audio data right here, starting at the beginning, going all the way to the end of the array right here. But it'll take every nth step in the every nth element inside this audio data. So if the step is 10, for example, it'll take value 0, 10, 20, etc., all the way over to the end. So this lets us downsample by skipping a bunch of different samples, so we can ship less data back to the front end. Then lastly, I would like to just return this down here as well. So I can say waveform, and we can then pass back the values. The values will be waveform data .toList like this. We can then also just send back a sample rate in case we would like that in the front end. And I think that was 22,050 like that. So I'll just copy that value and hop back in here and just return that. And I would like to also just return a duration of the clip. So this would be the length of the audio data divided by the sample rates. So these are samples per second, and this is going to be the samples. And if you divide these two, you'll get out the seconds, so the duration of the clip. Then before actually building out the front end, we can just deploy this and test it out. So what I would like to do is just hop down into this local entry point and then just print out a little bit of the data that we sent back from the waveform, for example, just so we see that it returns something and that it works. So the way I'm going to do this is by hopping down here, and then I'll say waveform info is equal to results.get waveform with a fallback value of just an empty dictionary right there. So we would like to get the following property right here, and then the values inside of that. So we can then say if waveform info, then we can say values is equal to, and I'll just say waveform info dot get, and we can say values. Now we can say print, and then something like if first 10 values, And then we can say round v and 4 v in values, and then we will slice the first 10 values like this. And then we just need to put this over here instead, and then we'll say dot dot dot. So we'll just print out one more thing. I'll just print out the duration. So I'll say duration, and that is going to be waveform info dot get duration, like that. And then we'll just have a fallback value of 0 if that isn't there. Good. So now we should be able to deploy this endpoint. So I'll say modal deploy main.py. This should just take a couple of seconds. So now it is deployed. Then we can say modal run main.py. So now we'll just wait for this to finish, and I'll come back in a couple of seconds when it is done. First of all, I can see that the first 10 values right here look good. So we do see some data coming back, which is great. I do see that the duration is 10 seconds, but as far as I remember, it's actually 5 seconds. So I think we have something wrong going on with either the sample rate or some of the logic which we created earlier. And then we still get the correct prediction out, just like we did before. So let me just take a look at the duration and what goes wrong, and then come back to you with the solution. Alright, so I had a chance to look into this, and I found a little mistake that I made earlier. So I downloaded 2 more samples, this one and this one. This is a clapping and this is a thunderstorm. Both of these are just random samples that I picked out of the GitHub repository right here and downloaded. And then I wanted to test out some of the other things as well. So first of all, I ran the following command. Let me just see if I can find it. I ran the following command right here to just extract the actual sample rate from the files that we are running into the model and training the model on. So whenever I run this command, I can see that the sample rate is actually 44,100. So this is the sample rate of all of the different files from this dataset. So one of the errors that we made earlier is that I set the sample rate right here to 22,050. I did this 2 different places in train.py. So actually the model is configured a little bit wrong, and it should actually be 44,100 both right here and also down here. This obviously didn't impact the training enough to give us a lower score than 83%, which is pretty good. But you might get an even higher score if you actually fix this to the correct sample rate that matches the files, because this will cause the Mel Spectrograms to be more correct and also more clean. So what I next did was that I went into main.py. Then instead of having 22,050 right here, so just a hand-coded sample rate, I took the sample rate that we actually got from the VAV file, and then I used that instead. Also up here, where we do resample on the server, I changed this from 22,050 as well, right there and right there. So this is what it originally was. Then I changed that to 44,100 because this is what the model has been trained on. So even though this isn't perfectly correct, because as you see, we trained the model with the following configuration, but with another sample rate in real life, this is still what the model was trained on, so that is what we should pass into the model. Therefore, we will instead make sure that the sample rate actually matches what the model was trained on, which is 44,100. So now after deploying this, and let me just do that. If I hop over here and then I say modal deploy main.py, we should be able to see that the following 3 audio files match perfectly fine. So if I just take this one, for example, that is clapping, and this one, that is a thunderstorm, and we know the chirping birds already. I can then say modal run, and then I can say 1.vav, that is going to be the clapping. So I'll say 1 right there, not 1.vav right here. I'll say main.py right here. And then we should be able to see the label of the prediction coming out being clapping. So I'll just come back whenever that is done. So now we see clapping right here. So 88%. And we also see that the duration is correct. And then I'll just check with the thunderstorm as well. So I'll just pass that in and just wait for that to finish. And we also got the correct the correct prediction for the thunderstorm. And lastly, let me just check with the chirping birds. So I'll just put that in as well and wait for this to finish. And the chirping birds is the correct prediction as well right here. And we see the duration is correct. I do see that the duration is in a tuple right now. So that is of course a little bit wrong and I don't really want that. So what I'll do is just change this. It is actually put in the wrong place, this in parentheses right here. So that should fix it. I also see I need to fix that as well. But as you can see, the API is now working. So we can send back both the predictions, the visualization of each convolutional output, the input spectrogram, and then also the waveform. How correct these are, we'll need to see whenever we actually build out the front end and test that, but they should be completely fine. So yeah, that was the backend part of this series. And what I'll then do now is just go ahead and actually build out the front end so we can show the visualizations by calling the endpoint, which we've just created. So just as a side note before we hop into the front end part, I actually did just fix the model configuration. So I put in the correct sample rate both right there and also right there. And then I retrained the model once again. And then the accuracy became 84.25%. So it isn't really much higher than the 83% which we achieved earlier. I have also before trained the exact same model right here, just with the sample rate that is incorrect like this, on the same dataset, and I got the accuracy all the way up to 86% with the incorrect configuration. So therefore this incorrect sample rate right here doesn't really seem to have much of an effect on the actual accuracy on the model, of the model. It is pretty interesting though, because before when we trained the model with the incorrect configuration right here, what it leads to is that this Mel Spectrogram thinks that the sample rate is actually 22,000 when it is actually 44,000. And this will then lead to distorted spectrograms where the frequencies are twice the size of the reality. So the model is actually going to learn the wrong features. But this didn't really seem to be a problem for the model, and it learned to make the correct probabilities or correct predictions, even though we had the wrong spectrograms. So it seems they were smart enough to get around this little issue, which is pretty cool to think about. So with this out of the way, we can go ahead and actually build out the front end. So to first get started with the front end, I'm going to create a new Next.js application right here in the root. So I would like to use the T3 stack to initialize that, just because that is what I know the best. So if you search for the T3 stack and then you hop into the following URL right here, then you should be able to copy this command and then paste this into the root in a new terminal right here in the audio CNN repository. So I'll just go ahead and do that. And then the project is going to be called audio CNN visualization or something like that. You decide, of course. Then you can press enter, select TypeScript, and I'll use Tailwind. I would like to not use gRPC. I don't really need any authentication just because this is a simple visualization program, not really any SaaS or anything that I want to distribute to any people. I also don't really need any database ORM because I don't really want to interface with a database because the application is so simple, so I'll press none. The app router I'll say yes to. I'll say yes to ESLint, and I would like to say no to the Git, and I would like to say yes to npm install. And this I'll just press enter for as well. So this should then create a new folder right here with a full Next.js repository right here, which we can then run in just a second. So I'll just wait for the npm packages to install and then come back. Great. So now that we can see that the project has been successfully set up, we can go ahead and actually run this. So first of all, I'll just close down all of these files that we have open and just leave main.py open only. Then we can see that we need to change directory into the directory which we just created right here. Then we can say npm run dev, and that should then start up the Next.js project. Then you can take this URL right here and paste it into your browser. And you should then be able to see the create T3 app, which is running on a local server right here because we are on localhost. So now we know that the front end is working as well, and we can go ahead and shape out how the application should look. So you can start by going into the source folder, then under app, and then you can find page.tsx. And the page.tsx file is what renders out the following page right here, because this is just the root page. So next I would like to just close this down, and then I'll take this entire thing and just remove that. If we then press save, we can see that it should update all immediately over here, which is what we expect. Cool. So now we can take the classes for this main right here, and then we can change those a little bit. I would like to say minimum height of screen, and I'll say BG stone 50, and I would like to say padding of 8, just so the content is padded and don't touch the edges on any of the sides of the window. Then we'll create a centered box for all content, so I would like to create a div We'll put in some classes mx auto to center it horizontally, and then a max width of 60%. And then if you want to see how it looks, we can just put in a background red 400 or something, and then put in hello into this box. Maybe we can put in a paragraph like this, say hello, and then we should be able to see this. And I just restarted the server, but now I can see it right here. It says hello. So that is exactly what we were expecting. So that is good. Then we can put on a header. So I'll just remove this background red, and then inside the div, I'll create another div. We should put on the class names margin bottom 12 and text center. Inside here, I'll put in an h1. So for heading 1, a big heading, and I'll say CNN audio visualizer. I'll then just put in class names. I'll say MB4. I'll say text for Excel. So very large text. Then I'll say font light, tracking tight. And then I'll say text stone 900 like this. So that was the heading. Then we can put in a paragraph, so just some subtext. I'll then say upload a WAV file to see the models, predictions, and feature maps like this. And I'll just format this a little bit because it looks a little bit too large compared to the actual heading up here. So I'll say margin bottom 8, text large, so way smaller, and then text stone 600 like that. And I think I'll just take this and make it medium instead, just so it's smaller again. Then under this paragraph here, I'll create one more div. I'll say class name flex column to stack the items inside of it, and items center for centering. Then I'll put in another div, and I'll say class name relative and inline block. Inside here, we'll put in an input. This input is going to be such that we can upload files. I'll close it this way instead of creating an int tag. We can then say type file. We can say accept, so we only want to be able to upload .vav files. We can then also say ID file upload, and we can say class name absolute. We can also say inset 0 with full cursor pointer and opacity 0 like that. So this is just a hidden input file. So if I just remove, let me just find that. If I just remove all these classes right here and just press save, then we can see that we are able to see the actual file pick a dialog button right here. But that is not what we want to see. We want to keep this hidden such that we can style the actual button ourselves. So next I would like to just quickly import ShadCN, just so we can reuse the buttons already created by ShadCN. So I'll just hop in under installation, Next.js, and then we can go to npm and just copy this command into the terminal. So if I just open up the terminal right there, create a new one, and then say cd, let me just open up one like this instead actually. So now we have opened it up a terminal inside this folder right here, and we'll be able to install ShadCN just in neutral color, and we should then be able to add a button if that is what we want to. So I'll hop under copy to clipboard for the button right here, and then just paste that in. And then if we hop back over here, we should be able to actually see the button once we create it in just a second. So rather than this input, we'll put in a button. This button will have some text. We can just say choose file for now. We'll just need to import this button and then say variance outline size large like this. And we then also want to put in, and this was actually opacity 0 and opacity 10, because otherwise we'll be able to see it, which we don't want to. And then after size large, we can put in some class names. So border stone 300. We'll then just create a use state up here to track whether we are currently analyzing a file or not. So I'll just say use client first of all to make this a client component. This means that we can use things such as use state, which can only be done in client components. Now I can say const, and then I can say is loading, and set is loading to keep track of whether we are currently analyzing a file or not, is equal to use state. We'll set loading to false by default, so we'll go ahead and import this. Then down here, instead of choose file, we can then change the text dynamically based on whether is loading is true or false. So down here we can say if is loading, then we would like to show analyzing ... Otherwise we'll show choose file, and then also we'll disable this up here if we are currently loading, such that you can't really upload a file if we are already loading. So I'll go ahead and do that as well. Now if I click right here, we shouldn't really be able to see that it is loading, so I'll actually just set this to true, and then we can see that it says analyzing, and if I do click it, nothing really happens. If I set it to false and save, we can then click this button and then it'll work, and we can choose a file. And I'll also just disable the actual button if we are loading, so I'll go ahead and do this, meaning that we can also not click the button if we are loading. We'll just create a simple function now for handling what happens whenever we select a file. So if I click right here and then I click and select a file, we should be able to see something happening. So I'll say const handle file change is equal to, and we'll make this an async function that'll take an event. This event should be a react.change event of an HTML input element, like that. And then this should return a function. So whenever you click choose file and then select a file, we would like to grab that file. So we'll say const file is equal to event.target.files. And then we'll grab the first one because we only want to select a single file at a time. Then we can say if not file. So if no file is there, we'll just return and not do anything else in this method right here. Then we can set the file name first of all, so we can show that in the UI. So I would like to create one more use state, const file name set file name is equal to use states, and then we'll just make this an empty string for now. Then we can say set file name and set this to file dot and then name, like this. And because we are about to start analyzing a file, because we just picked a file basically, we'll just set is loading to true as well. So I'll say set is loading. So whenever you select a file, it'll start loading immediately. So we'll say set is loading true. And we'll also just create a use state for tracking whether there's an error or not. So I'll say error and then set error. And this will just be an empty string for now. I'll just make this null actually. So it can be either a string or null, like this. And then if there is no error, then it'll be null. Otherwise it's going to be a string containing the actual description of the error. We can then create one more use state for storing the state of the data we get back from the API. So we can say const and then something like visualization data and set visualization data is equal to use state. And we'll just need to define the actual type of what we can get back from the API. So we'll just set this to null for now and then say null, like this. And then we'll just create the TypeScript types which we expect this use state to store, and also that is what we expect this API right here to return. So what we should create in our frontend is something that matches the types of the following keys and properties right here. So visualization, predictions, input spectrogram, and also waveform. Good. So going back in here, we can have an interface called prediction. This prediction will have a class, which is a string, and we can have a confidence of that class, which is a number. So a class could be a dog, a confidence could be 90%, for example. Then we can have an interface called layer data. We have a shape, which is a number. And we have values, so the actual values of that layer, and this will then be number. We have two dimensions because we have width and height. Then we also have an interface called visualization data. Here I would like to have a dictionary, so we'll say layer name, which is a string, and we'll then have the layer data for each of the different layer names. We can then create an interface called waveform data. We'll have all the different values, which are numbers. We'll have the sample rate, which is a number, and we'll have the duration of the waveform, which is also a number. Lastly, we'll have an interface called API response. This will have a prediction, which is of type prediction. So that is why we just created the one above. Like that, we'll just make this an array because there are multiple predictions. We'll then have visualization. Visualization is going to be of type visualization data. We'll also have the input spectrogram. This will be of type layer data. Lastly, we'll have the waveform, which will be of type waveform data like this. Good. So now we have basically modeled what we get returned from the backend over here. So that is what we can then store in a use state whenever we get a response from the backend. So we can now say that visualization data can either be that if we do have a response, or null if we don't have anything returned from the backend yet. So every time we upload a new file, if we have already uploaded a file and gotten a response before, we'll just reset the previous response to null such that we can fill it out with the new response. So I would like to also say set, both of all, set error, set this to null, and also set visualization data to null, just so we have a clean slate. Then we can say const reader is equal to new file reader, because we are about to upload a file directly to the server. So I would like to say reader.read as array buffer, and we'll read the file. And then we can say reader.onLoad. And this will be equal to async. And in here, we would like to convert the array buffer, so the raw binary data of the file which we just selected, into a base 64 encoded string, which we can send to the backend inference endpoint. So first we can get the array buffer, so that is the contents of the file that was just read in as raw binary data. So const array buffer is equal to reader.results as array buffer, like this. Then we can say const base 64 string is equal to, we can use a method called btoa. Then first we'll say new, and then uint 8 array, where we pass in the array buffer dot reduce. In here we can say data and bytes, and this will then become data plus string dot from char code bytes with an empty string right there. So let me just explain exactly what this does, because this is a little bit complex when you just look at it for the first time. So the file that we just selected up here is first of all read as an array buffer, and then array buffer is just raw binary data, but this should be converted into a base 64 string such that we can send this to the backend inference endpoint, because that is what is expected in the backend. So first the binary data is converted into a string. So the array buffer reads the file selected over here, and it is going to be read as just raw binary data, which is the contents of the file. And we then have this in this array buffer variable right there. Next we're trying to create this base 64 string. And this outer function btoa stands for binary to ASCII, and that is used to create base 64 strings. But this btoa function can't work directly with this array buffer, because this is just raw binary data. So to prepare the data for this btoa function, we use this new uint8 array, and this will create a view basically of our binary data, where we can access each individual byte and then loop through those with reduce. And then each individual byte is going to be a number between 0 and 255. Then using this reduce right here, we can loop through each one of those bytes. And then for each byte in that array, we are running data plus string.from char code on the specific byte. And this will then convert a byte's number into a character and then add it to a string. And then we start with an empty string by marking that we have an empty string down here. So this reduce part that I marked right here just basically transforms the list of byte numbers into a single string of characters. And the final result of all of this is then passed into the BTOA function, which will then encode this into a base 64 string. That is what gets stored within this base 64 string variable. So now that we have encoded the file to send to the backend, we can go ahead and actually send it to the backend. So what I'll do is hop down here, and then I would like to say const response. And then I would like to say is equal to await fetch. And then I would like to make an HTTP request to the actual deployed endpoint. So if we hop under our apps over here in modal, and then I'll just make this a little bit larger, we can see that we have a web endpoint. And by clicking right here, we should be able to see the actual deployment URL. So I can take this, I think I'll just copy it if that is possible. So I'll say copy, and then we can paste this in as where we make the fetch request to. So I would like to just paste it in right there. And then as the next parameter, I would like to put in an empty dictionary. And then we can specify the method, which is going to be post, because remember, we set it up to be a post endpoint or post receiving endpoint. And then for the next parameter in here, I would like to put in the headers. This will be content type. And then this will be application at JSON or /JSON. And then after the headers, we can put in the actual body, which we send to the endpoint, and we'll send out JSON. So we'll say JSON.stringify, and then we'll stringify audio data base 64 string. And remember, the reason we have audio data as the key name is because that is what we defined up here in the inference request schema. Good. Then this request right here is being made, and then after the request we can say if not response.ok. Then we'll throw a new error where we say API error, and then just let me make this a formatted string. Then we can just do something like response down there dot status text, just so we know what the error is in the terminal. Otherwise, if the API call worked out just fine, we'll say const data of type API response is equal to await response.json, like this. So we take the response we got back from the server, convert it into JSON, and then we store it in a variable with the type API response, meaning we can get the properties with types on them. So that's pretty nice. And then we can say set visualization data, and we'll set this to the data because a variable of this type is what we can store within this use state right here. Then down here under the reader.onload, we can go ahead and say reader.onError, and I'll then make this equal to the following, and we'll say set error failed to read the file, and we'll say set is loading to false, like this. And we can also just wrap this entire thing in a try if we want to. So what I'll do is just mark everything, or select everything, sorry. So I'll just take this, and then I'll wrap this in a try, catch. Inside the catch, we'll catch an error. And let me just put this into here. And then inside the catch, we would like to say set error. And we'll set the error to error.message, like that. We will only be able to access this message property though if this is of an actual type error, and right now it is unknown, so we'll just check what the type actually is. So we'll set the error if error is instance of error. In that case we'll set it to error message, otherwise we'll say an unknown error occurred, like that. And then down here in the finally, which we'll just create as well, so that is going to be ran regardless of whether the catch or the try finishes. Then we'll say set is loading to false, just because we want to set is loading to false regardless of what happens. Then down here we'll just show the actual file name whenever you select a file. So down about here we'll say file name, and we'll say and we'll then put in a batch from Chatien. So we'll just need to go ahead and install that component quickly. So I'll hop over here and then find the batch. I'll pick the npm version, hop into my terminal, and then I'll put in this command for installing that component. And then we should be able to import the batch. Oh, not that one. That one from components UI batch. Great. Then we can say file name. And let me just open up the following one. Then we can say file name. I think we need to spell it with a large N. File name, and I'll just go ahead and save that. Then I'll just make this a hard-coded string and set this to true just so we can see how it looks. And then for the class name, we'll go ahead and say empty for, so we can space it a little bit from the choose file up there. Then we can say pg stone 200, text stone 700. Let me just find this. Text stone 700, good. And then we'll say variant secondary, like this. Great. Now I'll just use the correct file name, both right there and also right there. And then we should be able to actually see what happens when we click right here. I'll just implement the error message first though, and then we'll test out the actual file uploading. So I'll just hop down here, and then I'll say error, and we'll put in a card, which is another component which we'll need to install. So we'll hop under card, find the card right there. Oh, install that. Then we can hop back into our web page, and we'll just import the card here. And then inside the card, I'll put in the card content. Inside the card content, I'll put in a paragraph, and then I'll say error, and then we'll make sure just to show this at all times, just so we can test it out. Inside the card, inside this error right here, we'll put in the actual error message, if there is any error message. Because remember, we do set the error message up here if an error does occur, both right there and right there. Then we can style this a little bit. So we'll say class name text red 600, like that. And then we can go ahead and hop into the card, say class name. For the class name, I'll put MB8 border red 200, and I'll put in BG red 50, like that. And then we will of course only show the error if the error actually occurs. So we'll just go ahead and make this a conditional. Good. So now that we have something that should work, at least for a proof of concept, without actually showing the data that is returned from the backend, we can go ahead and test it out. I think we need to just do one thing though, because right now we defined this handle on file change, but as you can see, it is grayed out because it is unused. So what we'll do is just copy this and then actually use it down here. So we'll find this input, and then we'll put in on change, I think it's called right there. So whenever you do select a file, and we'll then call this handle file change. So I'll go ahead and save this, and over here I'll just refresh just to make sure the server is up to date. And then we can say choose file, and then we can put in 1.vav, so that is the clapping sound under the audio CNN. You can also go into the dataset right here and then download one of these VAV files if you want to test out another one. Then we'll hop under here, select the file, click open. Then we can see that we now see analyzing, and we see the actual file name being printed out on the screen. If we hop under modal dashboard, and then we go under the web endpoint right here, we should be able to see the request that is currently running. So we can click that, and then this should run in just a second. Good. So now we get a 200 response back. And then over here, we can see that everything worked, and we don't really see the error message. So it seems to be working just fine. And now we just need to actually show the data on the screen. Next, I would like to take all the data which we got returned from the backend. So that is the visualization data right here. And then order those into a hierarchy of the convolutional layers and then their internal layers. Because remember, if we hop into the model.py right here, we have both the feature maps of all the outer layers. So layer 1, 2, 3, and 4. But we also pass in this prefix for internal layers, so layer 4 dot and then block 1, for example. So if we just hop into this and see how it looks, we have two internal layers right here for layer 4 specifically. So this means that under layer 4, I would like to show the internal layers. So we therefore need to create a hierarchy of the internal layers and then also the top level layers, which are these one right here. So the way we're going to do this is by looking at this layer 4 dot. So if we take a feature map and then check if it contains a dot, then we can take the first element before the dot, so before the split, and this will then be the name of the parent layer. So that is what we're going to do right here in the page.tsx. Therefore, we'll just create a function for doing that. So I'll hop up here and do this. I'll call this function split layers, and we'll pass in the visualization, which is going to be visualization data. We will say const main. This will be a string and layer data. So this will contain all the top level layers. This will be equal to an empty array. So the feature maps we find from top layer or top layers will then be appended to the following array right here. Good. Now we can also create an array for the internal layers. So we'll say const internals is equal to that'll be of the type of a record. We'll have a string and we'll have a string and layer data like this. This will be equal to a new dictionary. So the type of this is really that we have the parent name, the name of the parent right here. And then we also have the name of the internal layer as well as the actual feature map to show within that layer. Good. Now we can say for const name data of, and we can say object dot entries, and we would like to loop through all the entries of visualization. Then we'll say if not name dot includes a dot like this. So the reason for this, and then let me just open model up. The reason for this is that we can check if a layer is a top level layer or a internal layer by checking for this dot right here. So this obviously would be a top level layer because there is no dot included, but this would be an internal layer because there is a dot separating the parent and then also the name of the current layer. So we'll check if it is a top level layer by checking for this. And if that is the case, we'll then say main.push to push the top level layer to that actual array, and we'll push the name and the data like this. Otherwise, if we have an internal layer, we would like to say const parent is equal to name.split, and we'll split by the dot. So the reason we are doing this is because we'll split this entire name by the dot, meaning we'll get two separate strings out, and then by doing array destructuring like this, we'll then select the first element in the split array. So that is going to be layer 4, for example, which is the parent. So therefore we have the parent name by doing this destructuring method. Then we can say if there is no parent, so if parent is undefined, so if something went wrong, we'll then say continue and skip that. Otherwise we can say if not internals parent. So right up here we created an empty dictionary, so we'll need to create a specific entry for each parent. So we'll just check if the entry exists already. So we'll say if internals parent does not exist, then we would like to just create one. So we'll say internals parent is equal to a new array. So we can store all the internal layers for that specific parent. Then what we'll do is say internal parent, and then we would like to push the actual internal layer. So we'll say push, and we'll push the name, comma, data like this. And then lastly, we can go ahead and actually return both the main, so the top level layers, and also the internal layers like this. We of course then also need to actually use this method called split layers. So we'll just go ahead and go down to right before the code is rendered, and then we'll say if visualization data is there, then we'll call the split layers with the visualization data dot visualization. Otherwise we would like to just, and this will need to be a question mark because it is a conditional. Otherwise we'll just return main as an empty array and also the internals as an empty dictionary like this. And we'll just need to save this of course. So we'll say const main and internals is equal to visualization data. Then we can start building out the layout for actually showing these feature maps. So I'll go down to right beneath this arrow right here. Then we can say that if the visualization data is available, so if it is not null, and if that is the case, we'll render out this div right here. So this div will then say class name space y8. So we'll put a spacing of 32 pixels between every element inside the div. And I'll start by rendering out a card. Inside the card, I'll put in a card header. I'll then say top predictions, like this. Then what I'll do, just so we can follow along, is just to refresh over here, choose a file, and just let this all render out, just so we should be able to see the actual top predictions because the visualization data will be available. And now we're able to see the top predictions here. So under the card header, I'm going to put in a card content. So I'll say card content. Inside the card content, I'll put in a div with the class name space y3. Inside this, I'll show the top 3 predictions. So over here in main.py, remember we returned, if I just scroll down, we returned the top 3 predictions right here. So we took the top k, if I can find that, we took the top k here to return the top 3 probabilities. So I would like to just render those out first of all, before we even show the feature maps themselves. So we can go ahead and say visualization data dot predictions dot slice, and we'll say 0 to 3. So we take the first 3 dot map, and then we can say prediction and the index of the prediction, and then for each of these we'll render out a div. And then because we are inside a map right here, we'll need to set a key for the innermost element. So we'll say prediction.class. Inside here, we can then say class name space y2. And then we'll create another div inside of that. We'll say class name flex items center and justify between. Then inside this div, we can go ahead and put in a span. Inside the span, I'll say prediction.class like this. And then I would like to replace all of these underscores right here with just a space, just so it looks like this instead. And I also want to show an emoji for each one of these, just to make the UI a little bit more engaging to look at. So what I'll do is I'll scroll all the way up here, and then I'll define an emoji for each of the 50 classes. I've just used ChatGPT just to define this map. So I would encourage you to just hop into the GitHub repository and just copy in this map, which I'll just copy in now as well. So let me just paste this in. So right here, as I said, just go into the GitHub repo and just copy this into your code, just so you won't have to type out every single one of these, because it will take a while. So we'll have something called ESC50 emoji map. So for each class that is present in the ESC50 dataset, we'll also have an emoji attached to that. And this means we can show an emoji next to the actual class whenever we see the predictions. So now that we have the actual map, we'll just need a function to take one of these and then return the actual emoji that corresponds to it. So it's kind of a little helper function if you want to say that. So we can say const get emoji for class. This will be equal to where we pass in the class name. The class name is a string. And I would like to return a string because the string should contain the emoji. We can then return the ESC emoji map where we index in with the class name. So the one we pass in right here. And then otherwise we'll just return a default emoji. This will just be something like the speaker. So I think this is a good one. We'll just need to wrap this like that. So now we can call this where we pass in the class name right here to also get the emoji out. So let us just try and do that. We'll just do it right over the prediction here. So I'll go ahead and create a curly brace statement where I can put in, or I can call a method. And in here I would like to then say prediction.class and then just save this. And now we'll be able to see both the emoji and also the actual class. And what I'll do is I'll just wrap this in a div. And then for this div, I'll just go ahead and say class name, and then I can put in text medium. I can also put in font medium. I can also put in text stone 700. And just to space these apart a little bit, I'm just going to put in an empty space like that, just so we're able to see it a little bit more clearly. But these are only the actual classes. I also want to be able to see the actual probabilities or scores for each of the classes. And that is why I put in this flex items justify between, because then we can put in a batch right after where we show the actual predictions. So I'll put in a batch, and then for this batch I'll say prediction.confidence multiplied by 100. And then I'll say to fixed 1, and I'll then put a percentage sign after that. So I'll go ahead and do this. And I think we just need to fix some mismatched parentheses. So it's going to look like that. Then we'll say variance. And then depending on whether it is the first element or not, because the first one is going to be the one that's probably correct, so I want this to stand out a little bit more, we'll then set the variant differently. So I'm going to say if I is equal to 0, so if it is the first element, then we'll set the variant to default. Otherwise, we'll set it to secondary, like this. And then we just need to match something correctly. I think we need to put in a, like this. So we just had to change this to a question mark. And now we're able to see the top predicted class, so the one that we actually predicted is, and then also the two next ones in case that is interesting to us. We can then also just hop into Chatcn here and install a progress bar to create another cool little effect. So I'll just search for progress, find the installation command, hop into my terminal, and install that. And now that that is installed, we can hop under this div right there, and then we can put in a progress bar. Just import that from components UI progress. What I'll then do is I'll say value is equal to prediction.confidence times 100, and I'll then say class name, age, 2, and save. If we then hop back over here, we're able to see a progress bar for each one of these, just so it looks a little bit nicer and more engaging to us. Now we can then render out the input spectrogram. So under this card right here, you see how I put in space Y8. That is because we would like multiple items within this div that are spaced vertically. So right after the card, we'll put in the next item. So I'll put in a div. This div right here should have the class names grid, and we'll have grid columns 1. We'll have a gap of 6. We'll have on larger devices grid columns 2, and then I'll go ahead and save. Then I'll put in a card first of all with a card header. We can then say input spectrogram. Then for the card header, I'll just style this a little bit. I'll say text stone 900, like that. And then right beneath this, I'll put in a card content. For the card content, I'll put in two things. I'll put in the actual feature map, which is a component which we'll create. And then beneath this, I'll put in a color scale, which is another component we'll have to import as well. Cool. So let's start with the simplest one, and that is going to be the color scale. So I'll hop under my files right here, and then under source, and then we'll create a new folder called components. This is actually already there. So under components right here, we'll create a new file called the color scale.csx. In here, we'll say const color scale is equal to, and then we'll create a new component. We'll then say export default color scale, like that. And then we'll just let the user pass in a width, a height, a minimum, and then also a maximum. Good. And we'll just need to define the types for these as well. So what I'll do is just copy this and then let us define the types. So the width should be an optional number. We'll have the height, which should be an optional number, and the exact same thing for both minimum and maximum, like this. And then the width will just set to 200 per default. The height will set to 16 per default. Minimum will set to -1, and maximum will set to 1 per default. Good. Now we can render out the actual color scale. So first, we'll define a gradient which we can use to show the actual color scale, and this is going to be a CSS property which we'll just define. So what I'll do is just say const gradient is equal to, and we can create a linear gradient, and we should have a to right. We'll then say RGB, and we can put in 255, 128, and 51. This is the first color. The second color in the gradient is then going to be RGB, 255, 255, 255, so white. The next one is going to be RGB, 51, 128, and 255. Good. So that is going to be our gradient. So for the component itself, we'll say return div with the class name flex items center and gap free. And then let me just take this color scale and actually import it over here in the page, just so we can follow along as we are building it. So I'll just go ahead and import this color scale, and then also add the properties just for good sake. So we'll say width 200, height 16, we'll say minimum -1, and we'll say maximum is equal to 1. And then let me just take this and wrap it within a div. We'll say class name, margin top 5, flex, and justify, end like this. And then we don't really render out much right now, so that's why we can't see it. So let's just try and do that. So first I'll put in a span in here. Inside the span I'll put in the minimum value just so you can see that. And then I'll create some classes to this, or I'll add some classes, text extra small, and I would like to put in text stone 500. So that is the first one. I'll then create another span for the maximum value, and then we can actually put in the color bar between these. So I'll put in a div, and then inside this div, I'll just close it with a single tag actually. Then I'll say class name, rounded, border, and border stone 500 like this. Then we'll put in some styling as well. So I'll say, or some manual styling. So I'll say style, and then we can set the width. The width is going to be width pixels wide. And then for the height, we can set the height pixels high. So that is why we can pass down these props and render it dynamically. And then for the background, we'll just set this linear gradient up here. So what I'll do actually is just copy this, just because there's no reason just to define it up here. It was just to show you what it was. So I'll just set the gradient like this. So this is going to be how it will look. So we have the gradient right here, and then it is going to be aligned over here on the right side of the card. And then when we have a larger screens, we'll have two different columns, such that we can have the input spectrogram and also the raw audio, so the VAV file over here. Good. So the reason we even have this color scale in the first place is because whenever we put in the feature map, we'll be able to see what the red color means and what the black and what the blue color means as well. Otherwise, the colors won't really mean much whenever you look at the feature maps. Good. So now we have the color scale, and then we can go ahead and take a look at the feature map. So the feature map will be a component as well. So if I hop under components, new file, feature map.tsx, in here we can define const feature map, and we would like to be able to pass in the data, the title for the feature map, and also a property called internal. So if you have this feature map, will be able to render out both top level feature maps, so the ones right here, but also the internal feature maps, so these ones right here. But these ones should obviously be smaller than these ones because these are top layers and these are internal ones. So these ones should be beneath each of the top layer ones that they belong to. So that is why I would like to create a flag called internal, and if you set this to true, it will be rendered out as a smaller version than the one that we render for the top level feature maps. Cool. So with this done, we can go ahead and create types for these as well. So I'll just copy this dictionary, and then the data should be a two-dimensional array of numbers, and then I think we just need to open up the component. And then the title should be a string. And then internal should just be a boolean, which we'll just make optional just so it can be false or null, and then we won't really show it. We'll then just check the format of the data first of all. So we'll say if no data or no data.length or data 0.length, then we'll just return null, so we won't really render out anything. And then otherwise we can start by creating a canvas, and to create a canvas that shows this feature map, we'll need a map height and also a map width. So we'll say const map height is equal to data.length, and we can say const map width. This will be the data 0.length. So this is going to be the length of the inner dimension right here. So the data format that you see right here represents a 2D array. So you can think of this like a grid or a coordinate system. And then the outer array is going to be a list of rows, and the inner arrays is going to be representing a single row containing the values for each column within that row. So that is why we need to take the map height by taking the outer array, and then the map width by then taking the length of the inner array. Next, I would like to find the highest absolute value in any of the numbers within the dataset. So this includes all rows and also all columns. And the reason I would like to do this is to be able to actually normalize the data. So after finding the absolute value, we can divide every single data point within this data with that to normalize the values to between -1 and then 1. This means that the colors are going to look way nicer than if we didn't normalize, because if we didn't normalize, it would be extremely red and then extremely blue, and it would look terrible. But whereas if we actually do normalize it like this, the colors are going to look way more stable and exactly like we show them right here in the input spectrogram color scale as well. So to do this, we can first of all go ahead and say const absolute max is equal to data. We can then say dot flat. So this is a 2-dimensional array, but we'll flatten this into a single array. Then we can say dot reduce like this. And whenever we do reduce, we'll iterate over the flattened array to reduce it down to a single value. We can then say accumulator and value. So this ACC also accumulator holds the maximum absolute value found so far. It is going to start with 0, and the starting value we'll define over here as the last element of the reduce. This is going to be the starting value, and the value right here is going to be the current number for the array being processed. Then inside this reduce, we can go ahead and say math.maximum, and inside this we can put in the accumulator and also math.absolute, where we put in the value or 0 like this. So what this means is that for each number we'll calculate the absolute value. This is with math.abs, and then we'll compare it to the current maximum, so the accumulator, and then we'll return the larger of those two. And then this right here, so these two question marks, means that if value is either null or undefined, we'll just set it to 0, so it won't really be a large number. Good. So this should give us the absolute maximum value, either in negative or positive, in the dataset, which we can use to normalize the rest of the values within the dataset. We can then go ahead and just say export defaults and then feature map, just so we can render it out and see how it looks while we build it out. And then in here, we'll just say feature map. And then I would like to import that and then add the missing attributes. So we have the data first of all. And then for the data, we can put in visualization data dot input spectrogram dot values. And for the title, what we'll do is we'll say format a string like this. Then we can put in the visualization data dot input spectrogram dot shape dot, and we'll join these together with an x like this. So it looks like width x height. So we have the width times the height basically. So that is what we're going to do. And then for the feature map over here, we'll just need to render that out. So the first thing we're going to do is just return something. So we'll go down here and then we'll say return. And then we would like to return a div. Inside this div, we'll just say class name with full. And we'll say text center like that. Inside this div, we'll put in an SVG. And the SVG is what will render out all the different rectangle squares on, which is going to make up the entire feature map which we are going to build. Now below this SVG, we'll just put in a paragraph that just renders out the title. So we can then press save. Down here we can say class name mt1 to space it a little bit from the SVG. We'll say text extra small. And we'll say text stone 500 like that. And then for the SVG, this is where the heavy logic comes in. So we would like to set the view box and make it the size of the actual map that we're going to create. So we'll say 0, 0, map width, and we'll say map height like that. So the first two zeros here, 0 right there and 0 right there, is going to be the minimum width and also the minimum x and the minimum y. These will set the top left corner of the variable area in the coordinate system. These two is just going to be the width and also the height of the internal coordinate system inside this SVG which we're drawing out. And then I would like to also set another property. So we'll say set preserve aspect ratio to none. Just go ahead and save that. Then we can put in some class names. This will be this one. So we'll put in MX auto. We'll put in block, rounded, border, and border stone 200 like this. And then we would like to also say that if it is an internal one, so a smaller version of this feature map, we would like to give it some different properties. These should be width full, max width of 32. And if it is not an internal one, so it is a larger one, we'll give it width full and we'll give it max width of 500 pixels. So it is just going to be a little bit larger if it is the top level one, instead of this one where it's only 128 pixels. So it's going to be about 4 times as large if it is a top level spectrogram or feature map. We can also put on for this one over here, so if it is not internal, a max height of 300 pixels like this, and we can put on an object contain like this. Good. So these will be the properties which we will need for the SVG. Inside this we can loop through all the different values right here in data, and then we can build out small rectangles and make it look like a full-scale feature map or heat map. So what I will do is say data.flatMap. So we'll flatten the actual multidimensional array and then loop through each one of these in a map. Then we'll get row and index. What we can then do is say row.map. So we'll loop through every single item in each row. Inside here we'll get the value for each of the elements and j. Then we can normalize the value. So we'll say const normalized value, because in here we'll have the specific, so value right here is going to be a single value from this multidimensional array, so a single value in the coordinate system basically, and we'll just need to normalize those. So we'll say is equal to absolute max, and if that is equal to 0, then we'll just say 0, otherwise we'll take the value divided by absolute max like this, and that should then normalize that value. Down here I'll just put in a return statement just so we return something. And then I think we are missing one of these end parentheses. So we have some kind of mismatch between the parentheses. So I think that we might want to put in one of these, and then it should be fixed. And then right now I just want to get out the actual color values for this value right here. So I'll say const and then RGB. And then we will just create a little helper function called getColor, where we can put in the actual color of the pixel up here, and then we can get a color value out, because right now the feature map is just grayscale, but we would like an RGB value out. So we'll just need to convert the normalized pixel value to RGB, and then we can render it out as a rectangle. So we'll go ahead and create a little helper function. So we'll go into lib, and then we'll say new file. In here we can say colors.ts, and then let me just do this. So in here I'll say export constant get color is equal to value, which is the number. So that is just the grayscale value or the brightness of that pixel. And then I would like to return 3 different numbers, R, G, and B. And then we can say let R, G, and B be variables. If the brightness is then, so if the value is then less than 0, more than 0, sorry, so there is actually a brightness, then what we'll do is we'll then convert these into blue values. So first of all, let me just see if I can comment this out, and then also comment this out, and then just select one of these just so I can show you what I mean. I'll just wait for this to finish. So as we set down here in the color scale, if we have a negative value, so a value between -1 and then 0, we'll render it out as a red pixel, and we'll render out the strength of the color depending on how negative the value is. We'll do the exact same just for a blue value if the value is between 0 and 1. So that is what I'm trying to do up here. So if we have a value that is more than 0, we would like to render out a blue color. So that is what we'll do now. So we'll say red is equal to 255 times, and we'll then say 1 minus value times 0.8. That is the red. We'll then also define the green. the green will be 0.5 here instead, and then the blue is just going to be 255. So we'll have full strength for the blue color channel, and then we'll have a toned down version of the red and also the green color channels, because we multiply these weights of 0.8 and 0.5 onto those channels. Good. So that was for the blue. Then we can say else, and then if else, then we would like to do the same, but we'll turn up the red color channel completely. So we'll say 255 for the red, and then let me just take this one, paste it down here, and then for the blue channel we'll make that a 0.8, and then the green channel is going to be 0.5 still. Cool. So now we have defined the different RGB colors depending on whether we're in a negative or a positive range. Then we can go ahead and actually return the values. So we'll say math.round R, math.round G, and math.round B, like that. Cool. Then we should be able to hop back into our feature map and just use this method. So we'll say getColor, call this, where we pass in the normalized value. Then I'll just take this and import it. And now we should be able to actually render it out. So for each pixel, what I would like to return is a rectangle that will be rendered within this SVG box. And then a rectangle, let me just close it like this instead. A rectangle should have a key, and we should have the key be based on a dynamic string. So we'll say I, and we'll say J, because these coordinates will always be unique to the specific rectangle. Then we'll say X is equal to J, and we'll say Y is equal to I. So this is where it is going to be positioned. Then we'll give it a width of 1, and we'll give it a height of 1 as well. Then we can say fill. So this is going to be what the fill of the rectangle actually is. And what we're basically doing right now is that we're rendering out every single pixel in this feature map. And then the fill should be RGB. And we would like to put in the R value. We would like to put in the G value. And we would like to put in the B value, like that. So if I go ahead and save this and then hop over here and then pick a file, hopefully we should be able to see something. So I'll just wait for this to finish. And it seems like it is rendering fine, but we have a little problem. We can only see blue colors right now, and we can't really see the red colors. So it seems like the red colors are being rendered out incorrectly. So I'll just figure out why that is, and then get back to you. So here's what I found. Whenever we have a value that is supposed to be blue, so a value that is more than 0, this is all fine, because let's say value right here is 0.5, and then we multiply that by 0.8 and then subtract that from 1. Then we still get a positive value between 0 and 1. But if we have a value that is negative down here, let's say we have minus something right here, well then we can't really subtract this negative number from 1 and then still always get a positive number between 0 and 1. Therefore we would like to make this a plus instead, both right there and also right. And whenever I save this, I think we should be good down here. Yeah, so now we are able to see the red colors just fine. And if we didn't put in a plus right here for the red values, then these values might become outside the range of 0 to 255, which is what R, G, and B allows. And that is why we couldn't see any colors right here, because they were probably outside the values of what they were allowed to be. So that is why we say plus right here and then minus up here. And now we're able to actually see this input spectrogram. So this is how it is going to look. We have the spectrogram where we can see positive values as blue and negative values as red. Good. So let me just close down this feature map because we're done with that. Then next to this input spectrogram card, I would like to show another card, and that should be the raw waveform. So I'll go ahead and just remove the following right there, and then just say audio waveform like this. And then for now, we don't really have any components that can show this raw audio waveform. So we'll just wait with implementing that until a little bit later, and then we can show the other feature maps with this component that we just implemented first. So if we go beneath this diff right here, we can just say feature maps, make that a comment, and then we can put in a card with a card header. And then inside this card header, we can put in a card title. Inside this, we'll say convolutional layer outputs, like that. And I'll just import this card title like that. And then down here, and I actually forgot to put in this card title the other places. So let me just do that. I'll just take the card title and just do this for both the audio waveform. So right there. And also for the input spectrogram up here, just so we have cards that look alike, like this. So now they all look the same. I'll just do it for the top predictions up here as well. I think I forgot that. Yep, top predictions. And now that is fixed as well. So now going down to this new card, which we just created for the convolutional layer outputs, we can just go ahead and show the actual feature maps. So I'll hop into the card and then I'll create a card content. In here, I would like to put in a div. I'll then create a div with, a grid with 5 different columns. And the reason is that we have 5 different layers I want to render. We have convolutional 1, 2, 3, 4. So that is 5 in total. So I'll say class grid columns 5. And I'll say gap 6 between the different grids. In here, we can go ahead and say main layers. I think we need to spell this correctly. Main layers dot. And let me just see whatever we called it. We just called it main. So we'll say main dot. And we can then say map. And we can get the main name. And we can get the main data. And what we'll then do is render it out. So we'll say div, and because we're inside a map, we'll need to specify a key, a unique key for each of these elements. This will just be the main name. What I'll then also do is just say class name space y4, and I'll say div. Inside this div, I'll put in an h4 where we say main name. Like this. So now we should be able to see the names of the 5 convolutional layers because we have 5 different returned from the API. Then I can also say class name mb2 font medium and text stone 700 like this, just to make it look a little bit nicer. Right beneath this, I'll put in a feature map. So this means we render out a feature map for each of these, this one, etc. So these are the top level feature maps. The data is going to be the main data.values, and the title is going to be the main data.shape.join together. And we'll join them together by an X, just like we did before. So this should render out these different feature maps. So if we open it up, we can now see the different feature maps being rendered out as they should be. Cool. So with that done, we can go ahead and maybe just make this a little bit wider because right now they're pretty small. So I think we set it to, was it 60%? Yeah. So maybe if we set this to 80% or even 100%, this should be way better. If set it to 100% right here, now we can see it much more easily. Also, when we open it up like this, we'll be able to see all the convolutional layers in much higher detail. So as you can see, all these small different rectangles are the rectangles which we render out. So if I go to feature map, these are those specific rectangles. They have a width and then also a height, and then they have a position each. So this position of both the X and the Y is what we see down here. So this is 0.0, 0.1, etc. And these are then all the pixels that comes from this data. Cool. So these are then the outputs of the convolutional layers. So we have the input spectrogram, we feed this into the convolutional neural network, and then we get this out. So this is the first layer, this is the second layer, etc. And then we can see how it starts out more complex, and then it continuously becomes more and more abstract until we only have a 4x14 pixels feature map over here at layer 4. Great. So now that we have the top layer or top level feature maps, let's go ahead and render out the internal feature maps, because that can be pretty interesting as well to look at. So going down here, this is where we render out the top level feature maps. And then for each of these, we'll just also render out the internal layers. So this will be internals. And then for the internals, we can index in with the main name. So this means that we are looping through all the different mains, and then we'll find all the different internals for that specific main by doing this. We'll then say and diff. We can then say class name age 80. I'll then also just say overflow y auto, rounded, border stone 200, bg stone 50, and I'll say padding of 2. This will create a rectangle of height 80 under each of these that do have internal layers, and then we can render out each of the internal layers inside this rectangle. And if they in total make up more than age 80, then we'll be able to scroll up and down. Good. So inside this diff, we'll create one more. We'll create a diff with the class name space y2 to make some vertical spacing between these internal layers. I'll just put in an end tag as well, and then I'll say internal main name, and then I can say dot sort, and I'll go ahead and do this a dot local compare b. So what this will do is just sort all of these internal feature maps alphabetically, and then after sorting them, we can just go ahead and say map to loop through them, and then we'll get the layer name and the layer data. And we can then render out a feature map for each, like this. And then because we're inside a map, we'll need to specify the key. So I'll say key, and the key is going to be just the layer name because those are going to be unique. The data is going to be the layer data dot values. The title is going to be something like layer name, where we replace the main name dot with just nothing. And then lastly, we can just put in that this is a internal one. So we'll just say, I don't remember what we called this prop actually. We called this prop internal. So we'll just set the internal prop to true by doing this. True. And I just figured out that I put it inside this wrong parenthesis. So we just need to do it outside here because it is a property. So now these should be rendered out as smaller versions of the large ones up here. So we can actually just try this out. And also, by the way, the reason that I removed or replaced all of these main name dots with nothing is because otherwise we'll see, I'll just show you actually, it is way simpler. So I'll just open this one up and then come back whenever this has been analyzed. Great, so it just finished analyzing. And then if we scroll down, we'll be able to see all the different internal layers. So we have block 0 to convolutional, block 0.relu, etc. And then the reason that I put in this replace down here is because if we hop into the actual model, the internal layers are named by, let me just find this, I think it's all the way up here somewhere, a prefix and then dot convolutional. And then the prefix is going to consist of layer 2, dot block, dot, and then convolutional. But right here we only see block.convolutional. So because we already put these feature maps under this layer 1, I don't really see the need for also displaying layer 1.block0.convolutional because it's pretty easy to see that these are a part of this one up here. So I just removed the name of the parent feature map such that it looks a little bit more clean. So now we can see the internal layers as well for all of these different convolutional layer outputs. So that is pretty neat to see. And then lastly, I also want to just render out the actual audio waveform. So the VAV file, which is what is used to actually generate the spectrogram. So let's just go ahead and do that. We'll need a specific component to generate this or to display this audio waveform. So we'll need to just go ahead and create that. So I'll go under components, new file, and then I'll say waveform.tsx. In here, we'll be able to say const waveform is equal to data title. Data is going to be a number, series of numbers, because remember the waveform is just a one-dimensional data. We only have a single array of numbers, and these are just the samples. And then we'll have title, which is a string. And then down here we can say export constant waveform, like that. And then we'll just be able to import this in a second. I think we'll need to say export default, like this. And then when we hop back in here and then find the audio waveform, we can just put it inside of the card content. All right, so I'll put in the waveform, and then I'll put in the data, which is going to be visualization data.waveform.values. Then for the title, I would like to put in the visualization data.waveform.duration.toFixed. So 2 numbers, and I'll say seconds. Then I would like to say visualization data.waveform.sample rate, and I'll then say hertz, like this. Good. So right now this waveform isn't imported, so we'll just import that. And then let me just see what it is complaining about. Waveform cannot be used. That is because we don't really return anything yet. So I'll just go ahead and say return React fragment. And then I'll analyze the file just so we can see it while we develop it. Then inside the component, what we can do is first do a guard statement where we check if the data is valid. So I'll say if not data or data.length is 0, then we'll just return null, so we'll render nothing. We'll then also define a width and a height of the actual canvas which we'll draw. So the width is going to be 600 and the height is going to be 300, like that. And the center where we'll show the actual x-axis is going to be the center on the y-axis, so that is going to be center y, and this will be equal to height divided by 2. So under this we'll be able to say const valid data is equal to data.filter. We can loop through all the different values, and then if any of the values were to be not a number, for example, so if is not a number, and we'll say and is finite value. So if any of these are not a number, they'll be filtered out, or if they're infinite, so minus infinite or infinite, they'll also be filtered out. This just ensures that we can actually render out the actual audio waveform, because otherwise the rendering would fail if we had another number, for example. This should not happen, but we'll just keep this filled just to make sure that it doesn't happen in worst case. So then we can say if valid data.length is equal to 0, then we'll just return null, because then there isn't anything to show anyways. Now we can then create some code that is going to be responsible for taking the array of raw audio waveform data and then converting that into a string of commands that we can insert into an SVG path. So if we have an SVG tag right here, we can put a path into that. So a path is going to look something like this. So we'll render out this path specifically in the code right here, and then we'll insert the path that we actually create into an SVG tag down here in the return statement. So that's what we'll do right now. And the goal is basically just to map each audio sample to an XY coordinate system, which we can then plot on this 2D canvas, so within the SVG area. And then each of these points on the 2D canvas is going to be connected by lines, so it looks like we have a continuous signal, even though it is sampled. So first we can find the signals minimum and also maximum vertical boundaries, so the biggest values on the y-axis, both in the positive and in the negative range. So first we'll go ahead and say const minimum is equal to math.minimum ... valid data, like this. We can do the same just for maximum. We'll just say .max. Next we can say const range is equal to math minus minimum. This is going to be the range on the y-axis that the signal spans across. We can then create another variable called scale y, and this will be equal to the height, which we defined up here to 300 times 0.45. So this scale y will determine the maximum vertical amplitude of the signal. So if this is a big number, then the signal will reach very high and very low when drawn in the canvas. But if this is a very low number, then it's going to be very compressed and not take up a lot of space on the y-axis. So next we can actually generate the SVG path data string. So we can say const path data is equal to the valid data dot map. And then for each of these validated data points, we'll get a sample and then also the index of that sample. So in here we can then say const x is equal to, and I would like to distribute the points, so every single sample, evenly across the horizontal space. So first what we can do is we can say I, that is the current number. So let's say there is 100 samples in total and the index that we are currently at is 10. Well, this means that this should be placed 10% across the width of the actual canvas. So we'll say I divided by valid data dot length minus 1. This will give us 10%, for example, if this is going to be, if this was the index number 10. Then what we can then do is multiply this by the width. So this will then also be dependent on the width. So this means that if this was index 10 and there was 100 samples in total, we would then have this point be placed at width 60 or at position 60 on the x-axis. The y value where we want to place this point is going to be just on the center y, right there. So this is just going to be the default value for the y, but now we want to actually calculate the correct y value. So we would like to convert the audio sample's amplitude into a vertical pixel position. So the way we're going to do this is first by checking if the range is positive. So if max minus minimum is more than 0, because it definitely should be, otherwise we might get some division by 0 errors later on. So we'll say if range is more than 0, then we can go ahead and say const normalized sample is equal to, and we'll say sample minus minimum divided by the range like this. So this will convert the raw sample into a consistent range between 0 and 1. So if a sample, for example, has the value that is minimum up here, it is going to get the value 0. But if a sample has a very high y value that is closer to max, then it is going to get the value 1. But here the samples are going to be between 0 and 1. But what I would like to do is have samples be between minus 0.5 and 0.5. Because if we do this, this means that the x-axis can be placed at the y value 0, meaning that samples can both be below and above the x-axis. So to change the range from this and then to this right here, what we'll do is go ahead and say y is equal to sender y minus normalized sample minus a half times 2 times scale y right here, like that. And then we can go ahead and create the actual path value, which we'll embed into the SVG tag. So first we'll say return. Then I would like to say if I is equal to 0, then we'll put in an m, otherwise we'll put in an l. So m is going to be move first point to, that is what that means in an SVG, and l means move to for any subsequent points after the first one. So the first one must start with m, and then after this, what we'll put in is x dot to fixed 2 and y dot to fixed 2 as well. And I think we just put in one too many of these, or maybe we forgot one right there. And then because this is done for every single sample, because we're inside a map, we can then take all of these different points right here, and then we can join them together into one single string, where we put in a space between all of these, like that. Then we can start to implement what it should return. So I would like to return a div with the class name flex, height full, and width full, and flex column. In here I'll put in another div with the class name flex, flex1, items center, and justify center. Right outside this div I'll put in a paragraph where we can show the actual title of the waveform, like this. And I don't really know why it is not rendering. Maybe I should refresh over here and just try to do this again. And then in the meantime, we can just style this title, empty2, text center, text extra small, text stone 500, and save that as well. Then if I scroll down, now we're able to see the title like we are supposed to. Then inside this div right here, what I would like to do is just create an SVG. Inside this SVG, we'll just define a couple of things. We'll first define the view box. This is going to be 0, 0 for the top left corner, and then the width and the height, which we defined earlier up here. Then we can also define a property called preserve aspect ratio. And in here we define what happens if there are mouse space available, then the SVG will take up. So if we set X mid and then also Y mid, we'll need to make this X small actually. And then we set this to meet. This will then center it and then keep it in the middle. So basically we'll center it horizontally, we'll also center it vertically. And then together these two means that we'll center it both horizontally and vertically within the available space. Next, we can put in some classes. We can put in block, max with full, rounded, border stone 200. And then inside this, we can also put in a max height of 300 pixels, like that. And then inside this SVG, we can put in a path. We'll just close it like that. Then we can put in a D, that is going to be for the data. So D should be M0 center Y. Let me just spell this correctly. And we'll then also have H and the width like this. So this is going to be the center line, aka the x-axis. We'll also set a stroke color. The stroke color should be E7, E5, and then E4. We can then also just set a stroke width. And the stroke width should just be 1. Then I think we need to actually go ahead and re-render this over here, re-render the entire page before we are able to see the changes. So that is what I'm just going to do. I just re-rendered the page, and then down here we can see that we have a border now, and we have an x-axis right here in the middle of the y-axis. Good, so that is exactly what we wanted. And now we can just render out this entire path right here of the different points which we joined together. And that is actually going to be a path just like this one, except that the data is going to be different. So the data right here we can pass in as the path data, and then we'll just say fill is equal to none. We'll also set a different stroke, so I'll just say 444 and then 30C, 03C. The stroke width will be a little bit wider, and then the stroke line join is going to be round, and the stroke line cap is also going to be round. Now I'll just need to refresh over here again, like this. And now that it is done, we can scroll down, and this is what it is going to look like. We have the actual audio signal both being above and below the y-axis. So this is what it looks like. We then also see the duration down here times the sample rate. So you're able to see that as well. Good. If I just make the screen a little bit larger, we're able to see this in much more detail. We can see the audio waveform, the input spectrogram. We can see each convolutional layer output, and also including the internal convolutional layer outputs as well. One more thing I would like to add is just this color scale right here, just for the convolutional layer outputs down here as well. So this is luckily pretty simple to do. If we hop into the page and just search for color scale, we can actually just grab it and then scroll all the way down to right before the card contents. This should be good enough. And now we'll be able to see the color scale down here as well, just like we wanted to. So now that we have rendered all of this out, let's take a look at some of the data and then actually take a look at it to see if we can figure out some meaning behind the data, and then also what happens internally inside of the convolutional neural network. Alright, so before just doing that, I just want to correct one more thing. I think it's kind of a shame that we aren't fully utilizing the space of this card right here for the input spectrogram. So I'll just make a property that styles this feature map a little bit differently if it is the input spectrogram compared to if it is one of the convolutional layer outputs down here. Because right now they're styled in the same way. So what I'll do is I'll hop into the feature map, then I'll put in a spectrogram property. This spectrogram property is just going to be an optional boolean. And then over here at the feature map for the input spectrogram, I'll set this to true. So I'll just do this. Then down here, what I'll do is I'll say if it is not internal, then we'll also do an additional check for if it is a spectrogram or not. And we'll do it by doing this. If that is the case, so if we do have a spectrogram, we'll set it to with full and object contain. And now over here, this will be styled just like it normally was, but this input spectrogram is going to be much larger. So it's going to be much clearer to look at. So that is just what I wanted to do. Let's now talk about what we see. We can start with the audio waveform here. So because we have uploaded the clapping file, it makes sense that we have these short bursts of energy. So clap, 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 etc. throughout the entire clip. So that is basically what we see with these super high amplitude peaks. So right there, etc. throughout the entire 5 seconds. Now for the input spectrogram over here, we can see that we have the x-axis, that is going to be time. We have the y-axis, that is going to be different frequencies, low down here and high up here. And then we have the amount of energy per frequency, which is going to be the color that is measured in decibels. And just like we had different bursts of energy because it is a clapping clip, so a burst, 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 etc. We can also see how these carry over to the input spectrogram. So we can see these vertical orange lines, and this means that every single clap spans across multiple different frequencies. We can see though that the claps trigger the low frequencies more, that they appear up here in the high frequencies. And that also makes sense when you think about what a clap sounds like. So as I explained earlier, whenever we trained the model, or even before that when we went through what Mel Spectrograms even is, or even are in the CalDraw file, the transformation from this audio waveform format and over to the Mel Spectrogram turned this audio problem, as you see over here, into an image recognition problem, because these vertical stripes are key visual features that the CNN can then look at to identify that this is a clapping sound that we are looking at. Then scrolling down to the convolutional layer outputs, so the feature maps right here, we can see how the model visualizes or sees at different stages of processing throughout the different layers in the neural network architecture. You need to remember though that these feature maps right here are aggregated. So for example, if this one it would output 64 different channels, then all 64 different channels are aggregated into a single feature map, such that we don't have to have 64 different feature maps for each one of these, which would be quite a lot of maps to look at. A pretty cool thing though is that you can see some similarity between the feature maps right here and then the input spectrogram, which we do feed into the neural network. We can see how the low level frequencies down here, which are pretty active in the input spectrogram, and also the vertical lines are clearly visible in the feature maps that come out of the convolutional layers, both in the first convolutional layer right here with a 7x7 kernel, and also in the second convolutional layer right here containing 3 residual blocks. As the output of this convolutional layer 1 passes through layer 1, of convolutional 1 right here passes through layer 1, 2 and 3, we can see that these lines, so the vertical lines for example, become more and more abstract and more pixelated as well. So the feature maps in general just become more abstract and also smaller in size, as you can see on the pixel dimensions down here. So we start out with quite a lot of pixels, and then we go all the way down to 4x14, which is way fewer pixels. So these sharp lines, as you see right here, all the vertical lines, they just begin to blur and then they consolidate into more generalized blobs that doesn't really make much sense for us when we look at it. At least on this convolutional output and this convolutional output, we can see some resemblance between the input spectrogram and then also the feature maps. But as we move further across the layers, we won't really see much resemblance at last, because it just becomes too abstract for us humans to understand. We still are able to see that these low-level features up here are extracted both in layer 2 and also in layer 3, but those features are kind of abstracted away over here in layer 4, where the output, the feature map is very abstract. So at layer 2 and also layer 3, what we are hoping is that the network is no longer just seeing lines like we do over here in convolutional 1 and layer 1, but more so learning what a percussive event even is. So a percussive event meaning whenever you clap, for example. And then for the layer 4 over here, you can see how many pixels we have. Well, all of these different pixels are then distilled down into these 4x14 pixels, as you see. So the audio cliff has basically just been reduced down to its most essential characteristics, and these are then fed into the fully connected layer that is used to make the prediction of this being a clapping, as we see up here. And then we can also just talk about the view of the internal blocks down here. So remember how we built our model using residual blocks, and then each of these residual blocks would have 2 convolutions and then also a ReLU layer coming after that. So after this the output of this block 2, the convolution, is then the feature map after the main 2 convolutions have been done and also the shortcut connection been added. But this is going to be before the output have been passed through the ReLU activation function. So what you, for example, can see is that before ReLU, you have some orange, and this indicates we have negative values. But as we saw in the Excalibur, ReLU takes all negative values and make them 0. So that is also why you see all the orange disappearing when the input has been passed through, when the feature map has been passed through the activation function of ReLU. So this is before ReLU and this is after ReLU. So that is what we see with these different internal layers as well. For the first layer down here, if we take a look at the internal layers, we can see that it really focuses in on the lines. So the lines are a little bit blurry up here, but then it focuses in on the lines such that they become very clear down here at the end. So that is pretty interesting to see. Then over here in layer 2, we can already quickly start to see that the features are becoming more abstract. So because the spatial dimensions right here are halved, we are forcing the network to summarize what it learned over here in layer 1. So these sharp vertical lines that we saw over here in the internal layers are becoming less distinct, as we can see over here, and just beginning to merge into broader regions of activation basically. So maybe over here the network is moving from just detecting these simple lines as we did in layer 1, and then moving to learning what the concept of a line even is, or maybe even what a cluster of lines mean. So these are just basically complex of features that it is able to extract from what it previously received from layer 1. Then over here in layer 3, we have a very significant increase in abstraction. So in these two, we were at least able to see a little bit of the lines. Over here, they're very clear. Over here, they're not as clear. But over here, there isn't really anything at all that we are at least able to see related to the vertical lines from the input spectrogram. We still are able to see these different low-level frequencies down here, so they are still preserved. We are also seeing some more orange over here in layer 3, especially also in layer 4. And this presence of orange really shows that the network is starting to learn more complex things, because whereas the blue shows the presence of certain features, the orange might show the absence of features. So the network is now learning a more nuanced understanding basically, which is really good, and also what we kind of would expect in these later layers. And then over here at layer 4, we see that after every single residual block, we get a lot of orange out in the feature maps, which ReLU then resets to 0. So we have a lot of complex learning over here in layer 4, where the feature maps are also very abstract. So over here, even though it's pretty cool to look at, it doesn't really make much sense to us because we can neither see any of the lines, so the vertical lines, or we can neither see the low frequencies over here. It is simply just too abstract to show any of these low level features. But this is all good though, because as we can see, we have about an 85, I think it was 83% accuracy on the model which we trained. So we know it works. Great. So that was a little walkthrough of the different diagrams which we have just created and also what they mean. And then I hope you learned a little bit about convolutional neural networks and how they work, because now you have at least tried to train one and also kind of visualize what it does with the data when data is passed in through the model, and then all the way up until a prediction is made. So before we end the video, let's just hop into Excalibur and talk a little bit more about the things that we haven't yet covered. First, I would just like to talk a little bit about the results we actually got in this video. So first of all, we had 50 different classes to pick between in this ESC50 dataset. This means that we have 50 different options to pick between. So if we just had a model that was not trained and was just randomly guessing different classes, random guessing would be about 2% accuracy, because if you take 100 and divide this by 50, then you get 2. So we would have about a 2% accuracy if we didn't train the model. So that is the baseline which we are trying to improve upon. We trained our model to become around 83%, but the best model that I have trained with the exact same hyperparameters and the exact same dataset was 86%. So if you take 86 and then divide this by 2, you'll be able to see that we have a 43-fold improvement compared to the baseline, which is really great. And this also really stresses the how powerful these convolutional neural networks are, because they are really good for classification tasks such as the one we did in this video. Next, we can talk about some of the exercises that you could do to learn a little bit more about convolutional neural networks, or a lot more if that's what you want to do. So first of all, a pretty simple thing you could do is just retrain the model just with a different amount of layers, for example, a different amount of in or out channels, or some different hyperparameters. So you can see exactly what this does to the accuracy, because you can basically just change the amount of layers and then hit modal run main. And this will then retrain the model and then print out the accuracy. So this is a pretty interesting low effort task where you can just play around with the CNN and just use some of the modal free credits to just see whatever happens to the model whenever you change some of the hyperparameters. Another thing you can do that is a little bit more challenging is actually training the model just in a different audio dataset. So we are just basically set up to do audio classification, because this ResNet architecture is pretty general and also very powerful. You can both do image classification but also audio classification with it. So you can definitely try and find another dataset and then try and train the model on that dataset without changing much within the architecture. So try and do that if you want a little bit more challenging tasks. One more task you can also do is just think about the model architecture and then try and talk to someone or write down what the different layers do in the architecture that we built and also why they're necessary. For example, why is there batch normalization layers? Why are there dropout layers? Why are there residual layers? And why are there shortcuts? So if you really want these different concepts to stick and you want to remember them for the future, it's really good to just try and write down why they exist, just so you think a little bit more about the architecture. And maybe you can also do some research on your own about the different layers, just so you know what they are. So you maybe be able to use them in the future as well, because you will run into a lot of these same different architecture principles and also different layers in future architectures in neural networks that you'll build. Great. So thank you so much for following along with this video. I really hope you learned a lot about convolutional neural networks, both how they work from a theoretical standpoint and also a little bit about just how basic neural networks work, and then all the way up until how you can build something with it that has an actual use case. So thank you so much for following along in the video, and then I'll see you in the next one.